Continue recording. Speaker not working properly. Check my speaker diyor. Çok önemli değil.
Tamam.
Good morning. Nice. Speaker.
Good morning hocam.
Morning. Just. Yeah.
Merhaba.
Morning, Nash.
Good morning.
It's here also. Just looking for our first speaker now, Denin, which is absent now. But we have a few minutes for. Now, if Nazanin isn't able to attend first, you can go first with your presentation. Is that fine?
Okay.
Great. Thank you. I think Ertuğrul is here also, but he just attend as a attendance, not panelist. Maybe we can check it.
Günaydın.
Günaydın.
Günaydın. Günaydın hocam.
Bir iki dakikamız var. Bir bekleyelim isterseniz. Bir konuşmacımız yok hala. Onu Pınar'la şey yapacağız, başlatacağız bu durumda.
Bekleyelim mi hocam yoksa başlayayım mı?
Bekleyelim, bir iki dakika bekleyelim, öyle bir açılış
Tamam.
edelim, öyle gireriz. Tamam.
Tamam.
as we see here. Yeah, we are just unable to attend the session. Okay, not possible. Hearing. I'm just waiting a few more minutes to start the session. Since the other panelists are not able to attend right now. Okay, maybe we can start with our first speaker. Firstly, welcome to 8th session on green energy. We have 6 presentations like the green energy. First, I'd like to start with the second presentation. Our first speaker is not available right now. The presentation title is about the capital energy substitution in Turkish manufacturing firms, role of firm size. The presenter is Pınar Sezer. Pınar, could you introduce yourself first with a few sentences and then you can share your presentation with us?
Okay, thank you. Hello, my name is Pınar. I'm a research assistant in Hacettepe University, Department of Economics. Today, I will present you my work on capital and energy substitution. And now I will share screen. Here is the presentation plan. First, I will talk about the motivation and I will talk about literature for a short time and the purpose of the contribution. And after that, I will say a few words about theoretical framework, data, and empirical analysis. And at last, I will talk about results and conclusion. The motivation of this work is the oil crisis in 1973. And after the oil crisis, we see that the energy is included in the production factors, production function as a production factor. And but in the first 2 studies, there are conflict results, and we see a literature which is trying to understand the different results in the literature. And the substitution elasticity. The substitution elasticities are important in energy, environment, and investment policies. And coefficients, there are also coefficients in the general equilibrium models. Contribution of elasticities to the important topics in energy economics literature is also an important motivation for these studies. In the literature, we see the pioneer works of Bardon and Booth and Griffin and Gregory, and these 2 works had different conclusions about the relationship between capital and energy. And they used aggregate and sectoral data. And we say that this contradictory results in the literature is a permanent thing, and there are also attempts to explain different results. But on the other side, there are some common characteristics of these studies. For example, the functional form and the measure of substitution, which is used in the studies, and the econometric method used in the studies. After the influential work of Solow, there was a different path in this literature. And Solow suggested that this relationship between capital and energy production factors should be examined by microeconomic data. So we see a few macro level studies in the literature. This suggestion was accepted in the literature, but the problem was there was a limited data for microeconomic data. So we see a few studies, only 6 until now, and they are all for only developed countries. And to our knowledge, there is only 2 factor substitution studies in Turkey, and they use aggregate data, and they work on a very late data set. In this study, I used microeconomic data and used the recent data set. The purpose of this study is the calculation of substitution elasticities between capital and energy for Turkish manufacturing firms between 2005 and 2013. First, I calculated on price and cross price elasticities and Morishima elasticities for the firms in general in manufacturing industry, and then grouped firms based on the firm size. And the contribution of this study, it is the first study calculating factor substitution in macro level in a developing country, and one of the few studies which calculates Morishima elasticities. And this is the theoretical framework of the very basic theoretical framework of the study. As I said before, after the oil crisis in 1970s, there is an inclusion of energy as a production factor to the production function. And using the production function or the cost function, we can calculate on price elasticities and cross price elasticities and Morishima elasticities. And this information gives us how does the energy demand change as the energy price changes. On price elasticity tells us that. And the cross price elasticity of energy coefficient tells us how does the demand for capital change as the energy price change. And at last, Morishima elasticity tells us how does the capital to energy ratio change as the price of the energy change. By looking at this coefficients signs, we can have information about relationship between energy and capital in the production process. For example, when we look at the coefficients cross price elasticity, if the sign is smaller than 0, we say these 2 production factors are complements. If the sign of the coefficient is larger than 0, we say that these 2 production factors are substitutes. On the other hand, we can also comment Morishima elasticities, and it is a better measure of substitution elasticity. If the Morishima, if these 2 factors are substitutes, the coefficient of the Morishima elasticity will be bigger than 0, and if they are complements, it will be smaller than 0. At first, in order to calculate these elasticities, you have to choose between a production function or a cost function. In the literature, there's a lot of studies which is focused on the production function due to data limits. I had a chance to choose cost function, which can be a better beginning point. In the literature, functional forms are very common, and the most common used function is the translog, and I also choose translog function. And measure of the substitutions are Elin-Uzova, cross price elasticity, and Morishima. Elin-Uzova is widely used in the literature, but there is some discussion about Elin-Uzova, and some researchers suggest that Elin-Uzova doesn't add any information to cross price elasticity. So in my work, I choose cross price elasticity and Morishima in order to calculate the substitution elasticities. The data I used was firm level data, which includes these years. There are 10 sectors and over 50,000 observations. And in order to calculate the elasticities, I combined several data sources. The most important one was the annual industry and service statistics, which was in the Turkish Statistical Institute. And there was a huge and long data mining process for firm level data. After this, I combined the data I prepared with energy balance sheets and sectoral energy consumption data. And there were 3 steps of the empirical analysis. And first, I estimated the transport cost function and factor share equations simultaneously using iterative, seemingly unrelated methods. After that, I calculated on price and cross price elasticities. And using these elasticities, I calculate Morishima substitution elasticities. And I repeated these stages for manufacturing industry as a whole and for all the firms grouped by the firm size, which was small, medium, and large. And here are the results of the coefficients. It is the first results are for the manufacturing industry, and I highlighted the coefficients I was focused in the context of this study. As you can see, this one is the cross price elasticity of the energy, which is trying to find the answer of what happens to capital demand when the energy price increases. And this coefficient suggests that there's a weak substitution between energy and capital. And it is positive, so it indicates substitution, but it is very close to 0, so we can talk about a weak substitution. And I would like to emphasize that cross-price elasticities show the economic possibilities of substitution. On the other hand, Morishima substitution elasticities indicate technical substitution possibilities. And when we look at the Morishima substitution elasticities, we see a strong substitution relationship between capital and energy in manufacturing firms. And these 2 results are compatible with literature. And we see that the cross-price elasticities of energy price and capital price are asymmetric. They are not the same. It is also important for the literature. And these are the results of the second analysis. In this analysis, I calculated cross-price elasticities and Morishima elasticities for all of the firms grouped by firm size, small firm, medium firm, and large firm. And you can see the definition of this firm size below the table. And here is the coefficient I was looking for. And when I see the cross-price elasticities, I see that they are not affected by the firm size. As you can see, they are very close to each other. But there is an outstanding result here. We can see that as the firm size increases, on-price elasticities also increase. It is which is these coefficients. As you can see, as the firm size increases, the on-price elasticity of energy increases also. And when we look at the Morishima elasticities, we also see that they are affected by firm size, which indicates as the firm size increases, the technical substitution possibilities also increases. What does these calculations mean? Substitution between energy and capital in Turkish manufacturing firms. When we look at the cross-price elasticities, we see that there's a weak substitution, and the cross-price elasticity of energy is not affected by the firm size. On the other hand, we have a different result regarding Morishima elasticities. There's a strong substitution, and Morishima elasticities increases as the firm size increases. Which means Turkish manufacturing firms have technical substitution potential, but it is limited by income effect, which occurs after energy price increases. I want to emphasize that cross-price elasticities includes both income effects and substitution effects. And when we look at the cross-price elasticities, we see the economic possibilities of substitution. But the Morishima elasticities indicates that Turkish manufacturing firms have technical substitution potential, and especially as the firm size increases, this technical substitution possibility also increases. It's an important finding, I think. And these results have some important consequences regarding energy policy. As we know, when we are designing energy policy, we can have different kinds of policies. And for example, some countries prefer to design energy policy using energy price policies. And these results also have some indications about that. As you can see, as the price of the energy increases, the energy demand decreases. And with the firm size, there is a larger effect. So policymakers should take into account that large firms are more vulnerable to energy price changes. And there's another consequences regarding rebound effect. We define rebound effects as the gains in the energy efficiency, which also reduce real per capita of price of the energy. And hence the energy consumption will rise and potentially offset the initial reduction in the energy consumption. At that point, on price of energy is important because if it is high, rebound effect will also be higher. And from this finding, we see that rebound effect is higher in large firms in the manufacturing industry. So when designing energy policies, this should be also policymakers should also take into account these effects. And this is all the things I want to say about my presentation. Thank you for listening.
Mert, thank you very much for your very interesting presentation. I'm just checking whether there's any question for you. I don't think okay. May I ask a question?
Of course.
You made this analysis for the years between 2005 to 2013, right?
Yes.
What do you think about the recent conditions, for example, after the COVID-19? What do you think about, for example, the price elasticities on energy for maybe not only Turkish companies? You can answer this question for globally. What do you think about the companies, the specific companies like manufacturing industry?
I don't think there's much change after COVID pandemic or the 2013. My data range is small because of the data limitations, but I don't think I will find very different results regarding this because these substitution possibilities. Because I focused on the substitution between capital and energy, and there is not so much changes regarding this substitution, but maybe when we look at the substitution between labor and energy, there can be maybe another changes about when we took a larger time span. But when I have more access to data to the recent dates, I plan to redo my analyses and compare them and look at if there's any structural breaks in the time span. And maybe I will have chance to find and research the reasons of these structural breaks.
Okay, thank you so much.
Thank you.
Once again, I'm just checking our next speaker. Özge is here. Okay. So our next presentation, design and testing of an IoT-based carbon monoxide monitoring UAV methodology, challenges and opportunities. The presenter is Özge Küçükgünger. Özge, could you introduce yourself first with a few sentences and then we can make your presentation, please?
Okay, I want to share my presentation, then I want to judge myself. And okay, firstly, my name is Özge Küçükgünger. I'm doing my Master of Science on Civil Aviation. I will be presenting about the methodology, challenges and opportunities of an IoT-based carbon monoxide monitoring, UAV design and testing. The contents are motivation, research background, methodology, flight test, test results, conclusions, and reference. Here are some examples of usage areas of UAVs, like agricultural practices, observation of the coast and coastline, cargo transport, fire and train monitoring, and deliver emergency care. Nowadays, with the increase of technology and industrialization and use of motor vehicles with poor quality fuel, exhaust gas, or the wrong positioning of industrial facilities, with the development of the industry, air pollution has become one of the main environmental problems of today. Air pollution drastically affects the depletion of the ozone layer and the increasing greenhouse effect on climate change. Various studies available in the open literature provide investigation studies for the industrial areas roles on the air pollution, as steel industry, oil industry, cement industry, energy industry, transport industry, and other industries. In such areas, using the remotely controlled UAV provide cost-effective solution. Here are some examples of project about air pollution measured drone. AirSense 100 is a drone-based air pollutant mapping solution. The ARMS has great instructing significance in forecasting severe pollution as well as grading prevention. Sniffer 4D is a hyperlocal air pollutant mapping system for collecting accurate air pollutant information in three-dimensional space. When coupled with infrared remote velocity measurement technology, this technique can be used to determine mass emission rates. The evolution on previous studies provided the trends of this area of study, which is related with our research in the past 8 years, can be seen in this table. In order to keep the flight of the UAV, long life components and motor with low current are needed. A light, modular, and compact design will allow the UAV to be stored and transported easily. Therefore, we have determined the following characteristic: rotary wing, autonomous flight capability, long flight time, stable flight, air quality measurement system, single board computer integration, modular, compact, and fail-safe. The AKM UAV designed in this study were designed from scratch. The data transmission of the UAS was performed using an IoT model and a cloud. Performing air quality measurement operation using a UAV as remote sensing platform requires a number of special design requirements. The design prerequisites and design choices were made to answer them explained in the table 3. The outline UAV design fundamentals. Rotary wing UAVs and VTOL UAVs are the two platform types can offer the hoverability, which is very important to get close to emission areas like chimneys. A multi-rotor UAV configuration was selected for meeting the hover requirements to minimize cost and pilotage requirements. The vertical flow problem is an important characteristic issue must be considered when designing an AQM drone. The vertical flow occurs around the propellers and mixes the air around the multi-rotor UAV. The UAV is with takeoff weight in between 500 grams and 4 kilograms are considered as UAV 0 category. So the takeoff weight of the UAV was kept under 4 kilograms. The adequate endurance was determined as 45 minutes by using the literature survey. The requirements of for AQM drone is to get close to exhaust structures such as chimneys, flues, or pipes. The solid UAV model was carried out as shown in figure 1. Rotary wing UAV frames carry a high percentage of the structural and electronic equipment of UAVs and are generally the largest volumetric components of UAVs. Therefore, the material to be selected, their protection should be durable but low in density. Thus, the material to be used in its production was determined as carbon fiber plate originally manufactured in the composite workshop. The rotor arms and landing gear of the UAV were made of carbon fiber tube. As for the connection parts and motor mount, additive manufacture method was used. Polylactic thermoplastic material was heated and then layered up using the 3D printer. The most important subsystem of AQM UAV could be defined as propulsion subsystem and mission subsystem. The propulsion subsystem provides lift force and control throughout the flight in multi-rotor rotary wing aircrafts. Figure 2 illustrates the main components of the mission subsystem of the multi-rotor UAV, which consist of propellers, motors, electronical speed controllers, a battery, and a power distribution board. The airflow that occurs during movement of the UAV and the rotation of its propellers as previously mentioned, it can affect the measurement quality. The effect of propeller airflow were tried to be reduced by adding an extension. Their extension boom or probe design have been applied in the literature for air quality measurement UAVs if any precaution were taken airflow problem. In this study, an extension rope hanging from the UAV airframe was used instead of a frame extension on the same level with propellers. Application may require a flight close to ground level that may be dangerous for the UAV. The testing process was carried out using a controlled fire. Organic materials were burned to produce carbon monoxide gas emission. The burned materials were selected mostly around the criteria of being household wastes. Thus, a landfill fire was tried to be simulated. Then the AQM UAV were flown autonomously over the area on 6 meters altitude from the ground. PPM readings were uploaded as live data to the IoT cloud server throughout Wi-Fi communication during the flight as labeled with timestamps. And GPS locations of the UAV were also obtained from the flight computer records as also labeled with timestamps. And then the PPM readings and GPS locations superimposed and using the timestamps as shown in the figure 5. The sensor data that uploaded the IoT server with the live connection is also presented as figure 6. UAV with autonomous flight capability could be used to monitor problematic areas using various sensors, educate for the application. As presented in the study, heat maps and alerting system could be implemented for this task. And thus a subsystem of early warning systems, remote of early warning system, remote sensing UAV can detect air quality problem in a cost-efficient way. IoT technology utilization in the study provided opportunity to gather and assess data on live transmission. Instead of saving the data on removable drives like an SD card would require human interaction for data assessment. Using IoT entirely in autonomous monitoring could be performed around potential problem source. The main drawback of the autonomous monitoring using an AKM UAV is the uncertainties may arise during the operation. Windy air both affects data measurement quality and the air flight negatively. Thus, operation under these conditions should be avoided for the healthy data acquisition. A fully autonomous UAV operation as presented in the study with capability of transmitting live data is very cost efficient. Considering the popularity and importance of smart city studies, and these ACAM UAVs can be integrated in many fields to monitor pollution and emissions autonomously. Since the methodology provided in the study requires less proximity with the air pollution source, the required pilot experience without autonomous control is also reduced. Reference. Thank you for listening to me.
Thank you very much, Özge, for your great presentation. And IoT is settling our lives recently very much and useful for many. You have a question from one of our audience. I'd like to extend that question to you. If you face a severe wind condition by means of effective air quality measurement, how do you or your autonomous UAV deal with this problem?
Actually, it's a big problem for this AKM UAV because we are testing this system, but under normal condition. But autonomous flight is disable and the UAV is controlled manually by the pilots.
Mm-hmm.
Then the UAV is positioned against the wind direction. Thus, the sensor can accurately measure carbon monoxide. Actually, it can be a solution for this big problem.
Okay, and you made a field test, small field test, right?
Yeah.
You show some results. I saw the carbon monoxide is 4 and 5 ppm, something like this. How do you, evaluate this condition? Because, generally carbon monoxide is known as incompleted condition gas,
Actually, we And now we work, we doing some tests in our center, civil aviation center in our university. Then we tried some testing condition, like you can see last presentation figures, and we tried and we have some different conclusion and results from this testing, and it's so hard firstly because we don't find any carbon monoxide source. Then we tried this, maybe we can arise most correct test result. Then we tried this, and we find this solution.
Okay, thank you so much again. Our next speaker is Fethi Coşkun, and presentation experimental investigation of a vapor compression refrigeration system for thermal management. Fethi, could you introduce yourself with a few sentences, and then we can start your presentation, please?
Okay, I can say now. Can you see my presentation?
Yes.
Okay.
Okay.
Hello everyone, I am Fethi. I am student at Yazı Technical University, Mechanical Engineering. In this presentation, I will present to you the vapor compression refrigeration system that we have designed and experimentally examined for a server case. The purpose of this study in harsh ambient conditions for the operated server case to devise and manufacture a compact vapor compression cooling cycle with macro-channel heat exchanger that ensure reliable operation and by keeping the device temperature below maximum operating temperature and will not cause a decrease in performance of the case. The server case normally cooling with forced convection in existing system. There are 9 electronic cards with a total power of 360 watts in the system. These cards are cooled from both heat points. There are fins on these points. With the help of this fins, heat absorption and with the help of the fan, heat rejection to the ambient. At low ambient temperatures, this air-cooled system can always be considered more useful and less costly. But considering the high ambient temperatures, sometimes the desired cooling cannot be achieved in the system. Therefore, we turn to a different cooling system. In the PNI diagram, we see the layout of the main components and fittings in the new cooling system. We placed 2 evaporators made of copper pipe on the side walls to be cooled. Other equipment, 1 compressor, 1 condenser and fan, expansion valve, side glass and dryer filter in back of the case. In addition, pressure manifold is placed in the aerator compressor aerator and compressor outlet. 8 temperature sensors are placed on the sidewalls of server, and 2 temperature sensors are placed aerator and condenser outlets. In this system, the condenser is considered a macro-channel heat exchanger. The copper pipe used for each evaporator has a 3 millimeter inner diameter, 2,800 millimeter length, and wall thickness of 1 millimeter. The compressor is operated at a temperature of 55 degrees, and speed control is done according to different heat loads. The expansion valve is an automatic expansion valve. Condenser fan is DC axial compact fan with an airflow rate is 710 cubic meter per hour. We used as refrigerant R134A for circulating system. Instead of electronic cards, we used aluminum plates. We provided the power of each electronic cards with cartridge heater that screw into the plates like this. The electronic connection of the system is examined for section, cased inside panel, cased outside, and computer connection. The processor of the system is ARM Cortex MCU, which is connected to digital potentiometer. Other substantial connections are 4 MOSFET drives, each controlled by PWM. MOSFETs which enable heater blocks to be operated at desired power with cartridge heaters are connected to 12 volt SMPS. And then if we look at the testing procedure and results, pressure and sidewall temperature value of the system are examined at 24 degrees, 40 degrees, and 55 degrees, which is maximum ambient temperature in the compressor for the compressor data. Another factor that determines the test is working loads of heaters. Thus, it's aimed to see the reactions of cooling system in changing load situation. The system firstly operated a load of full load at the ambient temperature of 24 degrees. The entire system was activated at the same time. In test, compressor speed 2300 RPM, fan speed 1050 RPM, working pressure of the system, low pressure 2.68, high pressure 10 bar. The condenser side is at the minimum 26 degrees and maximum 47 degrees. Average compressor temperature 25 degrees. In the test carried out at 40 degrees ambient temperature, the fan operated 3000 500 RPM, compressor speed 4,000 RPM, the high pressure value 14.3 bar, low pressure 3.48 bar. The side wall temperature of the case is average 31 degrees. In this test, at 55 degrees, which is the maximum ambient temperature at which the compressor can be operated, as can be seen from the figure, the side wall temperature were kept average 60 degrees. For a better result, extra cooling is required in the compressor for this test. In this test, the system operated at full load for 30 minutes and at half load for 30 minutes at 24 degrees ambient temperature. The test is continued until the temperature becomes stabilized. The figure shows that the system is started when the side wall temperature is at an average 70 degrees. In the final cycle temperature is equilibrium at 30 degrees, you can say. Likewise, here the system is started when side wall 40 degrees and final cycle reach 28 degrees. In this test, compressor speed and fan speed is higher than before. At the highest ambient temperature, the compressor and fan speed are almost maximized. Compressor speed 5,000 RPM. Fan speed 7,000 RPM. Average temperature reached 35 degrees. As a result, in tests at different ambient temperatures, compressor and fan speeds were also changed to improve cooling performance. Surface temperature of the compressor was taken into account in order not to cause any malfunctions during the test, while the cold plate temperature decreased at 24 degrees and 40 degrees. The compressor temperature remained in the operating range at the same time. However, in tests performed at 55 degrees, compressor surface temperature reached the maximum operating temperature. In order to operate compressor safely at an ambient temperature at 55 degrees and above, it may be considered a good solution to provide extra cooling by passing the pipe in the low pressure line around the compressor. While the compressor speed is fixed, the condenser fan speed can be changed and the effect can be observed. Optimization can be made in condenser selection. Alternative expansion wires, especially at electronic fixed types, can be tried. Additional performance tests can be done to improve the system. Thank you for listening.
Thank you very much for your presentation. And the cooling performance looks enhanced greatly with this method. And you mentioned about the condenser can work effectively for the temperatures above 55 degrees Celsius, right? And you'll go ahead with the optimization studies for next.
Yes.
What do you think about the temperatures? For example, the optimized value in terms of the temperature, the ambient temperature, the 55 degrees?
For this test,
Yeah.
maximum 55.
Maximum. Okay.
Yes.
Thank you very much once again. I think our first speaker with us right now, Nazilin Güre. So may I ask her presentation as next one, if you don't mind. The presentation title is State of Art Green Cryptocurrency Mining Models. Nazilin, could you introduce yourself first with a few sentences and then make your presentation, please?
Sure, thank you for having me. I'm a research assistant in Beykent University and a PhD candidate in Marmara University in Electrical and Electronics Department. I'm a very enthusiastic researcher about cryptocurrency, energy, and energy harvesting sections. Shall I start?
Sure.
Okay, thank you so much.
Yeah.
Okay. State-of-art green cryptocurrency mining models. And I'm Nazilin Güre. When we first look into cryptocurrency mining, we need to understand that it has many consensus mechanisms, but the most common one is for Bitcoin, which is responsible of the dominant energy consumption. The reason for this energy need is based on proof of work consensus mechanism, because to solve and find the block and for transactions to happen and to be recorded in those blocks, smart machines like devices like application-specific integrated circuit chips are necessary in our late years. Because they solve hash puzzles and find blocks, meanwhile consume energy and generate enormous amount of wastage at the same time. But the miners profit upon block rewards when they find the block, when they solve the hash puzzle and find the block, they are rewarded. And also for each transaction, they also earn different fees. In the right-hand side, you see the dynamic hash rate of Bitcoin. When we look at this, as more miners comes into the game, and more intelligent devices are introduced, the hash rate is arranged as such that it will be updated according to the maximum device capacity. So as more miners get into the game, the hash difficulty and the hash rate of Bitcoin increases. This means miners would have to have more ASICs, would have to have more energy consumption, and will generate more wastage. And for detailed cryptocurrency mining's environmental effects, I would welcome you my second presentation tomorrow. Briefly, when we just check what Bitcoin and Ethereum dominantly does, we see that Bitcoin energy consumption due to mining is almost like 0.2 of global energy consumption. And yearly it is 87 terawatt per hour. And for Ethereum, it is 12 terawatt per hour, which is almost equivalent of Georgia's, the whole country's electricity consumption. And for carbon footprint of Bitcoin, it is around 37 megaton carbon dioxide per year, which is equivalent carbon dioxide emissions of New Zealand. Similarly, for e-waste, for Bitcoin, it is 10 kiloton, which is equivalent electronic waste of Luxembourg. For single Bitcoin transaction, generate 93 gram of e-waste, 333 kilogram of carbon dioxide, and 700 kilowatt hour electricity consumption, which is equivalent of 24 US size house, daily US size home energy consumption. For Ethereum, this is 30 kilowatt per hour, which is equivalent of single US house energy consumption per day. This is very interesting because that e-waste can, electronic waste can be seen from how much heat that those devices generates. Here in a cold region on a snowy roof, there is only one house that perform mining, and you can see that they keep their door open here because it's so hot, and so hot that even the roof, the snow on the roof has melted. That's why those ASICs are subject to be broken easily, and they constantly need repairs. Previously, most of the cryptocurrency miners defend that 76% of their energy consumption is supplied from renewables. But then this value is re-estimated and corrected as almost like 40%. And among this 40%, the distribution of those renewables are 63% for hydropower, 17 for wind, 15 for solar, and 6 for geothermal. And among those fossil fuel source mining, 36% of coal and 38% of coal and 36% of natural gas is dominantly used. The problem that we see about renewable power plants is that they have long period of redemption, which is around 5 years. So investors do not tend to support them, since not even the profit, just the duration of cover those costs is 5 years. And then in terms of renewable power plants, cryptocurrency mining gain attention because when cryptocurrency mining is introduced to the system, some portion of generated energy is used by cryptocurrency miners. They can supply profit from the gained cryptocurrencies. Therefore, the cryptocurrency mining integrated renewable power plants reduce their long period of redemption time to a year. And then without the need of the investors, just by the intended, let's say, renewable power plant owners, by simply integrating mining rigs, they can cover their own costs, and financially sustainable renewable power plants comes into place. Due to cheap electricity need of those mining rigs, you can see the cost of the electricity here, electricity prices here. So the miners tend to switch to the locations to pay a little amount of electricity as much as possible. So this also causes centralization of blockchain, which shall be decentralized in consensus mechanism, but actually in physical systems, they became centralized by means of localization. Here, there is a chronology of cryptocurrency mining for cheap energy alternatives. The easiest and the first action was to move to the locals, which has cheap energy, and also like Kazakhstan, Ukraine, or such, to get rid of the cooling cost, because those regions are already as cool as possible. And then the second shift occurred to hot climates. This is where the first renewables comes into place in mining rigs, because they can harvest solar energy, and they can generate their own energy need. And then shift to near renewable power plants. This also dominantly occurred in China. They saw that if they just move to the closest place to the renewable energy power plants, they can easily gain those energy without any loss on cables and directly use them. And then start off mining as a green energy drives, just as I mentioned here. Now renewable energy plant owners adopt those cryptocurrency mining to reduce their long period of redemption from 5 years to a year. And then wasted utilization and green models evolved from the first one. One of the most innovative one is Hotmine and Carnot products. They use mining reheaters and then other solid oxide fuel cells for novel biogeneration plants. I will go each of them deeply just for a while later. Wasted harnessing for greenhouse crops, just as producing tomatoes and strawberries. Another very innovative and sustainable model is canadian van ventilation, as performed by Blockchain Dome by United Corporation. The region-based localization is mostly in China for mining rigs by 24%, and then followed by USA by 60%, and then Russia. For the remaining is for Kazakhstan and Iran. The first solar power self-sustaining mining just using classic solar power, and just by simply regulating the voltage, they can use it for ASICs and their servers energy, and from stored some portion of energy is stored in batteries, and they are used to feed servers energy. Because in cryptocurrency mining, you have to have the internet connection, and for mining rigs, gigantic amount of mining rigs, you would have gigantic amount of servers and data storage parts as well. Then there is this solar power cabin. This is especially designed for cryptocurrency mining, so that for those who will switch to cryptocurrency mining, they will just buy this cabin, and in this cabin they can automatically use the energy for their servers and mining rigs. This is a hydro miner, very commonly seen near China as well, but this one is in USA. By setting their mining rigs near hydropower plants, without any loss on the way, they can directly use the energy from generated hydropower, renewable energy. This is also very interesting subject. This happened a month ago. I may not pronounce this hydroelectric power plant, but this is very ancient and owning one of the first hydropower plant system in USA, having an 80s machinery. And then they were about to close because they couldn't make enough profit to cover the expenses of those old machines. And then they added cryptocurrency mining, just as small as we see in the picture. And this tripled their profit by then. So not only they cover the cost, but after a while, as cryptocurrency value increases, they even doubles their existing profit. And just as a recap, we carry on with the chronology. This is mining reheats for Hotmine. As we see on the right-hand side, actually this is classic household heating system. But this is the inside of it, and we see the mining rigs and cooling small heat transfer system, so that the heat generated from mining ASICs can be distributed to the room. And after a while, Carnot also produced similar house heating device by use of ASICs devices. So when you buy these Carnot and Hotmine, you don't pay for the electricity actually, because the generated cryptocurrency value already covers electricity costs. They say that in 11 months, it totally covers the cost of buying those Carnot and Hotmine when you totally cover your all rooms and all house, and even in Canadian harsh weather conditions. So they profit upon while heating your home. Solid oxide fuel cell mining is another innovative merge scenario. They use biomass and anaerobic dilation and classic solid oxide fuel cell system. And then those energy output is divided for grid and to feed the mining rigs. We see here Antminer because how they used is from Antminer, but they can also be ASICs as well. And then the cryptocurrency is generated. Another novel biogeneration system, which is very sophisticated, but this is the best so far I have seen, has three or four main parts actually. The first part, consuming the fuel, just as regular systems, and then dividing into two sections. First one goes to electrical generator, and the generated energy is fed for mining energy need. And then it is sent to exhaust heat utilization. From there, it also, again, the electricity generated is also consumed by mining rings, but also it is sent to adsorption unit. And in this adsorption unit, actually, the evaporator and cooling part is used to cool the mining rigs. So here,
could you sum up with
yeah, sure. Yeah, this is the greenhouse cryptocurrency systems. They feed crops. And this is the Canadian well utilization, where greenhouse and mining rigs heating system is well utilized. And this is the plenary view. So this is how those greenhouse feedback cooling system works in those mining rigs. And one other full structure is offered by GEM crypto mining. So they have all renewable systems. And as a final propose here, this can also be used, those heat for desalination, and thermal energy generators can be integrated as well. Thanks for your dear attention. You can contact me with any of those emails.
Thank you very much for your very interesting presentation. And, you know, as you mentioned recently, it's taking great attention recently because we all know the cryptocurrency drastically increased the energy demand in all over the world in many regions you mentioned. I'm just checking the questions. We don't have any questions, but we have, you know, time limitation, very short question. And I think tomorrow you're going to talk about the climate. What do you think about the climatic conditions, they enhance the climate change effect or something like this?
Related to cryptocurrencies. Yeah, it is a very interesting subject because it drives climate change, you know, for our attention as well, for my attention as well. But it's very interesting because Bitcoin will achieve its saturation in like 5 years or so, because it is supply will be fixed and there will be no mining afterwards. So mining for Bitcoin will not be the issue for after 5 years. I was keeping this insight for my next presentation, but why not? Yeah.
I'm very curious about your next presentation.
Thank you. I'll be waiting.
Thanks. I think our last presenter, Ertuğrul Demir, the presentation titled by composite and polymeric materials in radiation shielding applications, a review. Ertuğrul, could you introduce yourself first and then start with your presentation, please?
Thank you so much, Professor. My name is Ertuğrul Demir from Physics Department, Yeditepe University, Istanbul. Today, I'm going to present biocomposite and polymeric materials.
Ertuğrul, I think you have to use slides, so the screen is currently...
Could you see my screen?
But in different way. I'm gonna say,
okay,
you take your on the slideshow.
Like that, no?
Yes.
You see the notes, my notes, right?
Yes.
Okay. Let me check.
Maybe you can change your
I will.
I don't know which one
Sorry for that.
Shift F8 or 7.
Okay, let me check one more time. Sorry for that. Composite polymer presentation.
There's a small setting. Just you can write the word sequence or something like this. I'm not sure about technical thing, but
yeah, me too. Sorry, I'm really sorry for that. I don't understand why happened like that, but let me fix it. It's just
okay.
A second. Share screen and something happened to my computer. And okay, I got it. Okay, I got it.
Maybe you can go ahead like this, or you can make the arrangement from your desktop, your computer desktop. You can go ahead the settings and then.
I think this time it's work. No, it's same.
Related to monitor the screen, there is an option. You can choose multiple screen. You see the settings?
Okay, I'm going to.
Birden çok ekran diye bir seçenek var Ertuğrul. Desktop'ta görebilirsin. Monitör ayarlarına, görüntü ayarlarına gelince orada bir seçenek olması gerekiyor. Birden çok ekran diye. Oraya gidebilirsin. Veyahut da slideshow'u almadan gidebilirsin zaman kazanmanız açısından.
Evet, yani birden çok ekran şeklinde seçtim ama yine
algıla diyorsun orada birden çok ekranı algıla diyorsun, o sonra düzeltiyor.
Şimdi slide'ı mı görüyorsunuz hocam?
Şu an ekranını görüyoruz ama slide'ı alırsam slide'ı göreceğiz.
Slide gözükmüyor öyle mi?
Okay, it's okay.
Okay.
For us, but for you, you have to check.
Okay, you see my notes, I think, right?
Yeah.
Or just presentation you are seeing?
Yeah.
Okay. Sorry for that. My name is Ertuğrul from Physics Department, YedTepe University. Today I'm going to present biocomposite polymeric materials in radiation shielding applications. Let me introduce outline of my presentation. First, I will mention related concept of radiation and radiation protection. And after that, I'm going to talk about radiation shielding, polymer and its composites, and biomaterials for radiation shielding. In a simple way, radiation can be defined as the emission of energy in the form of particles or electromagnetic energy. And radiation can also be categorized as charged particle and uncharged particles. Fast electrons and heavy charge particles belongs to charged particle radiation family. On the other hand, electromagnetic radiation and neutrons can be considered as the uncharged particle radiation family. Radiation can also be divided into two main categories according its ability: ionized matter, ionizing radiation, and non-ionizing radiation. For us, ionizing radiation is much more important than non-ionizing radiation because ionizing radiation is defined as high energy radiation, strong enough to cause displacement of electrons from atoms and breakage of chemical bonds. Here, I would like to mention about ALARA. This is the main principle of radiation protection. It means as low as reasonable achievable. This principle means that even if it is a small dose, if receiving that dose has no direct benefit, you should try to avoid it. To this, you can use 3 basic protective measures in radiation safety: time, distance, and shielding. Time simply refers to amount of time you spend near a radioactive source. Minimize your time near radioactive source to only what it takes to get the job done. And distance, on the other hand, refers to how close you are to radioactive source. Maximize your distance from radioactive source as much as you can. This is the easiest way to protect yourself because distance and dose are inversely related with each other. On the other hand, another key parameter is shielding. To shield yourself from a radioactive source, you need to put something between you and radiation source. Radiation protection is an important field across a wide range of industries, from healthcare and medical imaging to nuclear energy, nuclear medicine, and non-destructive testing. Materials interact differently with different types of radiation. For instance, tungsten is able to attenuate gamma radiation effectively, but when exposed to neutron radiation, secondary gamma rays can be produced. Materials that are strongest at attenuation gamma radiation are tungsten and lead, while high-density concrete and borate polyethylene are better materials for stable neutron. Thus, we have some key parameters in radiation shielding which need to be considered. These are environmental conditions, cost, and safety. We should take into account according to type of radiation while we are choosing the best radiation shielding material. For instance, cost is an important consider when selecting the appropriate shielding materials for a job. Lead, for instance, a commercial one, lead is a very effective and inexpensive shielding materials compared to materials like tungsten and other high-Z materials. Also, safety is important, selecting the right shielding solution. For instance, lead may not be permitted in some scenarios due to the toxicity of lead. So polymers with bismuth, tungsten, or iron may be better for these conditions. Researchers have investigated various radiation shielding materials to protect life and its surrounding from devastating consequences that occur from radiation exposure under attenuation or absorption of unwanted radiation. Weight, space, cost, and attenuation or absorption capabilities of materials used for radiological protection are key points for researchers to synthesize and develop appropriate shielding materials. Good radiation shielding material can attenuate, absorb, or block the maximum part of incident radiation. Materials that are supposed to be used as shield against gamma photons should have higher atomic number and density. As much materials impose higher probability of interaction that implies larger energy transfer with gamma rays. Besides, material with lower atomic number and density can make up of increased thickness as significantly as high atomic number materials in radiation protection. Customarily, lead multiple layers of single slabs of pure elements such as barium, lead, aluminum, copper, iron, and concrete are reliable, efficient materials that prevent humans from getting affected by hazardous effects of ionizing radiation. Despite having great radiation attenuation properties, lead and concrete are discarded due to the heterogeneous nature of lead, and moisture variation in concretes makes it hard to predict radiation protection properties. In contrast to the past, polymer and its composites offer a promise suitable alternative candidates to lead and concurrent in the field of radiation shielding due to its lightweight, durability, flexibility, along with superior physical, mechanical, optical, and radiation resistance properties. Latterly, investigators working in the field of radiation protection have focused and reported polymer matrices that can be used as gamma rays. These are, it can be say, bismuth oxide filled polycomposites, high density polyethylene composites loaded with tungsten, molybdenum sulfide, and boron carbide, micro and nano size tungsten oxide, lead oxide with resin polymer composites, and silicon rubber composites containing bismuth content and polymer bricks. Polyester composites reinforced with zinc composites of high density polyethylene with zinc oxide, lead oxide, and also cadmium oxide. It can be used for radiation shielding. Generally, polymers have very low mechanical characteristics, but are useful because of their flexibility in applications requiring such a property. They are usually deformed at high strain under loading. The improvement in mechanical properties such as tensile strength, modulus, stiffness is done by inorganic particles via reinforcement mechanism. Such properties can indeed be tailored by changing the volume fraction, shape, and size of filler particles. Polymer nanocomposites offer the promise of a new generation of lightweight hybrid materials with numerous possibilities for automotive, general, and industrial applications. Polymer composites are considered cornerstones engineering materials for many applications such as building, civil engineering, aerospace technology, electronics, and electrical engineering. Here, an interesting problem arises from the use and storage of polymer composite materials as waste. The accumulation of waste from polymer composite materials can lead a serious burden on humans and the environment by causing pollution to nature. Many attempts have been dedicated to using biodegradable fillers, which at the same time can enhance performance of the composites. Other researchers were concerned about developing thermoplastic composites with recyclable fibers to diminish the use of fillers without any harm to the environment and keeping it clean and healthy. Here, I would like to mention about comparison of polymer composites, composite-based shielding materials with conventional material. A qualitative comparison between polymer composites and conventional material used in aerospace and healthcare industry is provided in this table. Overall, material properties and their shielding effectiveness are indicated as low, high, or equivalent in comparison with conventional material. Even metal elements such as lead, tungsten, bismuth, lead oxide, or composites of these materials have been traditionally used for protection against X-ray and gamma rays because of their high density. The use of lead-based aprons, interventional radiological procedures, and related applications tend to cause occupational health hazard because of toxicity and weight factor associated with lead products. Alternatively, polymer-based shielding materials are lightweight, comfortable, and they can be designed to include non-toxic, high-Z filler materials that provide effective X-ray and gamma ray protection. The selective enhancement of radiation attenuation by the nanomaterials at lower energies was attributed to the increased number of particles per gram and grain size effects. Although such investigation need to be extended to other high-Z materials in order to fully understand the exploit the unique properties offered by nano-size materials. Such studies offer a basic for further research efforts, non-lead based polymer nanocomposites for shielding against low energy diagnostic application such as mammography. On the let me talk about a little bit biomaterials. Biomaterials are relatively new field for radiation shielding. Biomaterials science is broad field that defines biomaterials as biocompatible materials. Any material, whether synthetic or natural in origin, that is designed to be used in close contact with biological system, tissues and fluids that serve a medical purpose, such as evaluating, treating, augmenting, or replacing any tissue, organ, and bodily function. The usage of biomaterials in radiation is mostly related with human space exploration. Space environments are inhospitable to human life. Therefore, a life-sustaining habitat must be created for the duration of any mission with humans or other higher biological systems on board. Notable characteristics of space environments that must be accounted for include gravitational variability, temperature extremes, particle contamination, cosmic radiation, toxic or no atmosphere, and isolated and confined environments. Radiation exposure has long been considered a major challenge for long-duration human space mission. The Earth's magnetosphere and atmosphere are powerful shields against steady flux of cosmic radiation from protons and high atomic number, high energetic particles. At sea level, cosmic radiation is attenuated to global average 0.22 milligray per year. At high altitudes, where the protection of magnetosphere is intact, but there is a less atmosphere present to act as a shield, the incidence of cancer increases for those exposed to altitude for prolonged periods, such as commercial airline pilots. On the other hand, in deep space, beyond the protection of Earth's magnetosphere, the cosmic radiation is 104 gray per year, nearly 500,000 times Earth's yearly sea level dose. And these radiation values are influenced by interaction with the shielding and atmosphere of spacecraft and planetary surface, such as Mars. Contrary to popular belief, the solution is not merely lining spacecraft with lead, which is only effective for certain range of high energetic particles. For instance, lead is highly effective at blocking gamma and X-ray radiation, but also they generate secondary X-ray while beta radiation is passing through the material. Furthermore, although existing shielding provides some measures of protection against cosmic radiation, it greatly increases a spacecraft weight and cost to launch. But most importantly, commercial radiation shielding material like lead and tungsten, it doesn't completely protect astronauts against radiation. Shields 5 or 7 centimeter thick can only block 35% of cosmic radiation. And then NASA to investigate the use of pharmacological and dietary supplements to mitigate the effects of ionizing radiation. Here, at this point, biomaterials may offer a unique solution when compared to radioprotective geological materials such as lead. Biological materials such as melanin are both lighter and more flexible in their potential applications. A group of heterogeneous biopolymers, melanin, act as pigments and provide radiation protection, are found throughout plant, fungal, bacterial, and animal kingdom. Rega, it's one of researchers who is interested in this area, tested melanin nanoparticles in irradiate mice exposed at a dose of 7 gray gamma irradiation. They found that treatment with melanin nanoparticles protect tissues against radiation damage, thereby enhancing the survival of mice in treated groups, approximately 40% survival, compared to control groups, 10% survival, and concluded that melanin nanoparticles provide significant radioprotection to tissues. For biomaterials to be successful in space, when specifying design criteria for the biomaterials performance, 5 key characters of the space environment must also be considered: microgravity, microbes, fire resistance, and weight to launch. The ability of cellomelanin and melanin nanoparticles to block ionizing radiation is a promising candidate for the protection from cosmic radiation, though further research is needed to assess their ability to protect against other radiation besides X-ray. Thank you so much for your attention.
Thank you, Ertuğrul, for your very interesting presentation, and we learned a lot about the. Of course, we all know the importance of the radiation shielding, but there are great challenges in terms of the materials and the, protection materials. I'm just checking the questions. Actually, we already finished our time. So I'd like to thank you all for your presentations, very interesting and nice presentations. We had 5 presentations about the cryptocurrency minings and capital energy substitutions in terms of the manufacturing industry. It's really important one, and also some experimental investigation related to the refrigeration systems and about composite and polymeric materials for radiation shielding. Thank you very much for your attendance and attention for this session of 8 related to green energy. Have a good day, and please follow the next sessions of the conference.
Thank you so much, Professor. Have a good day.
Bye.
Thank you.
Good morning or good afternoon, everyone. I just would like to check if you hear me, everyone. If someone can give me a sign.
Yep, we can hear.
Yes,
Yes.
Yes, yes.
Okay.
Audible.
Okay, thank you very much. My name is Ankica Kovac and I'm coming from Croatia. I have the honor to chair this session today. And I suggest to start on time. Each presenter has 12 minutes for presentation and 3 minutes left for questions and answers. And we have to be strict on time, so please keep in this time. So now I would like to invite our first presenter. He is Tunuguntla Arun Sri Sai Krishna. I hope I pronounced it correctly. So please, floor is yours.
Yeah. Is my screen visible to all?
Yep.
Screen is okay, yes.
Yes. Thank you, ma'am. Thank you for giving me this golden opportunity. Good morning or good afternoon, everyone. I am Arun from Shivanara University, and I'm going to present on the topic performance analysis of double slope solar still for active and passive for Indian climatic conditions. And these are the authors for our paper. Yeah, coming to the basic introduction, water is very important factor in everybody's life, like every human being life. And even though water is surrounded for 70% of the earth, but there is a scarcity of fresh water in different parts of the world. But there are many solutions for this, like desalination, etc. That is the solution we took. Like we took the double slope solar still, which is coupled with parabolic disk-type solar concentrator. It is like integrating a passive solar still with an to make it an active solar still. Until now, a very less literature review or research has been made on solar still coupling with parabolic disk-type solar concentrator. Now we are working on it to increase the performance of it, like to increase the efficiency of a passive solar still, so that it will be in its active mode, it will be more effective. Yeah, here is the experimental setup, proposed experimental setup. Now this setup is being funding by Shivanara University, India, to conduct experiments on this setup. You can see the basic setup, like you can see a double slope solar still and a parabolic disk-type solar concentrator. You can see water storage tank, freshwater tank, and a brine tank. You can see a pump which is used to circulate water between the solar still basin and the parabolic dish collector. Here the inclination of the glass is taken as 15 degrees, which will give us the maximum output for the overall year climatic condition. It's not only for summer or winter based. It's the 15 degrees angle is taken to get a overall maximum yield. Also, which is also feasible for latitude and longitude conditions in Delhi. Yeah, coming to thermal modeling, few assumptions are taken to make the thermal modeling. Coming to the thermal modeling of parabolic dish, we need to get a equation to get the useful energy, so that we need to use different factors like heat removal factor, coefficient, collector efficiency factor, heat loss factor, and so on, so that we can get the useful energy from the receiver, which we can see from the equation 7. Like QU is the useful energy which we are getting from the receiver, and this energy is used this energy is added to the solar stills basin water, so that it will be more effective while coming to the evaporation, and it will give us the more yield. While coming to the thermal modeling of the solar, still heat balance equations are taken for inner and outer side of east and west glass, namely equation 8, 9, 10, and 11. And also heat balance equations are also taken for basin liner and water mass. After solving all these equations, we will finally land into equation, a differential equation with variable water temperature, and A and F of T are constants here for a particular time, like for a particular instance of time, like we took as 1 hour. From the on solving this differential equation in MATLAB, we can get the equation for water temperature, which is shown in the equation 15. The water temperature equation, from this equation we can get the water temperature, and from that we can get the temperatures of inner and outer glass temperatures for east and west glass in the equations below shown. Also we need to calculate the yield. We need to calculate the yield that we got from the solar still. So we are calculating the heat transfer rate, and from that we can calculate the overall yield, and we can calculate the total yield by summing up the overall yield, and also we can calculate the efficiency from these equations. Yeah, coming to the results, this is the input data which we took to find all the parameters for from 8 o'clock to evening 5 o'clock in a day. We took these results for Indian climatic Delhi Indian climatic conditions, and we performed the experiments. Here the input data is like solar radiation, focusing on east and west side of the glass, and also ambient temperature. From those we can get the temperatures of water and the inner and outer side of the glass cover for east and west side, for active and passive both. Like you can compare the results here, and it is visible that the temperature of water in case of active solar still is greater than that of passive. Yeah, coming to the useful energy that is coming from parabolic receiver. You can see the trend of the graph. So it is high in the mid noon, like from 12 to 2. After that, when the yield is plotted against the time of the day, you can see that for active solar still it is far greater than that of passive because of its integration with parabolic discharge solar concentrator. And same applies for thermal efficiency as well. And coming to the collector's efficiency, which is like parabolic dish type solar concentrator efficiency, the trend follows like this. Like it is also increasing from morning to afternoon, and it start decreasing as the sun sets. And also the heat transfer coefficients, like convective, radiative, and evaporative heat transfer coefficients are plotted against the time of the day, like for east and west glass for both passive and active, which are shown in these graphs. And coming to the final conclusions, the average efficiency of parabolic dish is found to be around 58% something. And also coming to the overall efficiency for active and passive solar still, it's around the average efficiency for a passive solar still is around 19.77%, and for that of active is 24.52%. And the yield obtained for a 2 meter square basin area is like for passive it's 8.48, and for active it's 14.16 respectively. And from these results, we are now conducting experiments to validate these results for the experimental setup, and these experiments are being conducted in Shivananda University, Delhi, India. And these are the references which we used for the modeling and literature review. Thank you.
Thank you very much for this great presentation. It was really quick, and we have 6 minutes for questions. So if anyone has a question, or if we have it in a chat, please ask. So if you are wondering something about this work, please feel free to ask anything. No one? Okay, so we have enough time to discuss. So I have a few questions. First one is, do you have, maybe I missed it during the presentation, but do you have the real experimental system, experimental setup somewhere on the real location, or this is just modeling?
Yeah, we have built the experimental setup, and the experiments are being done in Shivnara University, Delhi, India. India. The experimental setup is built in the month of March and April, and the experiments are being done now on the setup.
Okay, great. And for what do you use this energy? Do you have some? Is it just to the grid, or how do you use it? How it is designed? This system?
No, actually, there is no scope for energy here. It's a device which is used for desalination. Like we will get the fresh water from saline water, so that we are working on the improving performance of that still. Like for a passive solar still, it won't be that much when we are integrating it with a parabolic dish type solar concentrator. We are getting a much higher yield, and we are working on that performance base.
You are working on energy storage, if I am right.
No. Actually, it's not about energy storage. It's completely about a desalination of water. Like we are getting water mass. Like it's not about energy storage. We are getting water mass from the solar still, like fresh water mass.
Okay. I heard you mentioned batteries. So is
no,
it just misunderstanding? Okay.
Yeah. 1 second.
Okay. And on the slide before references, if you can put your on your screen, yes, yes, here. The point 1, 2, 3, 4. The yield of passive solar steel is observed to be 8.48 kilograms. What does it mean?
Yeah, it's like how much yield. I mean, the basic phenomena here is like the water will evaporate onto the glass cover, which is covered on the top of the basin. Like it is inclined in with 15 degrees angle, so that the water droplets will come and fall in the receiver, so that the water will be fresh. Like from the saline water, we will get those fresh water, and the mass which is getting collected in that receiver or the collector, that is calculated, and that comes to be 8.48 for a 2 meter square basin area for a passive solar still, and that of for active it will be like 14.6 1.16 kilogram.
Okay. Thank you. I cleared everything to me. So does anyone have some question? If not, we have 2 minutes more, but while the next author preparing himself, I will just turn on my document. So our next speaker is Navnet Kumar. Am I right? Yeah. Okay. Your paper is titled Comparative Analysis of Solar Energy-Based Water Purification Systems based on various designs. I'm inviting you to take a floor, and please keep in 12 minutes of your presentation. So we have 3 minutes more for questions and answers. You can introduce yourself shortly, so we will be just on time, please.
Okay, very good afternoon to all of you. Can you see my screen?
Yes, we see. You can put it, yes. Okay, you read my mind.
Okay. Okay, Ankita and others audience, very good morning to all of you. The today presentation, the title of my paper is Completing Analysis of the Solar Energy-Based Water Purification System on design. Myself Navneet Kumar. I am working with as a professor at Galgotia College of Engineering and Technology, Greater Noida, Uttar Pradesh, India. And in this research, we have two my other authors colleagues, V.K. Dwivedi. He is from Madan Mohan Malviya University, Gorakhpur, Uttar Pradesh, India. And the third author is the Professor Bandhu Singh. Currently, he is working with Department of Mechanical Engineering, Graphic Era, DM University, Dehradun, Uttarakhand. The outlines of my presentation are introduction and the motivation, and the literature review, research gap, the objectives, and the methodology, and the result discussions, and the conclusions. So, the potable water and the energy are the two inseparable and the essential things for sustaining human life on the earth, and the rapid population growth due to the industrialization and the insufficient conservation of the water and the deforestation, especially in developing countries just like India in the recent past, have placed pressing demands for the both fresh water. Fresh water is also known as a drinking water or a potable water, and the energy point of view. So already we know that only less than 1% of the water is available for the society for direct use, and out of which maximum fraction has been polluted due to the non-management. And there are many other distillation processes like reverse osmosis, electrolysis, multi-stage flash, and the distillation, multi-stage distillation, and the mechanical vapor compression. But these all the devices is used to run some electric source. We need some convection power to run all the devices. And these methods are the energy intensive and that depends on the fossil fuel based grid power and hence not reachable to remote areas. So we must focus on the device that will work on renewable energy, especially solar energy, as it is powerful and abundant. 30 minutes of the solar radiation falling on the earth is equal to the world annual energy. It is a cheap, environment friendly, and near existing. The solar distillation is one of the simplest processes to produce safe potable water from the basic saline underground water, even in remote areas on the seas and coastal regions without. India being a tropical country, there is plenty of the sunshine, and the average daily solar radiation varies between 4 to 7 kilowatt hour per square meter for the different parts of our country. And the water that is produced may be so pure and that the consumer do not like the lack of the taste and improve in the small quantities of the salt water can be added. This is called the electrolysis for the flavor of the water. And the primary function of the solar still can be outlined as follows. The first, water is heated by the sunlight to the point of the expression, and then the water vaporizes and then condensed on the glass surface. Glass surface is available at the top of the circle, and this process is removed impurities such like salt and the other minerals from the water and the microbiological contaminants. And the solar still is the instrument used to produce fresh water and unwanted water, but because of the lower, it is not used for the potable water. This is the drawback. The major drawback of the device is the less productivity. That's not used for the industry and the domestic. So therefore, research and development that is continuously works by the researcher to increase the yield or output or the productivity of the solar as you can see in this diagram, in this diagram, we have the two experimental setup. One is the single slope passive system in this figure, as you can see. In the second figure, as you can see, the single slope active system is attached with a one flat plate collector. In this system, we provide some heat from the heat. So this system is now known as the active system. Here is we are not supplying any heat from any external source. Only the sun energy is falling on the system, on the ground. So this is the passive system. This is the active system. So in the active system, we provide some external heat from other source. In this system, we are providing from each source. So here is the question for design of this system. As you can see, the various challenges for the design of the solar cell. So for the high efficiency, the solar cell should maintain a high feed water temperature, a large temperature difference between feed water and the condensing surface, and the low feed. And the second point is that a high feed water temperature can achieve if a high proportion of the incoming radiation is absorbed by the feed water. Hence, low absorption glazing and a good radiation absorbing surface are required. And the heat losses from the floor and the walls are capped. And the water is shallow, so there is not so much cooling. A large temperature difference can be achieved. The condensing surface absorbs little or none of the incoming radiation. The condensing water creates heat which must be removed rapidly from the condensing surface, which is like, for example, second flow of the water. And it should be also noted for 2,260 kilojoules per kg, required to evaporate water for a pump, 1 kg of the water for 20 minutes. It requires only 0.2 kilojoules per kg. Distillation is therefore normally considered only where there is no local source of the fresh water that can be easily pumped over a liquid. So these, as you can see, the earlier researchers have been done work done by the different researchers like Malik in 1982, Jackie, Rai, and the TÜBA. I skipped due to the time limitation. I skipped the slide. So the current literature circle, after the study of the various researchers, so we have identified the research there. The comparative analysis of the solar energy based water system has not fully helped. So in this study, we have done experiment on the three experimental setup. It is a single basin, single slope passive system. In the figure number 2, as you can see, the double slope. This is a double slope passive system. Only work in the passive. In this system, we have a double slope active solar energy based system. So one particular collector is attached with this system because here for the circulation of water, here we are providing the one pump. To run the pump, we provide the flat plate collector. So the parameters of or geometrical specification of the different setups. So these experimental setups are available at IIT. And all the experiments are conducted in the 2010. So as you can see, the basin area for the first facility only 1 meter square, for second 7 meters. This is the geometrical specification of these. The objective of this work to compare the daily yield of single basin, single slope passive, and the single basin, double slope passive, and the single basin, double slope passive solar system, and the natural. And to compare the thermal efficiency of the single basin, single slope passive system, single basin, double slope, and you can see, the modes of the heat transfer. The heat transfer in this setup or in the solar cell, we have two types. One is the external heat transfer, second is the internal. In the external, when we talk about the external heat transfer, so as you can see, so first we have the heat transfer takes place through the conduction, convection, and the radiation. In the conduction, the heat transfer takes place between gaseous or to ambient air to the environment. Through the convection, heat flow, heat interaction takes place in glass surface to the ambient environment, or third is the radiation, glass to the external. In the internal inside the solar cell, the evaporation heat transfer takes place between from water to the glass, the convection water to the glass, and the third radiation water to the glass. So as you can see, this is the total heat transfer for a system, internal as well as as you can see, the internal heat transfer, the heat transfer inside the solar system from water surface to the inner inside the water takes place by convection, evaporation, and radiation. Already I told you. Already discussed. And the convective heat transfer takes place by water surface and the humidity inside the solar system. It depends on the buoyancy, density gradient of the humidity and the temperature gradient of the different layers of the air. The convective heat transfer coefficient for east and the west glass we can calculate by using the ring equation, which is given by the and the evaporating heat transfer occurs between the water surface and the glass cover in the form of the water air, which is calculated through the equation by the open and radiative heat transfer. The radiative heat transfer can be written as we can calculate by using the equation, and now we have a total heat transfer by convection, radiation, and evaporation. And finally, we calculate the rate of the evaporative heat transfer can be written as or calculated by using this equation. And now, finally, we calculate the hour heat production of the fresh water can be calculated by this equation. W upon L. L is the latent heat of the evaporation. And the daily yield or a productivity or the output of the system can be calculated by the per day 24 hours. By and for this is the daily yield for passive system, this is for active. In the active, we are using the flex pressure. And the conclusion of this research work is we have identified different parameters. The daily yield, we can also see the productivity of the system. Single basin double slope passive system was found to be 1.83 kg per meter square for a day. While the daily yield of a single basin double slope active system was found 2.7. So here we can say we are increasing this value in comparison to the SPG to single slope basin double slope yield 1.5 times, and the thermal efficiency is lower than single basin double slope system as compared to the single basin double slope single active system. On the other hand, in terms of thank you. Thanks for your time.
Thank you very much for this interesting presentation and deeply detailed presentation. We have 1 minute for maybe 1 or 2 questions. If someone has a question, please ask Professor. You can write it in a chat box, or you can ask. Okay, if no one, I have just one. It's not technical. It's just I'm wondering, did you taste this water when you produce it as a clean water? You said you produce clean water. Did you taste it? Is it drinkable yet or not?
Initially, it is test gas, but we went through the pelletization. We can convert to the test form.
Okay, okay. Thank you very much. We are just on time. It's 10:15, and I would like to proceed to the our third speaker today. Thank
you very much.
Thank you, Professor. And I would kindly invite Hasan Khan Kuku Kerdem. Please, the floor is yours.
Thank you. I want to share my screen, but I think Nanvet Kumar.
I would like to apologize for this unpredicted noise. Sorry.
It doesn't matter, but I couldn't share my screen because of, I think Nanvet Kumar is sharing.
Professor, please, can you stop sharing your screen so we can share a third presentation? You can just click somewhere on the stop sharing button, please.
Okay.
Is it okay now?
Is it visible?
Yes, yes,
okay,
yes.
Thank you. Okay, hello and welcome all. Kaan Küçükerdem speaks. I am research assistant at the Iğdır University, and I'm gonna present my presentation titled Solar Energy Used for the Irrigation of Maize Production in Harran Plain of Turkey. This is the outline of my presentation. As you know, irrigation is really important, and main purpose of irrigation is to provide the water required by plants in timely and sufficient amount with minimum energy and operation cost. World farmers use fossil fuels as energy sources, which are non-renewable and environment unfriendly. On the other hand, most of farmers in the world are using conventional methods of irrigation, which cause a huge loss of water and precious source of water, reduce yield as well. Thus, the need of the time is to use sustainable approaches in every field to use our resources. Solar energy used in irrigation. Solar energy is one of the best renewable energy sources, which can be combined with mechanical system to pump irrigation, transfer the water, as solar radiation coincidence with crop water requirement. Crops require more water as solar irradiation increases, and therefore more water can be pumped. Furthermore, it's a long-term cost saving and environment friendly resources. The use of solar power drip irrigation system reduces the energy and water consumption between %40 to 80 in agriculture sector, as well as increase the yield up to 100% and enhance the environment. Advantages and disadvantages of this type of solar irrigation system. There are no or less maintenance requirements. Operating time is long. They do not use fossil fuel and therefore do not pollute the environment. They use the sun as an energy source. In irrigation applications, time when water is most needed is the time when solar radiation is greatest. These advantages are initial investment costs are high, PV panel efficiency, photovoltaic module efficiencies vary depending on climatic condition. I wanna share the solar potential of Turkey, Şanlıurfa City and Harran Plain. As you can see the table, Şanlıurfa and Harran Plain has higher radiation and sunshine duration than Turkey average. This is really most important for the irrigation application at that region. Solar irrigation system design variables. Actually, I want to share purpose and scope of this study. Solar PV irrigation system needs to be dimensioned as accurately as possible. In design of SPP system, it's necessary to calculate the total height of water will be pumped, daily water required, and average amount of solar energy in the region. In this study, it's aimed to determine design criteria of photovoltaic installation required for water pumping system for drip irrigation. For this purpose, methods to be followed to determine the design criteria, such as water requirement of maize production, total irrigation requirement, daily hydraulic energy required to pump a certain volume of water to a certain height, the highest amount of energy of that PV modules should provide, power of PV modules and solar cells requirements are explained. Solar powered irrigation system mainly difference three way, and design without battery, and you can generate electricity from the PV array, and you can use it directly in DC motor pump, and you can design with battery, and also you can generate the electricity PV array, and you can use with DC motor or DC load. And also, if you have extra energy, you can charge the batteries. And also, this third one is design with battery and inverter. And you can use the electricity for AC and DC load with inverter. And if you have extra energy, more energy, if you like, you can charge the batteries. Solar powered irrigation systems, amount of water pumped in direct connection SPP system depends on properties of PV array, current voltage outputs, conversion efficiency and slope, meteorological factors, radiation intensity, air temperature, and hydraulic system factors, height of pipeline. As you know, photovoltaic module or array has consists of cells, and cells. After cells, you can make a module, and if you want, you can module in a series and parallel connection. In this study, we used monocrystal silicon module. It has maximum power 100 and maximum power voltage 23.3 and maximum power current 4.3. Equipment used photovoltaic system, basic equipment, solar modules, batteries, charge controller and inverter, auxiliary equipment, battery cabinet, counter, power monitor, fuse, diodes, cables, and mounting materials. Electric motor, depending on the specific of application, it can be directly connected to the PV array when a DC motor must be used. On the other hand, in the case where an AC motor must be used, a converter, often called a contactor, is placed between the PV array and the motor. For submersible pump system, motor and pump unit are designed together. For such application, user does not have possibility to select motor and pump unit separately. In the case of using surface pumps, it's possible to select the motors and pump units independently of each other. Pumps used in SPP system are divided into three groups according to their application characteristics. Submersible pump, it's used to withdraw water from deep wells. Surface pump, it's used to transport water from shallow wells, lakes, and rivers. Floating pump, it's used to withdraw water from the water sources with adjustable height. Submersible pump system and surface pump system, you can see the figures. You can see from the figures. Inverter, if an AC motor is used in SPP system, an inverter is required. It also keeps motor pump unit constantly dry and saves water by shutting down the system when the water tank is full. Design of drip irrigation system, as you can see in the figure. I'm gonna share some water requirement, determination of water requirement, a determination of evaporation. You can calculate this formula, and also you can put some data on CropWatt program, and of course you can calculate the evapotranspiration. Determination of water reserve in soil, you can calculate with this formula. Determining annual water requirement for crop and total irrigation requirement per day for drip irrigation system. You can use these formulas when you're calculating. Drip irrigation application variables, dripper selection, dripper selection and number of drippers, calculating with this formula. Applicable water amount, irrigation interval, and irrigation duration. You can use these formulas. Drip irrigation design variables, head loss. In determining allowable head loss for the main pipe, cannot exceed 30% of operating pressure is applicable. For the hydraulic design of drip irrigation, the difference between the manifold inlet pressure and the outlet pressure of the last dripper connected to the last lateral should not exceed 20% of the operation pressure. Number of drippers on lateral and lateral pipe block values calculate with these formulas. Power of water pump and power of electric motor values can calculate with these formulas. Energy requirements for irrigation system, required hydraulic energy and hydraulic energy at output of the SPP system. You can calculate with these formulas. Electric power of PV generator, PV array surface area, number of photovoltaic modules were calculated with these formulas. Findings, calculation, our calculation has some exceptions. Calculations were made for 2 decayers, a total depth of 100 meters for water source, and operation pressure is 1 atm. For maize production, row and intra-row spacing was taken into account as 0.7 and 0.20 meters respectively, and evapotranspiration value was 7 millimeters per day. Effective root depth for maize is 0.9 meter. The usable water allowed to be consumed is 30%. Infiltration rate is 8 millimeters per hour, and the dripper flow rate is 1.6 liter per hour for medium textured soils. Irrigation interval is 7 days. Net irrigation water requirement for the area to be wetted is 46.48 millimeters. Net irrigation water requirement to be applied in each irrigation is 6.59 millimeters per day, and total irrigation water requirement to be applied in each irrigation is 54.67 millimeters per 2 decayers. Lateral pipe length was calculated as 50 meters. Number of drippers in each row was 125. Each lateral flow rate of 200 liters per hour, and total lateral flow rate is 11.42 cubic meter per hour per 2 decayers. Power of irrigation pump is calculated 3 kilowatt. Pump type is 5.5 inches with 3 stages submersible pump. The pump flow rate is 5.5 cubic meter per hour, and the total installed power of PV energy system is 5 kilowatts. This is the result and recommendation in a growing season in Haram Plain, since maize is irrigated with the furrow irrigation method.
Excuse me, dear Khan, we have 1 minute left. So if you can switch quickly. Thank you, sorry.
Thank you. I'm gonna finalize it. Furrow is irrigation method. The fertile layer in the upper layer of the soil flow into the drainage channels together with irrigation water. It has been determined that the groundwater rises and the salinity increases in some production areas due to the wild irrigation in Haram Plain. Modern irrigation methods, drip and sprinkler system should be adopted in all production areas immediately. Tassel flowering period is the most sensitive period for maize. During this period, it was determined that farmers in the region were not sensitive to irrigation. In order to maintain vitality of pollen in tassel flowers, plants must be irrigated during this critical period and root zone must be moist. In order for plant to meet moisture lost by transpiration due to the air temperatures through roots, the humidity in the root zone must be high. Due to the fact that water is very deep and there is insufficient water, the entire land must be irrigated with the pressurizing irrigation. In addition, since there will be a water saving of at least 30% between flood irrigation and drip irrigation, water charge will decrease accordingly. In addition, it has been observed that the less fertilizer given in different periods with the drip irrigation system has a 10% positively effect on yield. Sorry, 100% will be. By integrating a driver into the pumping system, it will save approximately between 10 to 40 kilowatt hour of energy depending on variable water needs. Considering that each well works 10 hours for irrigation per day, this will provide approximately 7,500 kilowatt hour saving per month. Considering that this enterprise irrigates actively for 6 months a year, the annual saving will be 45,000 kilowatt hours. Thank you for listening.
Thank you very much for also great presentation. We are out of time, but we have 2 questions. So I would like to read you these questions because we don't have, I don't know, mingling in contact. So now I will read it. The first one is, what is the packing factor value for solar panel used in this work? It's the question from Professor Navneet
Kumar. Okay, I really remember very well, and I'm gonna check my values, and I'm gonna write you Navneet Kumar, Dr. Navneet Kumar, and power of irrigation pump 3 kilowatts.
Okay, you can also read the questions, right? Or the second one is power of irrigation pump 3 kilowatts, 33 stages submersibles.
Okay, I'm not very well and in irrigation pump, but I'm gonna check the data and I'm gonna note that this Nizar Ben Ezin, your questions. I'm gonna write you if you put your email on question or on chat box.
Khan, I think you have our all emails. Akif sent us, when Akif sent us a mail with the Zoom link, I think we are all in this, so you can pick.
Yes, of course. I'm gonna catch from there.
Okay, okay. Thank you very much one more time. And we are proceeding to our next speaker. And our next speaker is Nizar Ben Ezin. I hope I'm pronouncing all these names good. Is Nizar Ben Ezin here with us?
Yes. Good morning.
Good morning. Welcome. Can you please take your presenter, share your presentation, and start with your presentation. You can shortly introduce yourself so we can know you more, more details about you, just in short. Thank you.
Thank you. I'm Nizar Benazin, energy engineer and associate professor at National Engineering School of Monastir, Tunisia. I present today our research development of experimental investigation and theoretical model of water lithium bromide bubble pump operated absorption refrigeration machine. It's partaged the presentation. It's good?
Yes, it is very good.
Okay, thanks. Donc, I begin by the working principle of bubble pump absorption refrigeration machine, then the thermodynamic analysis. I present the simulation results, and then the designed experimental prototype and experimental results. The absorption refrigeration machine is produced cold at the evaporator in the basic of heat-driven generator. It is composed by an evaporator, an absorber, a generator, and a condenser. The circulation of solution between absorber and generator is done by a mechanical pump that consumes electricity. Our investigation in this research development work is to substitute this pump that consumes electricity by a heat-driven pump. The obtained ammonia or the obtained water lithium bromide absorption refrigeration machine is composed by a generator, bubble pump, boiler, a condenser, an evaporator, an absorber, and a solution heat exchanger. A thermodynamic simulation model is developed to analyze the performance of this machine. The modeling process proceeds by the following steps: formulation of the mass and energy balance governing the various refrigerator components, specification of the fundamental operating condition, the driving heat source temperature, the temperature of the produced cold, and the temperature of the environment. Characterization of the heat and mass transfer process on the various heat and mass exchanging device. Specification of the state of working fluid and operating condition at several locations of the installation. For each component of the machine, the mass balance, energy balance, and heat transfer characterization are developed. For the absorber, for the solution heat exchanger, we pay attention in the crystallization phenomena that take place in the solution heat exchanger and in the absorber. Our first research laboratory, our first experiments in laboratory, we can observe the crystallization phenomena of lithium bromide that obtained between the solution heat exchanger and the absorber. This is due to the increase of concentration of solution heat exchanger when we increase driving temperature in the generator. The simulation, to simulate this machine, the simulation model is constituted of a large set of nonlinear equations, mass and energy balance, and thermodynamic properties equation which is numerically solved. The cycle is simulated for 2 cooling medium temperature, 27 for water cooling, and 35 for air cooling. In each case, the simulation is performed for 3 driving heat temperature. The system parameter effect on performance are down. When increasing the driving temperature, the COP reach a maximum of each cooling medium temperature. The increasing of driving temperature increase the difference of concentration between generator and absorber, between rich and power solution. This increase of difference of concentration decrease the mass flow rate of solution needed to circulate in this machine. Also, the increasing of medium cooling temperature decrease significantly the coefficient of performance of this machine. When the temperature of medium cooling the temperature of cooling medium increase, the difference of concentration of lithium bromide solution between absorber
नहीं अभी चल ही रहा है इसमें, तो अब आपको वो मैं मैसेज भेजा था ना, मुझे थोड़ी सी कॉल करके बता देंगे, अनुज थोड़ी बता देंगे कॉल करके आपको।
And the mass flow rate of solution increase.
हाँ.
The design of the experimental prototype, the generator is designed as. Good.
Okay, I'm sorry. Can I see Khan? And please, can you mute yourself, Khan?
Sorry. वो वही बता देंगे ना, मैं नंबर उनका दे देता हूँ।
I think now we solved everything.
I continue?
Yes, please. I'm sorry, this is happening. They forgot to mute their microphone. Please continue.
Okay. Donc, for the design of the experimental prototype, the generator is designed as bubble pump with boiler and collector to collect solution concentrated on lithium bromide from the absorber. The liquid vapor separator is made of transparent ice to visualize the flow and the start of pumping. The obtained designed experimental prototype is composed of a generator, an ice visor, a condenser, an evaporator, an absorber, and a solution heat exchanger. The thermocouple type CATOM uses the temperature in the different point of the installation as incorporated in the inlet and outlet of all the components of this machine. The fabricated prototype in COPA is presented, and after fixing the probe and the pressure and temperature measuring device, a display and data acquisition board is designed. The experimental results, the first objective in experimentation is determination of the starting thermal power to know after how we can couple this machine with solar collectors. The experimental results show that the starting power of a 8mm bubble pump is equal to 46 watts at a disruption temperature of around 18 degrees Celsius. With this heating power, the evaporator began to produce cold at the temperature equal to 6 degrees. Necessary for to determine the efficiency of the solution heat exchanger, the temperature, the measurement of and monitoring of the temperature at the 4 terminals of the solution heat exchanger clearly shows that it operated with good efficiency. Donc, this machine, this new kind of machine that thermally driven to produce cold can be then coupled to solar cooling. That is, we can produce cold by solar, collected by thermal solar collectors. Thank you for your attention.
Okay, thank you very much for this great presentation. You are completely on time, and we have two questions. First one is, which software was used for this study? And second one also was, which software used for simulation purpose?
For the simulation,
yes.
I use the
for the study in general and for the simulation purpose.
For the simulation purpose, I utilize the Fortran program.
Fortran, okay.
Fortran program, yes.
Okay, thank you. And the second one is, what are the different parameters and boundary conditions for simulation?
The different parameters are the driving heat temperature, because the objective of this work is to produce cooling by solar panels, by thermal solar panels. Donc we do this experimental, the power and the temperature of heat driving this machine to produce cold. And this machine is very influenced by the temperature of the environment, the medium temperature, cooling temperature, to cool the condenser and the absorber.
Okay, thank you very much. I suggest to proceed to our fifth speaker today. And thank you one more time. And our next speaker is Mustafa Kemal Kaymak. Please take your presenter, and floor is yours. You have 12 minutes plus 3 minutes for questions and answers. Are you here with us? If host can check if Professor Kaymak accepted the presenter invitation. I saw the comment here.
Okay. Hello, hello, dear Kovac. I can start my presentation if it is possible. Can I start now?
Yes, right now, please.
But other participants is sharing his screen. It have to shut down.
Okay, Nizar, please can you stop sharing your screen so Professor can share it
okay.
its own. Thank you very much.
Okay.
Thank you.
Thank you.
Good morning, ladies and gentlemen. I am Mustafa Kemal Kaymak. I will mention about the floating PV systems and electricity generation comparing with the terrestrial PVs. Okay. This is the content of my presentation. It has a 7 parts. First of all, I want to talk about solar energy. Everyone here knows a lot about the benefits of the solar energy. However, what I want to point out is weaknesses, especially the area it covers for many years, at least 25 years it covers any territory, and efficiency problems. For solar energy investments, double usable areas must be targeted. For example, rooftops, highway and railways. Vicinity of highways and railways is possible to construct floating PV or PV or only PV pipelines over the pipelines, over the irrigation canals. And water surface, which is the part we are interested in. Floating PV easily built on the water surface. This is the schematic view of floating PV systems. Component of the PV could be listed as below: floating platform, buoyancy anchor, PV panels, and electricity cable. Generally, last three component is same all the project, but depend on the location and project, floating platform can be changed. Sometimes it occurs only floated made from polyethylene. Sometimes pontoon and metal construction. It depends on the location, weather condition, and project design. As can be seen in the figure, there is a rapid acceleration in the FPV installation after 2015. So it is expected that FPV market reached to $2.5 billion until 2025. Who can use this kind of project or FPV systems? Water and Sewage Administration of cities, for example, in Istanbul, İSKİ can use this kind of project. Irrigation cooperatives, a lot of alternative here. Especially the most important thing is the Middle East and Africa because of the water shortage. And the other future of the FPV systems is the reducing of the evaporation so that Middle East and African countries governments can easily save their fresh water. Sometimes the other countries or many governments try to cover water surface with membrane or the other materials to save water. It is effective, but cost is very high. The first floating PV systems installed in Japan in 2007. One of the aim of this system is to compare water and air cool systems. It is important that it is not necessarily additional area so that it can be protected farmlands for future usage and needs, and also cooling of the water to increase efficiency of PV module. These are the some photos of floating PV application. It is easily seen that the European countries such as Italy and Spain were the leaders at the first, but nowadays China has taken over the leadership to build floating PV systems. This is the picture how to floating PV systems move to water surface. It is known that low temperature is better for PV cells, so that water cooling effect carried out by FPV can help to improve efficiency of PV cells. After this point, I will mention about our project. This is the area photos of Büyükçekmecelik. Right side is the terrestrial PV. Left side is the two floating PV project which we have done. The last one will be showed in the next page. Three floating PV systems have been installed in Büyükçekmece. Büyükçekmece Lake, which is the biggest lake in Istanbul, to supply fresh water. The main aim of this project is to increase amount of renewable energy usage in Istanbul and make awareness and recognition of people, of manager or administration to use floating PV systems to save fresh water of the city. Especially, I can say owner of the project is İSKİ, Water and Sewage Administration of Istanbul. What we do up to now, before the project, we collect a lot of data about territory, weather condition, especially personal assessment and experience from İSKİ worker, which is live near the Büyükçekmece Lake and work near the Büyükçekmece Lake. And then we investigated the lake shore to find suitable places for FPV installation and move to water surface. And then we calculate wind and wave load calculation under extreme weather condition. But it's very complicated modeling and formulation because there are a lot of 3D software, CFD software and practice formula, but they give different results so that our relation is to make a lot of prototype to observe what's happening in the on the lake surface. And then we design 9 kilowatt power floating PV. It is rigid system like a terrestrial. After this gain experience, we design and install 90 kilowatt power FPV system. It is semi-flexible. Last, we design and installed 30 kilowatt power floating PV. It's full flexible system. After the installation, we observed meteorological electrical parameters on the lake. This is the meteorological observation system on the surface of the lake. This is first floating PV system in Turkey. PV similar to terrestrial PV. We add some innovation like this element. Maybe you can see it, but it is very little. This element allows us to change of the angle of the PV panel depend on the incoming solar radiation. This is a unique system when we compare the other unique element component when we compare the other systems. Metal structure is aluminum, made from aluminum. After for a while, we gain a lot of experience from first system, and then we design 90 kilowatt power floating PV. This is the schematic view of the second system. This is semi-flexible. This hinge supply the movement of the system one way, only one way, so that we call this semi-flexible. We add hinge and kovan. Kovan provide the smoothly load transfer from the metal construction to pontoon. It's kind of a transmission element. The main principles, this is the inside of the pontoon. Kovan placed here, replaced here when we install and manufacture. Main principle of this system, domestic design and product, maximum efficiency, environmentally friendly, and shouldn't affect the lake ecology harmfully. Should allow, this kind of project should allow water flow and do not prevent solar irradiation totally reaching on the water surface. This is the other pictures during the installation of 90 kilowatt power systems. This is the completed view. This is another picture of three different FPV system. This left side is digit 9 kilowatt. The right side is the semi-flexible. in the middle, it is seen the full flexible system. The total amount of electricity generated from 90 kilowatt power FPV system is, I can see, is approximately 70.4 megawatts, and the capacity factor is 42% from 19 May to 4 July. Maybe you can say why it is so high capacity factor, because summer sunny weather condition reason of that, cause of that. After TÜBA FPV design and manufacturing, we gain a lot of experience, so that to solve some problem, it is necessary to design full flexible FPV. This is the some problems we have faced up in the project stage. First of all, this is the first application in Turkey. During the project, some authorities, manager, administration are being conservative. It is not easy to persuade some authorities. And it was difficult to find workmen to employ on the water, on the floating PV surface. There are some regulation gaps related with this new sector. There is no national and international standard in this sector. Encounter problems on the lake. Several weather conditions on the lake, it is so important for us, because this is the unique example in the, our project is the unique when we compare the other project around the world. Wind driven wave height, unstable load distribution on the system by the wave impact, manufacturing of the FPV because of the uncommon design. Workers and technicians cannot understand or figure out what the design is, because it is uncommon. They didn't produce this kind of design. Joining of each element on the lake surface under effect of the wind driven wave is very critical situation. Working under severe weather condition disturbs the workers during the process. After FPV design, we have a lot of experience, and our opinion, realize new design, full flexible design. This is the first prototype of the full flexible system. And then we produced and installed this prototype. After a while later, successful of the design brave us to complete 30 kilowatt power floating PV systems. This is the final version of the floating PV design of us. What is the main principle of the full flexible system? First, it has to be cost effective and 6 freedom degree of motion on the water surface, because of the continuously wave movement is.
Mustafa,
yes.
You have 1 minute more just left.
Okay, thank you.
And we have some.
When we compare the Natic, I didn't understand. Maybe my connection is weak. Terrestrial PV generation is higher than the floating PV system. It's a daily graphic. As a contrast to expectation, it is seen that electricity production of the both systems do not have significant difference. Some days, last systems produce higher than the terrestrials, some days vice versa. Without any discussion, in Turkey, we are trying to gain these systems and build a new energy sector. Based on the gained experience, a new technological trading item has been developed since 2016, and it is ready for application around the world. The most important point is to consider and design these systems under extreme weather and wear condition. Without installation this kind of system in real condition, it is impossible about PV systems. Field experiment is very important for this kind of project. Comparison terrestrial systems efficiency with FPV, it is not easy to say which one is the better, because capacity factor of 90 kilowatt power is higher than terrestrial. But however, for the last version of flooding PV, 30 kilowatt power, vice versa, it is experienced that flexible PV system constructed on the lake at harsh wave condition need flexible electric cable connection, design and component. Determination of mooring and anchoring system depend on the water level, highly related with the wave height is another important point. If somebody want to know more information, we have two papers about this project. If you want, you can read easily this and gain a lot of information about the flooded PV systems. Thank you very much for your attention.
Okay, thank you, Mustafa, for this nice presentation. So we have two questions. First one is, what is the average yearly solar intensity in Istanbul? And the second one is, what is the working life of this system?
Sorry. Can I read? What is the working life? The last question, it is just prototype and research and development project. We expect at least 25 years lifetime. What is the average yearly solar intensity in Istanbul? I didn't remember the exact number. Maybe I can write an email about average solar intensity in Istanbul, Mr. Komar. That's all I can say. Dear Kovac, I can't hear your voice. You
okay, no problem.
Mute your...
We can okay, no.
Okay, thank you very much. I just have a comment on your presentation. I would like to book my place visit at this power plant once I come to Istanbul, please, because I'm wondering to see how does it work. And I have a few more questions from my side, but unfortunately we don't have time. So maybe next time on some other conference we can discuss on it. Okay, thank you very much. And our next presenter
Thank
you. Our next presenter is Desh Bandhu Singh. Please take your presenter and floor is yours. Please, thank you.
Good afternoon to everyone present here. Am I audible?
Yes, we see everything and we hear you.
Myself, Dr. Desh Bandhu Singh. I work as a professor in Mechanical Engineering Department of Graphic Era, TÜBA University, Dehradun. I have managed to publish nearly 100 papers in various national and international journals of repute and 7 patents. I completed my PG and PhD from Indian Institute of Technology, India. I'm going to present my research on effect of water depth on the solar single slope solar steel integrated with evacuated tubular collectors. So the objective of presentation is we calculated thermal efficiency, exergy efficiency, and productivity on hourly basis and daily basis. The 2 months were selected for estimation, June and January. That is, one represents summer and other represents the winter season. And then average daily thermal efficiency and daily productivity has been calculated. Before going to the result discussion, we have a short review. This is the active solar steel. So the work on active solar steel was first of all introduced in 1983. This was the system that was introduced in 1983. In this system, single slope solar steel was connected with the flat plate collector. This single slope solar steel works on a greenhouse effect. How does it work? When the solar energy falls on the surface of the solar steel, some parts get reflected, some absorbed, and remaining is transmitted to the water surface. Again, when the solar energy falls on the surface, reaches the water surface, then some part is again reflected, some is absorbed by the water, and remaining is transmitted to the blackened surface at the bottom. This blackened surface again transmits heat to the water because temperature of blackened surface is higher than the water. Here, the purpose of adding collector is to increase the heat to the water so that higher evaporation can be achieved. In the case of passive solar steel, when no collectors or any other auxiliary devices are added to solar steel, it is the passive. And the output of passive solar steel is very low, nearly 1 to 3 kg per meter square per day. So to overcome this difficulty, this single slope solar steel integrated with collectors, we can say active solar steel was introduced. Next, we can see in this system, this power was supplied from the grid. So it is not self-sustainable. To make the system self-sustainable, another study was done by Kumar and Tiwari. In these 2 collectors were added, and 1 collectors were integrated with the photovoltaic panel. What does this panel do? It generates the electricity and drives the pump. So it becomes self-sustainable and it can be installed anywhere. Next study was done by Singh and Tiwari. In this, both collectors are integrated with the photovoltaic panel. The objective of adding photovoltaic panel was to increase the electricity generation. Basically, how much area should be covered and what should be the packing factor? It depends on the requirement of electricity and water, potable water. Now, next concept was that if we add parabolic surface to flat plate collector, then obviously heat gain will increase. So this study was again proposed by Singh and Tiwari, and in this system, again output is water, fresh water, and electricity. Further, this is the system on which I am presenting my research. Some parts has already published, like on exergy parameter, environmental parameter, and then energy matrix. These parameters have already been studied. Remaining parameter is effect of water depth on the efficiency and productivity. On that part, I am going to present here. So what is the advantage of adding evacuated tubular collector? Here we can see in the cross-sectional side view of evacuated tubular collector, we have a vacuum between 2 glass tubes. So due to presence of vacuum, loss due to convection does not take place. So loss is less. Due to lower loss, output will be higher. These are the fundamental equations that has been used. To obtain the fundamental equations, we have to write energy balance equation based on first and second law of thermodynamics. Basically, it is the first law of thermodynamics. Energy input is equal to energy output. So what we do, first we write the energy balance equations for all components, and then we solve this. After solving this, we get the unknown parameters in terms of some known parameters. What are known parameters here? Known parameters are like solar intensity, then we can say some constants, then atmospheric temperature. So there are the equations. Equation 2 is for heat gain. Third is when we put TF1 in heat gain equations, we get the general equations. And again, if we integrate Q1 with the equations of solar steel, we get the equation for water temperature and glass temperature. Once we calculated the water temperature and glass temperature, we can calculate hourly yield using equation 6. Here, heat transfer coefficients can be calculated using equations given in like 7, 8, 9, and 10. And then we can calculate exergy. Exergy is calculated on the basis of second law of thermodynamics. Again, here we need a water temperature and glass temperature, also atmospheric temperature also to calculate the exergy output of the system. So for the analysis, we have done analysis for efficiency and productivity, efficiency, thermal efficiency, and exergy efficiency. On thermal efficiency part, equation 12, you can see output energy upon input energy. That is gives the thermal efficiency. And if we add output, hourly output to 24 hours, we will get the daily output. Similarly, for daily input. In input side, we have heat gain from collectors, then solar intensity falling on the surface, and then electrical energy that is supplied to the pump. Here, electrical energy PU has been divided by 0.3 to convert electrical energy into equivalent thermal energy because we're dealing with the thermal efficiency. Then equation 14 and 15 represents the exergy efficiency, and 16 and 17 represents hourly productivity and daily productivity. So where we are dealing with the productivity, productivity means getting more and more, less and less input of resources. So here what we have done, we have converted hourly yield into monetary terms. Similarly, input has been converted into monetary terms, and then ratio gives the efficiency. So what is the advantage of calculating productivity? What is the advantage of calculating productivity? The advantage of calculating productivity is to find the feasibility of the system. If it is more than 100%, system is feasible, otherwise it is not feasible. So these are the equations for calculating the cost, input parameters, and then methodology. For methodology, we have used the computer code in MATLAB. All equations and input parameters, input data have been fed to the MATLAB, and output have been obtained. These are the input parameters. The solar intensity and atmospheric temperature, these are obtained from Indian Meteorological Department, Pune, situated in India. And result discussion, you can see in the result part, we have plotted those results obtained from the MATLAB, like thermal efficiency, both for winter and summer condition. We can see thermal efficiency decreases as the depth increases. Why? Because increase in depth results in the increase in heat content. So the solar energy is absorbed by the water, so efficiency, output decreases and efficiency also decreases. Figure 7 represents the average value of thermal efficiency. You can see as we increase the depth of water, efficiency first increases and then becomes almost constant. We can see at 0.56 meter water depth, it becomes almost constant. So you can say this is the optimum value. Similar plot is for exergy efficiency. Figure 8 represents exergy efficiency. Again, exergy efficiency also decreases with the increase in water depth for the daytime. But if you see overall, then it will increase because at the night time output is higher due to a higher mass content of heat content of water mass. So figure 9 represents the again exergy efficiency variation, and figure 10 represents the you can say average efficiency variation. Then productivity, you can see here interesting thing with the productivity and the daytime. You can see the productivity is decreasing. At the night time, it is increasing. The reason being that the daytime, as water mass increases, the heat content of the water mass also increases. So solar energy input to the water is absorbed by the water mass, and this absorbed energy utilized at the night time. So at the night time, output is higher, so efficiency increases. So productivity increases with the increase in water depth. Similar variations in figure 12, and then we have calculated on the basis of these two average daily productivity. And you can see for average daily productivity first increases and then decreases. This is for the whole day or 24 hours. And you can see it is optimum for 0.56 meter of water depth. So you can see further conclusions part, we have see the hourly thermal efficiency and exergy efficiency decreases with the increase in water depth in the daytime. Only productivity in the daytime it decreases, but the nighttime increases. And if you see overall, the efficiency and productivity increases. So the overall daily thermal and exergy efficiency first rises and becomes constant beyond 0.56 meter water depth. The value of hourly productivity of solar energy operated water purifier increases with the water depth, and the average productivity for has been found to be optimum for 0.42 meter water depth. So we have certain recommendations. What are the recommendations? This optimum values obtained for thermal efficiency, exergy efficiency, and productivity, and experimentally it has not been tested. So it is suggested to experimentally test before installation. And further, one recommendation is more that it has been studied for New Delhi only. So we are planning to extend it for other geographical conditions. There are certain references. Thank you. Thank you for listening patiently. Any question?
Thank you very much for this interesting presentation. Does anyone have a question from the attendees or panelists? If not, I have one. Do you have some roughly calculation of the cost of such system?
Pardon me?
Do you have maybe some roughly calculation about cost? How much would this system cost in total?
Cost already I have shown in the presentation. You can see.
Mm-hmm.
Cost equations have been shown for the cost, and we have calculated the cost. The cost has not been shown here. Cost has been incorporated in the productivity because input cost is there. So roughly, if you say uniform end of year annual cost, so it comes out nearly 3,000.
3,000 euros, dollars?
Rupees, Indian rupees.
Can you calculate it in euros or dollars?
If you calculate in dollars, it will come out nearly, you can say $50 to $60. $50 you can say.
$50,000 or?
50.
Dollar.
This is uniform end of year annual cost. Means we have distributed the cost for the whole life. And if you calculate uniform end of annual cost, so it comes out nearly $50. But if you see the overall cost of the system, it will be like 50,000 in Indian rupees. And if it is converted to dollar, it will be, it can be reduced on a scale of 60.
Okay, thank you very much. And now, according to the schedule, we should close this session, but we have additional presenter who was scheduled for the previous session, but missed it. So I would please you to stay to listen our last speaker. Just to check in my notes to read who she is. The presenter is Florence Aisweni. Florence, please take your presenter, and the floor is yours. You have 12 minutes, and we have 3 minutes for questions and answers.
Thank you so much for accepting to take this presentation. I really appreciate it.
It's confusing, Turkish time and everything. I was checking all the time yesterday and today. What is the correct time, please?
Exactly. Yes, so my name is Florence Aisweni, and I'm from the Robert Gordon University in the School of Engineering, Aberdeen. And here today, I'm to make a presentation titled Comparative Evaluation of Oil in Water Emulsion Separation with Aluminum Oxide and Zinc Oxide Nanoparticles Ceramic Membrane. So here is the outline. It's divided into 4 parts: the introduction, the preliminary feasibility evaluation, results and discussion, and indeed the conclusion and further work. So oil in water emulsion, it's actually oil and water mixed together. And most of these things come from industrial activities around the globe, ranging from cosmetic industries, food industries, pharmaceutical, metallurgy, and they are generated as waste products or waste materials that are discharged into the environment. And if discharged directly into the environment without treatment, can cause pollution. So based on these pollution, stringent environmental standards have been developed and created to limit give allowable limits of the discharge of oil water emulsion into the environment. Because of these stringent allowable limits, many conventional methods have been generated to either separate oil and water emulsions or at least reduce the concentration before discharge into the environment. But most of these conventional methods have their advantages and disadvantages, which I've listed some here. Most of it has a high operational cost as well as low removal effectiveness. Some can only remove big concentrations of oil in water or concentrations that are above 10 micrometer oil droplets, but they cannot remove concentrations that are smaller, below 250 milligrams per liter. And that is where our aim for this research comes in. This research actually aims at coating ceramic membranes with nanoparticles, basically aluminum and zinc oxides, on commercially produced ceramic membranes. This is going to be used to separate oil water emulsions and or reduce the concentration of oil water emulsions. The concentration we are looking at is 250 milligrams per liter and below. So the work of this nanoparticle is to actually increase the hydrophilicity of the ceramic membrane, thereby creating high flux and increasing separation and increasing also the oil rejection percentage. And we are looking at the possibility of creating two phases or complete separation of oil from water before discharge, and maybe see the possibility of reusing it. So that's the aim of this research. So membrane technology has been used over the years, and we've realized that membrane can be classified based on their pore sizes. And we look at different pore sizes as the image has displayed here. We have the microfiltration, ultrafiltration, nanofiltration, and then the reverse osmosis. And the individual pore sizes has been displayed. Membranes are actually made from organic and inorganic compounds, and the organic compounds membrane are called the polymeric membrane, while the inorganic compounds membrane are called the ceramic membranes. In this research, we are focusing on the ceramic membranes, and for these so many reasons that has been listed on the next slide here. It has a longer shelf life, mechanical and chemical strength. It can survive in organic solvents and has a compact design. Most importantly, it can eliminate secondary separation. This is the membrane that we are working with. All the characteristics of the membrane are listed below the picture here, which contains the length, the outer diameter, the internal diameter, the glazed ends, and then the pore size of the membrane. The whole idea of the nanoparticles is to coat nanoparticles on this membrane to increase hydrophilicity and possibility of reducing fouling in the membrane, because that's the major reason why membranes have not been used for most industrial separation, because after several usage, it causes the membrane to foul. So if there's a high increase in hydrophilicity, we see the possibility of reducing fouling using nanoparticles. Okay, so the next slide is talking about the methodology that has been used here. The methodology involves modification of this ceramic membrane with nanoparticles. We characterize these nanoparticles And then we create these oil-water emulsions that we are going to use because we are looking at concentrations below 250 milligrams. And then finally, separate this oil-water emulsion using a rig, in-house built rig setup. This is the rig setup diagram that has been built in-house in the laboratory for this experiment. And this is a schematic of the diagram. It starts with a feed tank A here, where the created oil-water emulsion is poured and moves through a tubing and is being pumped via a peristatic pump into the membrane module C right here. The membrane module houses the coated ceramic membrane, and the pressure the pressure in the membrane module will be measured using a pressure gauge D. Now, permeate comes out of the membrane module through this valve F and into a cylinder that is placed on a weighing balance. And at intermittent time, a measurement is recorded. Any other substance that has not been separated in the membrane passes through this valve E, which is called the retentate, and is being measured by a flow meter and goes back into the feed tank. So it's actually a continuous flow. So the results, we did a little preliminary evaluation of the ceramic membrane support that we used using scanning electron microscope, and we realized that the ceramic membrane support is rough and densely packed and has an uneven pore size distribution. And this is relevant in the next two slides that I am going to talk about. We also conducted elemental composition evaluation using energy dispersive X-ray analysis to find out the elemental composition on the ceramic membrane support. And we had titania, zirconia, bromine, and iron present. So we also looked at pure water flux passing through this rig and see whether if it's consistent over time, it's going to increase not just the flux, but also the possibility of antifouling. And we realized that passing the pure water flux through it remains stable over the 30 minutes duration that it went through. The significance of this preliminary evaluation was that we had an uneven pore size, which has the possibility of increasing the flux. We had a steady pure water permeate flux, which shows the possibility of antifouling. We had the presence of iron in the membrane that will be used in self-cleaning of the membrane using magnetic properties, because of its magnetic properties rather. And then we had the presence of titanium oxide, which helps in increasing the roughness. The higher the roughness is, the higher the flux when it comes to separation. Finally, we had the ceramic membrane robust, which is strong. We all have seen we listed in previous slides above the benefits of the ceramic membrane, that it can withstand high chemicals. So based on all these are the significance of the results. In conclusion, from the experiment carried out on morphology and pure water, we have indicated that there's a possibility of high flux, and that any variation from the flux will have to come from the hydrophilicity, pore size, and the porosity. The pure water flux on unmodified ceramic membrane remain the same over time. The next step on this research is to actually coat the ceramic membrane using aluminum and zinc oxide and passing it through and separating the oil water emulsion using this modified membrane. Thank you so much for allowing me to present, and I welcome any other questions that might arise from this.
Thank you very much, Florence, for this interesting presentation. Since you are the seventh presenter in this session, I would kindly ask if someone has a question to write you on your email, to to not take time of the next sessions. But your presentation was interesting. I have so many questions on it, but I hope we will meet somewhere in person, and we can also talk or email or something like that. Okay, thank you all of you today. Each presentation was extremely interesting, detailed, and impressive. And I wish you a wonderful day, and I wish you nice participation in this online event. Have a nice day, and greetings from Croatia. Bye.
Thank you. Thank you.
Good afternoon. Did you hear me?
Yes, good afternoon.
Yes, we
Good
can.
afternoon.
Good afternoon.
I would like to welcome with you all. I am Professor Safa Riyad from Cairo University, Faculty of Pharmacy, and I am Vice Dean for the faculty. I would like to introduce, we have 3 speakers in this session. We will start with Professor Ali Kindab. Hello, Professor Ali. I would like to make a small introduction about Professor Ali. Professor Ali is a general manager.
Excuse me, something wrong with my voice and AirPods. Is there something problem with connection? Let me check it. Sorry for that.
Did you hear me now?
There's no connection. I don't understand.
We can hear you loud and clear.
Yeah, we can hear you.
Okay. Professor Ali Kindab is General Manager, graduated from the Department of Mechanical Engineering at Middle East Technical University in 1990. He began his professional career at JAMA Group of companies, and later he worked at the Juris Ishat Mohandislik. He joined Zorlo Energy Group in 2008 as Deputy General Manager at Zorlo Industrial and Energy Facilities Construction Trade. He was appointed as a General Manager of Zorlo Energy Group as of January 1, 1917. Mr. Ali Kindab became the chairman of the board of the Geothermal Energy Association in July 2020, and he is also a board member of the Turkish Cogeneration Association. I'd like to welcome with you, Professor, and we have 25 minutes for your talk and the 5 minutes for Q&A. Please go ahead. Sorry, I can't hear your voice.
You're muted.
Yes, okay.
Can you hear me right now?
Yes, okay. Very good.
Okay, with my earphones, there's something wrong. I don't know why it's wrong. So I couldn't connect my earphones. I'm trying to give my explanation, my presentation directly. Sorry for that. So I have a presentation for today. Let me share this presentation. Just a minute. I'm looking for things to connect. How to load the presentation? I'm trying to understand. Share screen. Okay, sorry. Nerede abi bu? Yine bulamadım ya. I don't understand why.
It is below the screen in the green color. Share screen.
Share screen. Okay, I'm looking to share screen. On share screen, I cannot see the file.
The first you have to open your file into your computer, then you are going to share screen.
Understand. Okay. Just a minute. Sorry for that. Share screen, desktop. Something. I don't know. With this computer, something is wrong. Let me try from the other computer. Sorry. Yok yok. I'm quitting from this one. Şurada. Okay. We will quit from this computer and I will return to our computer. Sorry for this. Şu şeyden açarsın. Safa, can I change? Çevirdim ben. Tamam, bir dakika. Tamam. Şimdi benimki zor. Diğerine. Hangisi? Ya, şuna. Cancel diyelim.
If the presentation is not ready, we can move to, okay.
Is it okay?
Yes, I see it.
Okay. Okay. Okay. Sorry, I think I lost.
No.
Okay. Okay, let me continue. Sorry for this inconvenience again. Let me arrange just my computer a little bit. Okay. So, okay. Thank you very much for your patience. Sorry for this inconvenience again. And I have a presentation for today. My name is Ali Kunda. I'm chairman of Geothermal Energy Association. And I'm very happy to be here and to give you some speech on my issues. First of all, I would like to say good afternoon to all participants, and I would like to thank the organization committee for this event. It's a pleasure for me to join this event. Also, it's a good opportunity to discuss energy, science, and technologies. Today, I'm going to present about geothermal energy in Turkey. Most recent developments in Turkey about geothermal energy and the legislation, regulations, incentives, and price mechanism, and also about our huge potential of geothermal energy in Turkey. So what I will address for today in my presentation, I will give some information about energy, how energy, geothermal energy works, also geothermal energy, and give some information geothermal energy in the world as well, and in Turkey. So also we have a good incentives mechanism, a price mechanism in Turkey for geothermal energy developments. So I will give some information about this. The other thing is about geothermal energy in Turkey will be permit process. You know, this is a very important process for the new projects, implementation of the projects. That's why this is a good topic to share at this moment. And before last words, I will also give another information about the sources, I mean, geothermal sources and geothermal, again, potentials in Turkey. And the last one, the lessons learned. Okay, let me go to others, next slide. On this slide, you can see some figures and some pictures on this slide. So this gives you some information about the geothermal energy, geothermal resource, I mean. Geothermal resources, you know, either composed of the hot water, steam and gas resources and created by the heat accumulated in the depths of the earth. Or the thermal energy power, you know, the earth has already stored. Sorry. Okay. So my colleague, okay, put some figures on the screen. So sorry again. My new view not clear. So right now it's clear. So as shown in the figures, as a general principle, hot water and steam are brought to the power plants by these means of, you know, transmission pipes from deep of the earth, and this energy coming to the above ground is converted to energy in turbines, and then our system is a closed system, and the used and spent energy, spent prime, let's say, given back to the injection gas by means of some other of deep gas. In next slide, you know, there are mainly two types of energy systems converting the geothermal energy to electricity, power generation. These are called as flash system and binary cycle systems. Flash system is a typical, you know, thermal systems we know from the other, you know, coal and gas. Geothermal fluid, mainly coming from the earth, is led to the separators, and into separators we are separating the brine and the steam. And steam, we are taking the steam to the turbine, and it turns the turbine and generates electricity, and the again used and spent brine collected in the plant, and then this collection sent back to the injection to the ground, underground again, by using injection wells. This is a closed system, and it turns around, and so heated water again coming from the earth, we use it again, and then we send it back. So this is a closed loop, and then we generate our electricity by this way. The other binary cycle system, this is the systems we use mainly the geothermal resources, not enough. I mean, temperature may be low. It may not produce enough the steam to turn to rotate the generator steam turbine. So that's why we use another motive fluid. This is a low boiling temperature. So these geothermal fluid heats the motive fluid, and then this motive fluid rotates the turbine, and then we get the generation of the electricity. And this is again another closed loop system, and without any direct contact, we get the geothermal resources from the underground, and then we get some heat source, and we transfer this heat source to motive fluid, and then all the geothermal resources turn back to the underground, and this is again closed system, and then turns, and it's returning water, heat by again the geothermal system, underground geothermal system, and we get it back to above ground, and then this is a infinitive cycle. It continues. So the geothermal on the right side, so other than the electrical use, we use this geothermal fluid in many different kinds of applications. Some, we call them direct use, especially in Turkey or in the world, under 120 degrees Celsius. All the geothermal fluids can be used for other purposes, mainly in commercial residential building, heating and cooling, industrial processes, thermal and health tourism, agricultural applications, and recreation works. All this kind of information available at the right side. So geothermal fluid, we call it multi-purpose usage available. This is only energy in the world, multi-usage, potential available. So we can use for many purposes. In the next slide, I like to share some information about the installed capacity of the world in the geothermal. So if you look at the picture, this slide, you can see at the end of 2020, the installed capacity in the world reached to 14 megawatts. So this is a huge considering the geothermal capacity in the world. So at the right side of the figure, there's a tendency of Turkish development. I mean, this Turkish geothermal growth. So in a red line. So we become the fourth in the world as Turkey. So we reached the capacity 1,650 megawatt, almost this is capacity already reached in Turkey. So in the last 10 years, the growth of this capacity increase, you can see very rapidly, very extremely, increased capacity we had in Turkey. So the next page. In this page, let me give you some information about the Turkish energy sector. So as Turkey, we have had a rapid growth in terms of production of electricity. Installed capacity in Turkey, extremely increased in the last decade. So we reached 98,000 megawatt capacity. So when we look at this capacity, when we look at the right side, when we look at this figure, so geothermal capacity increased also too rapidly in the last 10 decades. So in 1984, we have 15 megawatt capacity only. So up to 2006, this 15 megawatt capacity already capped. But after 26, you can see from the figure. So every year we added 100, 200, or 300 megawatt each. So this was a world record. So this is nobody else can put such a big, capacities in a year. So this is the Turkish. We call this Turkish. Let's say Turkish performance. So it's a huge performance we had in the last 10 decades. So when again, when we look at this figure, we can see as Turkey, we achieved that more than 50% of the installed capacities belongs to renewable energy. I can say exactly. I can give you exact number. 52.8% of the installed capacity belongs to renewable energy in Turkey. So if you look at the also round table, so in that table you can see also each kind of energy has a distribution of each kind of energy, and hydro, wind, solar, and geothermal has a very remarkable capacities in Turkey, and we come to more than 50 megawatts of installed capacity in Turkey. In this page, I want to show you, as Turkey, last year in 2020, we produced 305,000 gigawatt hours energy. So this 3.1% of this energy coming from the geothermal. It's around 10,000 gigawatt hours. So then we also put the estimation, the hydro and solar and wind geothermal energies. As Turkey, we have almost more than 40% of share coming from the renewable energy. So this is also a progress. We achieved this progress in the last 10 years. So when also the current information about our geothermal share for this year, so end of July, so we can say we see that 3.3% of the produced energy in Turkey in this year at the end of the June is coming from the geothermal. So it's a good growth also geothermal in Turkey. So what can I say about the renewables? So when we look at the last 3 years, 90% of all the investments built in the last 3 years coming from the renewable energy. I mean, in Turkey, all the energy investments are returned to renewable energy. And also, when we look at the ongoing projects right now, so most of the projects is renewable, and I can say almost 100% of the projects related with the renewable. And then renewable projects take a big share in the next coming years. So I can say that up to until 2030, so 60% of the electricity produced in Turkey will be from only renewable energy. In this slide, this is a map showing the geothermal potential in Turkey. You can see the different kind of colors. So red colors belongs to hot temperature zones. The other blue is low temperature zones of geothermal capacity in Turkey. I can say that in Turkey, so, as I said, in the last 10 years, we have discovered big potential of geothermal energy capacity in Turkey. So we can say that as a situation, we can say that geothermal energy capacity in Turkey is reached to 3,500 megawatt for electricity production. Currently, installed capacity, constantly installed capacity of 1,650 megawatt. So another additional 2,000 megawatt capacity still exists in Turkey to implement and to build the projects. So in this map, considering this map, we can say that most of the rich areas, high potential areas located in the west part of the Turkey, but mid-Turkey, also east of the Turkey has a good potential in terms of the capacities. So in Turkey, the other point to say for Turkey is we explored potentials from the 40 degrees to almost 300 degrees. So the record temperature is 287 degrees Celsius in Turkey right now. But the official capacity declared by the General Directorate of Mineral Exploration and Research, this is the MTA in short, they declared Turkey has a capacity of 60,000 megawatt up to now as discovered. So upon this capacity, we can say that we can use some of this capacity for production of electricity, some of capacities for direct usage, means that household heating, cooling, thermal and health tourism, drying process, greenhouse heating, such as when we calculate all the potentials we use up to now, only 20,000 megawatt of this potential already used, and 40,000 megawatt potential still remaining for utilization. So on the bottom side, so for power generation currently we have, as I said, 1,650 megawatts installed capacities. We are heating 150,000 households. We have also 4 million tourist capacity, facilities available in Turkey. Also, we already 4,000 dekar area greenhouse heating available in Turkey. So lastly, I can say 1/3 of discovered capacity already in use in Turkey, but 2/3% of the capacity is still unused in Turkey. So in next coming years, we will see there will be good progress for the utilization of the geothermal and some good developments in geothermal in Turkey. So, which kind of encouragement we have in Turkey? In the last 10 years, there was a good feed-in tariff. So I would like to mention about the feed-in tariff mechanism for Turkey. So it was encouraged all this kind of progress for Turkey, but also there is a new feed-in tariff. This new feed-in tariff mechanism was announced in 30th of January this year and became effective from the 1st of July 2021. And it will be valid until end of 2025. So we have another feed-in tariff for geothermal, as I said, and this feed-in tariff will also encourage the new projects and the new implementation of the power plants of geothermal. Any power plant will achieving this COD, I mean that from the 1st of July of 2021 up to end of December, end of 2025, will benefit this feed-in tariff mechanism. And this feed-in tariff mechanism will be valid for 10 years. So 10 years, benefit will be available for any projects completed in this period. In addition of feed-in tariff mechanism, also there is another support for the localization, I mean local content, I mean local products. In case of any part of the power plant is produced locally, so we get another bonus. This bonus is 80 Turkish lira per megawatt hour. So we have 54 TL per megawatt hour. It's a base price for electricity. In total, it makes 62 Turkish lira per megawatt hour. So this is the total tariff we can get. And this tariff also is escalated 4 times in a year against the loss of the value against Turkish lira and also dollar. So we are the government has escalated this price 4 times in a year, and then nobody lose any value on this price. So we can keep the value of the price all the years. So permitting process, it's we have a good law, geothermal law. It was issued 2007, and according to this law, everything is there described. And the permit issues is very clear, and then we can step by step, we can easily, achieve every step, and after the step, we can go to the other step, and then we can complete in a certain period all the permits and with the support of the government and some other authorities. So first we get the exploration license, and we turn it to the operating license in a certain time. And then, so if you can see any project over there, so with this project, the major issue to get afterwards will be environmental impact assessment. So then we come into the process of this assessment report. So if we achieve a successful report, environmental report, in that case, the project way will be opened, and then we can easily continue on the project. And then in a certain time, we can say for Turkey, in 3 years or 4 years, we can come to a starting point of any project, and we can start the building of the project in 3 years. This is roughly considering also my less time left, so I can try to speed up. So there's a good law, and all the regulation and legislation is very clear in Turkey. So if you have a good potential in your license area, so, and also if there's no any environmental problem or any bottleneck or something like that, so you can easily achieve and overcome the issues, and then in 13 times, 3 years, I can say, you can come to project time easily in Turkey. There is one more item. It's added new in Turkey, hybrid projects. So this is very good in case you have any power plant in Turkey or a power plant project. You can also support this project with a hybrid project. Hybrid project is mainly from the renewable. So there are some. Let's assume you have a 80, you have a project or a power plant capacity less than 50 megawatt. So you can easily add another 50 same size of plant capacity as a renewable adjacent to your power plant. So you can increase your capacity. You can also get the benefit of the renewable energy for any power plant you have. So this is a good. So there are some other steps for that in case for any project more than 50 megawatt, for any project bigger than 150 megawatts. So there are some rules, there are some provisions, so you can easily achieve those provisions, and then you can, in that case, you can add a supplementary or secondary, let's say, power plant, near to your existing power plant. This will be additional benefit, and then you can get this benefit using renewable energy. So this kind of new laws encouraging renewable investments in Turkey. And then in my last slides, as I mentioned, up to 2030, more than 60% of the produced energy will be from renewable in Turkey. So this will be a good success, and this success coming from this kind of laws and regulations. So as I mentioned before, the discovered potential for Turkey right now, 60,000 megawatt, and we can use 1/3 of this total capacity, and the other 2/3 of the capacity means that 40,000 megawatts still available. And what can we do with this available and discovered potential? We can, as I said, we can reach to 3,500 megawatt power plant. So we have right now 1,500 megawatt installed capacity, roughly, and another 2,000 megawatt we can add. So this is our potential. What can we do more? We can add 25,000 decar greenhouse. So this is another advantage, another potential in our land. Also, using this potential, we can reach to 5 million household heating. So this is good for us. And then with the laws and the encouragements and incentives already we have, we are going in this way, and in a short while, we will see these numbers very easily in Turkey. We will reach to these targets. So this what about the meaning of this energy? This amount of energy means that we can substitute almost 9 billion cubic meter gas with if we install necessary things, so we can easily substitute 9 billion cubic meter gas with this energy. So if we convert the value, I mean, if we with this amount of the gas, we can easily save almost $2 billion. So only this is the from the source side. So there are some indirect also benefits. So we can also
sorry, Professor Ali. Would we hurry up? We have 3 minutes over our official time.
Okay. So, sorry for it was something we lost at the beginning. So this was the last one, and my last wording will be: so we have a good potential. It's already discovered in Turkey. We will be able to use only one small amount of this discovered geothermal potential, and we have still a huge amount of the potential discovered in Turkey. So we will be in the next year. We will be, doing some business with this discovered potential. But this is the discovered potential in Turkey. Most of the potential we discovered at the west side of the Turkey, but at the middle and the east side of Turkey still remains some potentials undiscovered. So if we also add these potentials to the Turkish, geothermal capacity in the future, we will see it's a good opportunity for Turkey using the geothermal. So thank you very much for listening to me. Thank you.
Thank you, Professor Ali, for the very interesting presentation. I think there is no question, but I have one question for you. It is from me. Did you recommend geothermal energy as a main source of green, sustainable energy in the coming years?
Yes, sure. I mean, it's known as geothermal is known as renewable energy, and everybody believes geothermal is renewable. So there are two ways of geothermal. At the first page of my presentation, I mentioned there are two systems available. One of the systems is conventional system. There are some water and gas and steam is already stored underground, but also there are some other ways of underground energy. I mean, earth energy is not is stored, but there is no any already stored. I mean, in the rocks. So with conventional system, we can utilize this energy as we do in Turkey, but on the other side, in the world, there are some other systems, there are some other technologies developing. I mean, this to get the energy from the earth. It's a dry rock, technologies, and on the dry rock, there are huge amount of energy available. So this may be a solution for energy of the world. I mean, so and many countries, trying to develop some technologies and techniques to remove this energy from the earth. And one of the technology is, the heat pumps, and with the heat pumps, many households in many countries, heated by heat pumps. So maybe in the future, all the households houses will be heated by the heat pumps. So this is a closed system. There is no any environmental, problems. And huge potential. Only thing we are looking for is development of some technologies.
Okay, thank you again. Now we shall move to, thank you, Professor Ali, for your interesting presentation. And now it is a time for the second presentation. Professor Dr. Albert Baba.
Dear Dr. Safa.
Hello, how are you?
Thank you very
Professor Albert. Welcome. I want to make a small introduction about Professor Albert Baba. Professor Albert Baba holds a degree in geology and doctorates in the field of hydrogeology from Duzik Eylül University, Izmir. He has 25 years experience in hydrogeological and environmental geology problems in different parts of the world. Since 2010, he has been professor in Izmir Institute of Technology as a director of Geothermal Energy Research and Application Center. Now, it is a small presentation. Now, the title of his presentation is the importance of the geothermal resources and its innovative properties, a case study. Welcome, Professor Albert, and please go ahead.
Dear Dr. Safa, thank you very much for your introduction. First of all, I would like to thank to the organizing committee. This is important conference about the energy and energy security. Today, I'm going to focus a little bit about give information about the geothermal source and its innovation properties. Still, Dr. Ali mentioned about many points, but just I want to go to a quick review. As you know that most of the countries, this picture shows that the energy distribution of each country. As you see that this is countries, this is especially most of the countries used to fossil fuels. For example, the red one is oil, the blue, open blue is this one is a natural gas, and then the brown is the coal. This is the boundary between the renewable energy and fossil fuels. As you see that most of the European countries now focus about renewable energy. It is nice to see, now we can see in the geothermal in the different countries, like a Turkey, like an Italy, like a New Zealand. And then we know that the 80% of energy comes from fossil fuels, but renewable energy is going to be increased, especially modern renewable energy. This is about 11.2, and this consists of again, the biomass, solar, geothermal heat, hydropowers. And then when we look at the Turkey, you know that Turkey is a big country. The emerging economy is like, you know, $762 billion GDP. But sustainable energy finance facility in Turkey are mainly financed by international finance institution programs. At that time, the energy is very critical in Turkey because Turkey is a major energy importer. More than 70% of the energy come from the other countries like Russia and Iran. And then therefore we have to, at that time we pay so much money, we spend so much money for our energy import. For example, in 2019, Turkey spent like 41 billion US dollar for energy import. And then if you look at the geothermal capacity, you know that the geothermal is increased every country, but in Turkey, you know, is the exponential, you know, exponential is increasing. This is installed geothermal power capacity grew by 2019, like this is 5% in the world. At that time, you see that the Turkey, Indonesia, Kenya, Costa Rica, but if you figure, you see that the Turkey is like they include about 32% of their energy come from the, you know, geothermal when we compare the world. You know that if you look at the top 10 countries, according to 2020 data, As you see that United States are third, Indonesia, Philippines, but Turkey is quite good because now is a fourth in the world class. And then we believe that this affected the economy of the country and then affected the positive for climate change. And then this is just overview of the energy system by sectors in Turkey. Just the data from 18 and 19. As you see that this is production in Turkey. If you see that the production we have coal, but other Turkish energies depend on the renewable energy. For example, this geothermal, hydro, and then biomass, and other one. But you see that most of them is consist of the fossil fuels. But we can use this type of the energy for the industry, residence, service, transport, every part of the system. And then if you look at the Dr. Ali also mentioned about this one. You see that the capacity of the installed capacity of Turkey now is the energy is reached 98.2 gigawatt, but all the results show that renewable energy also going to increase in the countries. For example, look at in here after the 2009, and you see how can the geothermal go into the system, and then also solar and then wind power in the system. And then if you look at the geothermal, you see that we are very happy because we have big potential. You see that some data, this is data from 1982, 84 to 2020, as you see how the Turkish geothermal electricity, that come from the geothermal sectors. This is the exponential increase, and then this is the, that is very good. This is a good example for the world. But also you can see that the other energy, renewable energy increased in the Turkey industry. Why the geothermal very important in this country? Because Turkey is located on an active tectonic zones. You see that in here, we have a Eurasian plate, we have an Arabic plate, and then we have a compression stress, and then we have also the Western Anatolian plate, we call that in here. This is extension zones. Along this extension zone, we can see that the big fault system in this region. And then the meaning that we have, if you have a fault system, if you have an active system, this is directly affected your source. And then if you look at the detail about the Turkey, this is the map of Turkey. And then you see that in here, this line is show about the major fault. As you see that, for example, this is the big North Anatolian fault. This is other one is the South Anatolian fault, and this is extension zone. And then also you can see in the Turkey, we have like a volcanic and magmatic rocks. The meaning that this is the source of the system, the heat source of the system. If you look at these graphs, you see that most of part of the system, that we have good source for the heat. And then also the red dots is show about the spring and geothermal. If you look at this graph, you see that all part of the country, they have a fluid, they have a geothermal source. For example, in here, you see that the southern part, we have many wells in here. And then also western part, we have many wells. But in this area, still, they need some research. And then if you look at the detail about the geothermal source, that the wells, for example, in Western Anatolia, in this part, we have like more than 1,000 wells. This is the reinjection well, production wells, that we can use for most of these wells for the power generation, but also we can use for the direct use application. And then in here, we have some wells. This is for the petroleum, still this is abundant well, but we believe that in near future, Turkish industry also going to focus about the geothermal energy in this area. The depth of the well is range from 1,270 to 3,960 meters in here. And then also the surface temperature is range like from 40 to 130 degrees in this region. And then if you are going to western part, that generally the temperature is range from 20 to 292 degrees in this region. And then this is show that the geothermal map, the heat source of the region. If you look at this map, you see that most of the heat source, the hot point can be seen in the western part, but also we can see in the center and then eastern part of the Turkey. But it is interesting now, the highest temperature was measured in here. This is the Niğdeköy, Çiftköy, Bozköy region. The temperature reached about 295 degrees. Also the other one, we can measure it in the Alaşehir Basin in Gedizgraben, 287 degrees. And also the Denizli, the Kızıldere region is in here 242 degrees, but also in Germencik. But also you see that also in the central Anatolia, we have a 183 degrees. But in here, we have an geothermal system. The meaning that we have not fluid, but we have a hot source. The meaning that it is possible you can use this one for also the energy. And then if you look at the power generation, at that time, Turkish have 60 power generation. And then most of them is located in the western part of Turkey. And then also we have combined system in the power generation. For example, the Zorlu groups, they had Kızıldere region, they heated the houses in here. They used to for power generation, but also they heated like a 5,000 houses in this region. And then also you see that the other, like a Beno Holding, the other one, they use for some greenhouses heating. The meaning that they have a cascade system in this region. Like the other one, like a Sanko, they knew in the district region, like the other one, you see that they use for the greenhouse sectors. Dr. Ali mentioned that we have a different type of the turbine, but in generally in the Turkey, we can see all this type of the high tech in the Turkey. And then if we generally make a review, as you see that in Turkey now we have like a 63 city have a different geothermal sources. And then we have really good some geothermal fields. This is approximately like a 346, and then the temperature is above the 20 and more. But generally we have more than, that 1,000 source in Turkey. And then we can see all this part of the country. And then if you look at the Turkey, you see that this is the Turkish map. All of them, you see that some pictures from different countries, as you see that all the pictures, that show that we have a geothermal point, geothermal ruins. For example, in the Western Anatolia, we have a Roman time structure, but they used by the geothermal at the time. We have also very nice, like a Pamukkale region. This is like a scaling problem, but this is very nice view for the tourism at the time. Dear my colleagues, if you are going to direct use application, if you know that in the world, direct use application is going to be increased day by day, especially if you want to improve the rural region, you have to focus about the direct use application. At that time, most of the countries in the world, they use for the ground source heat pumps, like a Sweden, Finland, they start to use ground source heat pump. And then in the world now, about 60% they consist of ground source, but also we have like 80% is bathing and swimming, about 60% come from the space heating, just 3.5% greenhouses and open ground heating, and then also 1.6 is the other industry. We are happy in Turkey because if you look at the direct use world leaders groups with heat pumps, Turkey located in the 4th in the world. But without heat pump, now we are the 2nd after the China. In the energy sector, power generation, we are 4th, but also in the direct use, we are in the 2nd. As you know that if you have under the 100 degrees, it is possible you can use the geothermal for industry drying, food processing, greenhouse application, fish farming, heating and cooling, that geothermal heat pumps, every application. And then also is a nice, at that time, you see that this is used the geothermal for the district heating. And then, for example, this is some sample about related to time. As you see that in here in Turkey, as you see that in 2000, people used more, the other, bioenergies, the other fossil energies. But now you see that when we look at the time, you see that also the geothermal issues of direct use in the Turkey is increased. And then as this is the graphs about especially the European countries, and then also the countries for the part of the world. You see that, for example, Norway, they use for the hydropower, and especially they use the renewable energy, but you see that these countries use more renewable energy. But if also in the Turkey, we have, it is nice, we say that we can use for the direct use about like a 50% for the renewable energy. And then if you look at check the situation of the Turkey, the total direct use application capacity at the time, 3,500 9 megawatt thermal. And then as you see that we can use in the different sectors. For example, in Turkey now we use for the greenhouses, we use the thermal facility, this is like a 12%, and we use also for the spa and thermal hotels, and then resistant heating about the 32%, and also food drying. And then you see that this is the some cities, some part of the cities hit by the geothermal. And the first geothermal district heating system was implemented in Balçova region in the western part of Turkey in İzmir city, 1996. At that time, about 40,000 houses have heated by the geothermal in here, but also we can see in the different part of the Turkey. And then the first geothermal space heating application in Turkey was done in the Park Hotel in Gönen region is in 1964. And then if you look at the tourism, you see that if you are going to every part of Turkey, you know, this is a number of facility. We have some hotels, but this heated by the geothermal. You see, and then also Turkish government have a good strategy about the thermal tourism. And then now in the Turkey, they separated by the groups, by the city. And then, for example, Central Anatolia thermal region, and then Frigya thermal region, like this part. And then also Southeastern region, this is like a Çanakkale region, and also Southeastern region thermal, like a Denizli, İzmir, and Manisa region. This is very critical also for the thermal tourism. And then greenhouse application, we can see every part of the Turkey, but it is nice to say at that time that the biggest, one of the biggest greenhouses located in the Dikili region, but also in the near future, we can see that in the world biggest greenhouses in this region, because at the time, Turkish total, you know, that they like, you know, all the total greenhouse area is about 3.4 is come from the geothermal. You see that this is the geothermal application in this part of the region. For example, Karali in here, the other region in here, Kozaklı, you know, we have different parts of the Turkey green application. But drying industry is very important. At that time, Turkey is currently in the 4th place in the world in the fresh fruit and vegetable. But it is interesting, for example, if you just look at the 2015 data, we produced about like a 50,000, you know, 50 million tons of the fruit, but you can imagine about 30% of this is discard. This is not acceptable. This has affected the economy. This has affected the life. But now, if you are going to dry this industry, you can, you know, you earn money. You minimize your, you know, the vast of the this kind of the fruit. And then this is some sample about agriculture drying application in Turkey for a peach, date, watermelon, pear. You see that this is some sample from Turkey for the drying industry. But you see that all the geothermal system have a different characteristic. I'm not going to so much detail in here, but all these later tectonic, and then all of them is controlled by some magmatic and volcanism. And then also this region, they have a different chemical. You know that you see that this is some numbers in here. Each numbers is, you know, they focus about the geothermal chemistry, fluid chemistry. For example, in this part is the measure ion. This is like a sodium. The green one, the red, pink one is like chloride. This sodium chloride. You see that if you are coming in this blue weekend, this is like, you see that calcium bicarbonate in the some system. If you have this, you know, each chemistry, they produce some different mineral. This some maybe the valuable mineral, maybe the hazardous mineral. You know, this is very critical. And then in some of our geothermal field, they have a carbon dioxide. And then this carbon dioxide, and then, you know, that is still is a problem, but we believe that this can be used in the industry. I will show you some sample. Okay, you see that if you are related to energy relation carbon dioxide incentive in the International Energy Agency members country Turkey, you see that still this is the, you know, compare the GTP carbon dioxide values, the country, Turkey located in here, like centers. And then if you are compared the per capita, you see that the Turkish is quite, you know, that when we compare the other countries, we are is good. And then, but we know that most of the carbon dioxide come from the different sectors, and then most of them come from the fossil fuels. Everybody mentioned about this one. And then also, you know, that how the carbon dioxide, the oil and natural gas, you know, they produce carbon dioxide and then affected our climate change of the system. And then, as many countries now wanted to reduce the carbon dioxide, if you look at the Turkey, for example, this is the Greece And then the other, you know, that Italy, Spain, but this is in Turkey, the red one. Okay, still we are, okay, we want to try to reduce, but I hope that in near future, Turkey's, because they used to renewable energy more, and then we are going to decrease the fossil fuels. And then also our geothermal field, they have some carbon dioxide values. Some of them is quite high when compared to other fields. But at that time, Turkish industry, they used to carbon dioxide for the coke, for the drinking. For example, some companies, for example, this is for Kızıldere region, Zorlu Group's area, as you see that they produce the carbon dioxide for liquid. And then this is good sample for the system. And then you know that the fire at that time, very big problem in the world. And then we believe that, you know, that this area is the forest region. It is possible you can capture this carbon dioxide. It is possible you can build a big tank on top of the mountain in this forest region, and then you can use the carbon dioxide for forest. This is fires. This is very important. We believe that this can, you know, that we should capture carbon dioxide. We use the carbon dioxide for the fire. We help to minimize this kind of the disasters. And then also we can capture the carbon dioxide. We can, this is a good sample, was on our university. You know, that we used to carbon dioxide and then we inject it to the system, and then we can minimize the scaling problem in the system. You know that the scaling is one of the big problem in the world. And then some geothermal fluid, they include like some mineral, like a boron. You see that the concentration very high, but it's possible you can extract this boron and use for the industry. And then, for example, this is one of the good sample in here. As you see that this is field, this is agriculture field, but we use this geothermal fluid because the geothermal fluid, they have minerals. This mineral is very valuable for the agriculture. You see that we can irrigate the tomatoes. This year, we produce many tomatoes. We use the geothermal fluid, and then we gain, and then we also dry these tomatoes. This is one of the sample about, good sample about Turkey. And then also some mineral like a lithium. It is possible you can extract lithium, the other, you know, element like manganese, zinc, copper, maybe gold. You know that. Therefore, we have to think about all the geothermal fluid. We have to analyze the chemistry, and then we understand this one. I believe that many countries, many people now working about this one. I believe that some pilot system, also in Turkey, we have a pilot system about lithium now. And then, dear my colleagues, we have some other application. You know that, for example, copper, you can use geothermal, produce copper sulfate. And then also you have a cheese, you have best cheese, you can produce whey materials. And then if you are summarized, yes, the geothermal is expansion all the countries, especially in Turkey. Turkish country government is support the system. As mentioned before, Mr. Ali, we have some regulations. Still, we have some gap, but we want to, I hope that in the future we are increased, but we have a big capacity. But enhanced geothermal system is very critical in the many countries, especially in Turkey. But we say that our Turkish capacity about the 60,000 megawatt thermal, but in believe that in the enhanced geothermal system, we increase also 200,000 megawatt electricity come from the enhanced geothermal system. And then we have to, the meaning that we have to think about all the perspectives of the geothermal system. Thank you very much for your time.
Thank you, Professor Albert. I have one question from Fatih Yilmaz. He says, thank you for your nice presentation. His question is, could you give brief information about the gases emitted from geothermal power plants? Where and how can it be used?
Thank you very much. First, you know that geothermal sectors, they have different gases, like a carbon dioxide gases, like a methane gases, hydrogen sulfurs. You know that we know that carbon dioxide. I showed some sample. It is possible you can capture the carbon dioxide, because still in Turkey we have a good example about this one. We can use for the drinking coke, because all the coke, they consist of the gases that come from carbon dioxide. And then also we have used to, you know, that we capture the carbon dioxide in the system, you know, in the chimneys of the system, and then we inject it in the fluid, and then you are minimize the scaling. This is the second. And then also it is possible to capture the carbon dioxide. You can for the fires, you know, that this is the sample. Hydrogen sulfide, and then also possible, you can capture the carbon dioxide and hydrogen sulfide together. also it is possible you can inject to the system. And then, you know that we have the many techniques now, you know, increase in the world, you know, new techniques. But I want to show, I will send you to some document. But thank you very much. But I know that this gas is a problem, but you have to think we have to gain these gases for economical gain. And then at that time, we have a problem with hydrogen sulfur, but it is possible you can minimize hydrogen sulfur. Therefore, you have established, you know, that you have built some system for capture the system.
Thank you, Professor Albert, for the nice presentation. Then we move to the third presentation. Professor Arthur Wipper, Professor, he left the University of Technology. Professor Arthur studied physics and chemical engineering at the University of Amsterdam, and he completed his PhD in the field of metal physics at the same university in 1992. He started working on R&D in the field of crystalline silicon photovoltaics and coordinated large national and international projects. From 2007 until 2015, he was senior manager of the device architecture group at the former ECN, recently integrated in the TNO organization. The title of the presentation is Trends and the Future Aspects of PV Technology and its Application. I would like to welcome with Dr. Arthur, and please go ahead.
Thank you, Safa, for the nice introduction. And also I want to thank the organization for giving me the opportunity to present some new results and also the trends. Now, first of all, the agenda. Let's discuss, let's say, the potential of solar energy and energy scenario and the market development. And then looking at high efficiency at low cost, especially low cost is very important. And then ways to further improve the efficiency of PV. And then also looking at integration and sustainability, and then finalize with a summary. Of course, I think the reason for PV and all renewable energy sources, you've seen the latest report from the IPCC, where the global warming is emphasized in more detail. So especially for the last few years, then the temperature is increasing too fast. And here you can see the impact, especially for, let's say, when you have 4C global warming compared to the pre-industrial time. Yeah, it will be catastrophic for our world. So we should do something about it. And renewable energy is, of course, the way to go. And of course, I'm presenting solar. And when you look at the, let's say, the energy, the energy consumption, or let's say generation in 2015, it was already presented. Most of it is fossil fuels based, and a scenario from Lithuanian University and also the Energy Watch Group. They think that for 100% renewable, they expect worldwide that around 70% will be solar. Of course, it is a very progressive one, but when you look at other ones, then PV is, let's say, very important part in renewable energy generation. Now, looking at the annual production worldwide, then you can see from the last decade that there was, let's say, about more than sevenfold increase in annual production, and mainly it's in China. Looking at, let's say, the total PV capacity installed worldwide, it was in 2010, it was below 50, and now it's close to 1,000. So you're talking about an increase almost of factor 20, let's say, in somewhat more than 1 year. And when you look at the PV share in electricity demand in 2020, in Germany it was close to 10%, Netherlands close to 9%, European Union 6%, and Turkey close to that. So it's somewhat different than, let's say, the energy generation, and worldwide is close to 4%. And when you look at the total renewables, then PV was about 42% of the renewable electricity production. Also looking ahead, the next coming years, this is what they expect for annual installations. So last year it was around 140 gigawatt, and it should increase to, let's say, 350 or somewhat in between in 2025, and in 2030 according to the International Energy Agency, for a net zero pathway, it should be above 600 gigawatt. So indeed, another factor 5-6 increase, which is, to my opinion, feasible. Looking at the different technologies, PV consists of different technologies, and the main one is what we call crystalline silicon. Crystalline silicon exists of two parts, monocrystalline and multicrystalline. Mono is the high quality material, and multi, also called polo, is the lower quality, but very cheap. But since efficiency is becoming more and more important, and also to reduce the cost, efficiency is becoming more important, mono is the dominating atom one. Thin film is another technology, so it's also flat plate, but also flexible. It's only it's 5% of the market and can be used for all kinds of special applications. Now, looking at price, so very important, the learning curve. So we have the module price versus the cumulative production worldwide, and here from 2002 in 2006 up to now, and you can see a huge decrease in price for crystalline silicon. And looking at the learning rate, it's more than 30%. That means when you double the production, then the price will go down by 30%. And for thin film, it's more or less parallel, but then let's say at a lower cumulative production. And here is 20 cents per watt peak for a module price. Here I extended the plot a little bit. So let's say till let's say the late 70s, and there you can see that the price at that moment was $100 per watt peak. So compared to the 20 cents, it's almost for nothing nowadays, and still going down the prices. And yeah, it's caused different things, standardization, economy scale, but also efficiency improvement is very important to reduce the cost. Here you can see the levelized cost of electricity for PV over the last decade. It's in yellow, and now you can see that it's around 3.7 or yeah cent per kilowatt hour. So really lowest compared to oil, gas, or even nuclear. And when you look at a large power plant, it's a bit. It's in Saudi Arabia. There's a record low bit of where you have, let's say, $1 per kilowatt hour generation. So that's below €1 per kilowatt hour. So yeah, to my opinion, as far as I know, I've never seen these low numbers for electricity generation. Now, why is power density or cell efficiency very important? You can see a plot for a rooftop system in Germany. So the medium ones between 10 and 100 kilowatt. And here you can see the price, the relative price for, let's say, the module cost here in orange, and in blue, they're talking about the systems cost. So the framing, the cabling, the inverter, and so on, and so on, and so on. And indeed, let's say 2006, the main part was the module cost. And nowadays, the main part is the bus cost. So that's our area related, mostly area related cost. So therefore, when you increase the output of the module, then indeed you can reduce the levelized cost of electricity. And when you look at the module, you can see it even more. For the module material, so I mean the glass sheet and the encapsulation material, it's almost 60% of the cost, and the cell processing is only 12%. And here it's about, let's say, making the silicon wafer. So you can indeed afford much more processing costs for increasing the efficiency to reduce, in the end, the cost. Now, looking at the industrial solar cells that are nowadays, when you look at the newsletters, they call PERC cells, and in the past it was just standard cells. And the standard cells consist of, let's say, what you call an aluminum BSF cell. So here you can see a picture, a cross-section of the solar cell. So we have a P-type silicon wafer, so boron doped, and on top we diffuse a very thin layer with phosphorus, and here you have the voltage over the solar cell when light is falling on the solar cell and electricity is generated. So the voltage is over the PN junction. And of course, we have an anti-reflective coating to make the solar cell black, and we have all kinds of contacting. And at the rear, we have highly doped with a little bit aluminum, and that's preventing losses at the rear side. But this cell, here you can see it in black, has, let's say, maximum efficiency around 20%. So to keep on improving the efficiency, we had to go and make the next step, and that's what we call the PERC cell. So it's a passivated emitter, but also passivated rear cell. So the aluminum back contact, or let's say the back surface field, is replaced by a dielectric, so silicon nitride or aluminum oxide or silicon oxide layer. And then need local contact, there you have still the local BSFs, and then let's say an aluminum contact. And with this, you can increase the efficiency, you can maintain the increase year by year. And This is a plot for the quantum cells, and it's by Hanwha Q cells. And nowadays, the cell efficiencies for the PERC cell are approaching 24%. So it's really better surface preservation, so less losses at the rear surface, but also the light capture in the solar cell is better when you have a structure like this. And the module efficiencies are now above 21%, so the commercial modules. And what are the trends in the worldwide? Nowadays, the P-type materials doped by boron, but you can mitigate some, they have observed some degradation. You can mitigate that, but when you go towards gallium doping, you can reduce the degradation or at least easily mitigate it. And nowadays, most of the wafers are already gallium doped, and they expect in the next 10 years that all the wafers will be gallium doped with respect to the P-type wafers. Another way is, of course, reducing the silver consumption, going towards lead-free. And still the interconnection, the soldering contains lead, but also the metallization context, they have very low concentration of lead. And we want to go to larger wafers. Nowadays, the wafers are around 6 inches, and we want to go up to 210 millimeters. And then, because currents are very, very high, they go to half cells. High throughput, also important. And another thing is we can make the solar cells not, let's say, a full blanket of metal at the rear side. We can also use an open metallization, and then we can generate light from both sides of the solar cell. So we make them bifacial, and depending on the application and depending on the albedo, you can increase the power output by 10 to 20%. And of course, when you have not only metal, an open metal pattern at the rear side, then you reduce the metal consumption as well. And multi-bus bar, multi-wire interconnection instead of, let's say, the really visible taps, and of course going to all black modules. Here you can see, let's say, the different cell size or wafer size. Here you can see the standard 6 inch, and now you can go to, let's say the 210. Actually, when it's from the international roadmap for PV, this was already outdated because most of the wafers are already at, let's say, 166 millimeters. So this is already a majority. Now, when you look at the PERC cell, the rear side is still limiting, and also especially at the contacts and also at the front side, they are limiting. And then, yeah, looking at semiconductor world, so they use also tunnel oxide contact with polysilicon, and it really reduces the losses at one of the sides to, let's say, almost zero. And the layers consist of, let's say, tunnel oxide passivating layer here at the rear side, and then we have a polycrystalline layer, highly doped, and that's what we call TOPCon, so tunnel oxide passivating contacts. Fraunhofer ISE introduced that concept, and ISFH, also in Germany, they call it POLO, but in principle it's the same concept. And these layers, especially now the tunnel oxide, can be applied by thermal oxide or by a chemical process, and the polysilicon layers is applied by LPCVD, and then anneal it, and then you can diffuse by highly doping, or indeed in the LPCVD directly in situ doping it, or PCVD with immediate doping. So this is probably the cheaper in the future. What about the results? Already mentioned, the aluminum BSF cell is limited by 20%, the PERC cells approaching 24%, and with the passivating contacts, TOPCon, but also other concepts, you can reach 26%. You can already see in the lab that 26% has been obtained already with the different cell concepts, also with, let's say, completely back contacted cells. So then you have, let's say, no metal on the front side and every junction and all the metallization at the rear side. Then above 26% was obtained by, let's say, yeah, with those TOPCon structures or polo structures. And you can also see for P-type and N-type solar cells, you can obtain these kind of efficiencies. Of course, it's nice in the lab, but yeah, the next step is industrialization. And that means that we apply kind of screen printing technology, very cheap. And we want to reduce the thickness of the polyether because it will result in parasitic absorption. And the surface of the solar cells is already textured, so a rough one. It has to do with the light coupling. You want to absorb as much light as possible. And the interfaces are then very important, and you want to reduce all the recombination losses there. And here I show some recombination numbers. The lower, the better. And when it's, let's say, 1 or even lower, then it's excellent, and then it's very, very good. So on let's say, on the bare wafers, we obtained already very good preservation. So hardly any recombination losses, but still at the contacts, especially because the contacts are penetrating a little bit in the solar cell, you can still have some additional losses. So what you have to do is to play with the diffusion that, let's say, just beyond the oxide, you have still some dopant layers. So what we call a dopant tail. So they're lightly doped. And when you have a tail like that, you can even further reduce the recombination losses at the contact. And with a new paste, you can even go down by a factor 2, 3, even more. And when it's 50 femtom, okay, you can say it's much larger than this one, but since the metallization coverage is only a few percent, so then your losses are in the same, so ideal. And that's for the N-type polysilicon layer. And when you have, let's say, P-type doped, so boron doped, then yeah, we still have to make some progress, but it's already quite good. And here you can see what's already obtained in industry, recent results. 25% solar cells have been obtained, and already 23.5 with these solar cells on module level by Jinko. You can see very recent data. And the next step is going to make them, the polylayers, even more transparent, and that's what we can do is alloying with a little bit of oxygen. And then with this plot you can see, especially here in red, and that the absorption losses at the higher wavelength are lower in this layer than compared to silicon or, let's say, the poly layers. So when you use these kind of layers at the rear side, then you can even increase the current output of the solar cell. Now you can see the open circuit voltage 740 is excellent passivation, so hardly no recombination losses at these layers, and the cell efficiency we obtained was close to 20%. So this was at Delft with the Delft colleagues. Another thing is what you can play with the front surface. That's add a silicon oxide nano layer, nano texture, so for even better light coupling. So silicon oxide on top of the silicon nitride, and then we obtained 23% for a full back contact of solar cell. Then, so all the metallization at the rear in the cell looks completely black. Another way of passivating the contacts is what we use, what we call heterojunction solar cells. And then instead of the poly layers, we use amorphous silicon. And so then we first have an intrinsic amorphous layer on top of the what we call the absorber, or the wafer material. And on top of that, you have the dope layers for the junction. And the layers are very thin, 5 to 10 nanometer, or preferably below 10 nanometers. But still, because of the amorphous silicon, you have some parasitic absorption. The disadvantage of the process, sometimes called an advantage, it's a low temperature process, so below 200 degrees, and it's PCVD. And the disadvantage is because you need special silver paste for contacting, and that means a high consumption. So especially because of the silver, this concept is still a little bit more expensive. But looking at the efficiencies obtained, the best solar cell ever made by Kaneka is 26.7%. So that's really the world record. And we look at the theoretical maximum is above 29%. So we're already close to that. And Meyer Burger is starting manufacturing this type of solar cells, and they want to extend up to 7 gigawatt in 2027. But also other companies like Enel are starting a production with this type of solar cells, or extending it also plans to 5 gigawatts, so in Europe. And Turkey is very active in installing production capacity for PV as well. Now, of course, as already mentioned, the silicon already absorbs some material. So when you change that to silicon oxide, then you improve the transparency. But you still need to optimize the conductivity as well. And when you add oxide, then you reduce the conductivity. So you need to optimize everything. Now here we have solar cell, still the heterojunction solar cells, but here we introduced a nanocrystalline silicon oxide layer, and on top of that, a very thin nanocrystalline intrinsic layer. And when you do that at the front side silicon oxide layer, so for example with this solar cell, and you measure the quantum efficiency dependent on the wavelength, especially at the shorter wavelength, you're looking at the quality of the front side. So really this top layers. And here you can see when you use the nanocrystalline silicon oxide layer, you can see that the response of the solar cell is better than when you use only amorphous silicon. And with this structure, with an you can see this an N-type silicon, and you have the P-type junction at the rear side, so rear junction, rear emitter cell, we obtained an efficiency close to 22.5%. The next step, the ultimate thing, to my opinion, is go to dopant-free. When you add dopant to materials, you always have a parasitic absorption. And metal oxide layers is one of the opportunities or challenges to make the junction. And here you can see the standard heterojunction soda cell, in this case with the p-type layer on top. And when you replace this p-type layer by molybdenum oxide, then you have a more transparent layer. And indeed, here you can see the increase with respect to the reference silicon heterojunction. So when you have so here make amorphous layers thinner and thinner, but with molybdenum oxide on top of that, you can really see an increase in response on the front side. And here's the same way we have, let's say, different layers for thicknesses for molybdenum oxide with a 6 nanometer amorphous silicon. So it can really improve the front side output. And in the lab, it was confirmed by ISF Caltech, so calibration lab, 23.5% was obtained by EPFL. But when you go to thinner layer, they still observe some problems with stability and all kinds of things. So much research needs to be done. And of course, this lab cell, and yeah, the front contacts are applied by screen printing, but very small cells. The next step, of course, going to larger wafers and then use the dopant-free passivating contacts. And even here, when you have, let's say, the amorphous layer on the front side, we replace the amorphous silicon by aluminum oxide. The rear side is somewhat different. We use polysilicon instead of amorphous silicon, but focus on the front side. And you have, let's say, the standard heterojunction, and here you can really see the improvement at the front side by replacing, let's say, all amorphous layer by metal oxide layers. And we obtained, let's say, already 80% with this large area cells. And looking at the limiting factor is the transparent conductive oxide on the front side. These layers are very, very thin, so you need a lateral conductivity, and therefore we apply transparent conductive oxide, which of course results in some reduction as well. But still, the potential is to obtain ultimate PV efficiencies. Now, the next step is, of course, that we should increase the efficiency towards 30%, maybe even in future 40%. And then you cannot use the single junction solar cells anymore. So what we can do then is make stacks of solar cells, what we call a tandem. And first of all, we start with a hybrid tandem with perovskite on a top cell and a silicon bottom cell. And the top cell absorbs, let's say, the UV part and a bit of the green, and the red part is absorbed by the bottom cell. And with this, you have a better utilization of the solar spectrum, because here you can extract more energy from the UV than silicon does. And it's still based on a mature technology. And the perovskite is really emerging technology, and they already obtained 25.5% efficiency with the perovskite single junction solar cell. And Oxford PV, and they have the world record with 29.5 efficiency for a tandem, small area. Now, how does perovskite look like? It's an ABX3 structure. The A is methylammonium or formadium or cesium. The B is lead, and the X is chloride, bromide, or iodide. And this is, and you can make this. It's a thin film solar cell. Here you can see the structure. You can make them flexible, and we even have a roll-to-roll system for making flexible perovskite solar cells in a lab condition, so not full production yet. Now, looking at the question always for the perovskite is, are they stable? Yes, they are. We already not as good as the silicon. A lot of research needs to be done, but you have already some key good results. So, for example, they passed, let's say, 1,000 hour one sun over time, but also all kinds of thermal cycling between 40 and 85 degrees. Damp heat, so really high relative humidity and high temperature, that's also survived. But yeah, we have, let's say, a glass encapsulation, even 3 layers. And one of the things is crucial for that is the ALD layer that was used for packaging. And also for the flexible bifacial perovskite, they passed, let's say, the single IEC test, not completely the thermal cycle, but the damp heat, it does. So huge progress has been made with those solar cells. Now the next step is, okay, what kind of tandem cell would you like to have? There are different types, 2-terminal, 3-terminal, or 4-terminal. Now the easy one is the 4-terminal. So then you have here separate contacts for the top cell and for the bottom cell, and the cells work independently of each other. And when you have 2-terminal, then of course the current through the cells should be the same. So you need to have current matching. And then it of course depends on the band gap. And here you can see the maximum for, let's say, the 2 terminal, for the 4 terminal is more or less independent. Now some world records results for the 2 terminal and the 4 terminal, and the red one is for the 2 terminal for crystalline silicon perovskite, and the black one, so 29.5, and the black one is for the 4 terminal. And you can see that within TNO, IMEC, Soliance, we obtained that kind of records. And also some thin films are result there. And when you look at the thin film, so 20% CIGS with the top cell, 80% perovskite, you obtain 27%. And when you do that with crystalline silicon, here we have a larger area cell with close to 90%. With a standard PERC cell, you can gain almost 6%. With a back contacted cell, heterojunction cell, you can gain 5%. And with a completely back contacted cell, we have a 25% back contacted cell, and then you can still gain close to 4%. Also, we made a large module out of it. Then, of course, the efficiency is still but low. For the perovskite is 14%, but then for the 10x10 cell, it was 21 PERC cell, close to 20, and then we obtained 22% for the tandem structure. But we have to do next steps, and we want to, much more PV is needed for the energy transition. That means you cannot hide it anymore. So integration and customized products are very important. So color, shape, and high power output. And of course, we have to go from renewable to sustainable. So earth-dependent and low-cost materials, lead-free, but also fluor-free in the material. Recycling, here you can already see some examples that we have, let's say, kind of release encapsulation, that you can fully recycle the cells, low carbon footprint, improved energy payback time or energy return of investment, etc., etc. Now here you can see all kinds of integrated products, what we can do with PV. So this was the Lightyear one car, where we have a curved module using TNO technology, back contacted, or apply it with, combine it with agriculture, or vertical bifacial PV modules, where we can still use the land in between, floating PV, integrated in roads, noise barriers, integrated in house, or just in the field, but then integrated way, or in facades where we use some print technology for to simulate the brick structure. And the technology behind it, we can make solar cells already mentioned. So this is the front cell of a cell. Here's the back side. You can see bare facial or back contact, where you can make all kinds of shapes or even different colors. And here also when we use printed circuit board technology for interconnection, and with this type of solar cells we can make a dome just to demonstrate all shapes are possible, and here also lightweight and curved. And the next step is of course making really customized product from let's say more or less standard products. So standard solar cells, we're working on a pilot line. So here we have, let's say, start with the back sheet and then we build up everything, and then in the end we can make, let's say, the final product, customized product, integrated product in the end. So in summary, efficiency is increasing with the aim to reduce the cost. Here you can see the famous plot you've seen already. And here you can see already the best results with tandems. So not with the perovskite, but actually this close to 30%, 36% is silicon bottom cell, but then with the 3,5 cells on it. So actually a triple junction. So it's already going towards 40%. And here you can see the different solar cells with the lab results. And here really commercialization. And of course, it should be an integrated product and it should be a sustainable product. So thank you for your attention. Of course, thanks to all my TNO and TU Delft colleagues.
Thank you, Professor Arthur, for this nice presentation. And I have some questions, if you can answer it. I will start by the last one. What will be the final size of the wafers? Is it 182 millimeter or 210 millimeter?
The general opinion at the moment is that the maximum size will be 210 millimeter. So, but okay, that will be, let's say, the future. But most manufacturers are already thinking about going to 180 plus in the near future. So they're talking about, let's say, transferring already now. So 166 is the current standard and will be transferred soon to 180 plus, and then the next step will be 210.
Okay, thank you. Another question.
But of course, in the module, the cells will be cut because otherwise the current will be too high. So be aware of that.
Okay, thank you. Another question. What will be the next generation of carbon silicon solar cell type after PERC cells in the industrial production?
So at the moment, indeed, PERC cells are the dominating one, and the next step will be indeed that, let's say, the TOPCon device, the TOPCon structure will be the next one, and it could be N-type. Some people say that it will be N-type, but to my opinion, I think that P-type, especially when you go to gallium doped, and the main industry is at this moment is working on P-type. I still expect that, let's say, for the near future, P-type TOPCon will be the first step, and then maybe because N-type has some advantages with respect to material quality, then let's say maybe for the ultimate efficiencies, let's say going to 26 plus maybe, then maybe N-type will be needed.
Okay, the final question is, how do you think Europe and Turkey will compete with Far East countries in manufacturing PV components?
Yeah, it's a very good question. Indeed, in Europe, we are thinking about it, and there are many discussions between the different institutes and also the different companies. I don't think that Europe and Turkey should compete with, let's say, the conventional silicon solar cells, but they should make the next step. So indeed, the highest efficiencies, that could be, for example, heterojunctions, maybe also TOPCon, but I think the heterojunctions and also the tandems, that will be the next step. And of course, the integrated products. Especially when you have, Europe is densely populated. So with respect to area, there is not much room, so you have to compete with other things. And then indeed, the integrated products, I think that they will be made locally. So besides the very good initiatives at the moment from Meyer-Burger, Enel, but also in Spain and also in Turkey, and also some special module manufacturers in the Netherlands. So the special products and also the integrated products, which will be dominating in the future. Also, when you will not transport whole facades, but when you integrate PV in the facades, and then I think, Europe will regain the good position with respect to manufacturing. And also looking at the transportation costs, that they're becoming more and more important. So then maybe even for economic reasons, financial reasons, could also be better to produce locally. And of course, political reasons are obvious. You want to be more independent from, let's say, certain continents, which we learned nowadays more, even harder than, let's say, in the 70s with the oil crisis.
Thank you, Professor Arthur. Finally, I want to thank the invited speakers, Professor Ali Kinda, Professor Albert Papa, Professor Arthur Weber, for the very useful and nice presentation. Hoping to see you soon, inshallah, in a live conference. Thank you.
Thank you. Thank you. Bye-bye.
Bye-bye.
Hi all, hope you all are doing great. I welcome you all to the session number 13 of TÜBA World Conference on Energy, Science and Technology. Our first talk will be by Dr. Janan Ekar. She will be presenting comparative sustainability investigation of hydrogen production methods. Dr. Janan, you may start, please. We'll have 13 minutes for the presentation and another 2 or 3 minutes for Q&A session, please.
Okay, 30 minutes, right?
You are right.
All right, okay, thank you so much. Hello, dear professors, colleagues, and thank you so much for everybody listening. I am going to share my screen now. Can you please confirm that if you see the screen? You see my screen, right? I'm not sure if anybody sees my screen.
Dr. Ajar, we can see your screen.
Thank you for your confirmation. So I would like to start without further ado. Today I would like to talk about the sustainability investigation of hydrogen production methods. Here I will start with the problem definition, motivation, why are we talking about hydrogen, and why we call hydrogen as the future, the fuel of the future, some hydrogen production methods, and the sustainability criteria of efficiency, cost, social cost of carbon, global warming potential, acidification potential, at the technology maturity level, and the performance rankings and some short-term, medium-term, and long-term solutions for a transition to hydrogen economy. We know that our population is growing and our standards of living increasing. That inevitably increases our energy consumption, but there is a price with that. The price coming with that is the carbon dioxide emissions, and the carbon dioxide emissions, and also the extreme resource consumption that is bringing us to a point where if we want to remain the living standards that we have right now and bring at least the same standards for the future generations, we need cleaner, more sustainable energy systems. And that need was more urgent than ever that with the report that was released by IPCC 4 days ago. So we know that our fingerprint is undoubtedly there and we can fix it, and hydrogen could be a part of it. So this is what's bringing us, because overall what we see is there is a decrease in renewable hydrogen cost. In the last 10 years, the cost decreased by 80%. And we know there's a strategic importance because according to the Hydrogen Council, 70% of the country's GDPs are somehow linked to hydrogen. And with Hydrogen Council, which was formed in the beginning of 2017 with 13 members, now exceeding 90 members, we know that there's also a momentum in the industry which is growing. So what is hydrogen? We know it's the most abundant element in the world, in the universe actually. It has high energy per mass density. It is the first element, it's the simplest element, and it's the lightest element. There are so many advantages, but there are some challenges. One of them is hydrogen is not found in a free form in the nature. So it's not a source itself, it has to be produced. So the first challenge is actually the production of hydrogen, the extraction of it from resources. The energy transition requires moving away from fossil fuels to renewables. So we need to use renewable energies, and we need to use renewable resources such as water to extract hydrogen. And we know that overall, the hydrogen ratio in the fields increasing, and with that increase, the carbon footprint of the fields decreasing. So the fields become greener and greener with hydrogen. Why not 100% hydrogen for that matter? So the first challenge to tackle for this 100% hydrogen energy systems is the production. In this study, there are 16 hydrogen production methods that are compared based on 7 different sustainability criteria. So when we look into the efficiencies, we see that larger scale, more established systems such as electrolysis have high efficiency. There's also natural gas and coal-based hydrogen production methods with or without carbon capture, and they seem to have reasonably higher efficiencies. And when we look into the photonic-based hydrogen production methods, we see slightly lower efficiencies because one of the reasons is when evaluating the efficiency of solar-based hydrogen production methods, the input energy and input exergy is actually incoming solar irradiation. Therefore, we see these like low numbers with photonic-based methods. And when we look into the costs, again, a similar tendency that we see more established methods, more large-scale methods, or higher technology maturity levels, we see lower costs, but with more novel, more up-and-coming methods and more like smaller scale models, we see higher and higher costs, such as photoelectrochemical cells. Another thing is that it's not just the production cost of the hydrogen, but there is an environmental footprint with this hydrogen production methods. And with the environmental footprint, there's an external cost. So we could relate this to the social cost of carbon. The more emissions, the more pollution, there will be like more expensive because there will be associated risks to the environment and human health or the ecosystem's health. When we compare these methods, then we see the photonic hydrogen production techniques advantages because their social cost of carbon is quite low. Similarly, we can look into the global warming potential. Global warming potential is calculated based on the carbon dioxide equivalent emissions of all the methods that when we are producing that, but considering that such as grid electrolysis. In grid electrolysis, the electricity resource is also taken into account. The cost of this electricity and the emissions that is coming with the grid electricity is taken into account. So it's more like life cycle assessment in terms of the emissions. It's not just during the production method itself, but also where the resources are coming from. So when we look into that, we see the largest impact, which is not a surprise, coal gasification and steam methane reforming. But what we can see is actually with proper carbon capture methods, we could reduce these emissions significantly. But it's not, the environmental impact is not just the greenhouse gas emissions, although our immediate action has to be the greenhouse gas emissions, because as IPCC report stated as well, we have more or less 10 years, maybe even less than 10 years left to reach the 1.5 Celsius target of Paris Agreement. But there are other environmental impacts, such as the acidification potential, which is the amount of SO2 released to air and water resources and the ground, which acidifies the solid or the water, and it impacts the agriculture, it impacts our water resources. So this is also very important considering the sustainability of future generations. And when we look into that, the carbon capture doesn't really help the fossil fuel-based methods. So when we compare these two, overall, we see that although they're large scale, more efficient and cheaper, when we look into the environmental impacts, we have to make a little bit of a sacrifice and move towards the cleaner options. But how can we do that? One roadmap is actually look at the technology maturity level, because what we can do is we can start transitioning towards the hydrogen economy with the higher technology maturity levels, and then buy some time for the more up-and-coming innovative methods to gain momentum. So overall, I know this is a little bit of a crowded, I'm going to show in detail. There are 16 methods here, 7 criteria. But when we look into that, okay, this image is giving us one thing. We see 16 methods, 7 criteria. Each criteria, different methods have advantages and disadvantages. This image, there is a 0 to 10 ranking. 10 is the ideal case. Ideal case is not existing. It has 100% efficiency. It has 0 cost, 0 emissions. So in that case, and also like the 10, like technologically mature. So in that case, what we can say, the more like the options that are closer to the outer envelope, the more sustainable they are. But we don't see that much here because it is crowded. What we can do, we can look into the top 5. And in top 5, we see that most of them have the common point of having a high technology maturity level and cleaner, like less emissions. So the efficiency is coming next, but it looks like immediately the technology maturity level and emissions and also like the cost that are coming important. In the medium 5, we see that there is more variation. The medium 5, there is more variation. So some of them have cost advantage, some of them have emissions advantage, but we don't see one tendency. And in the lower 5, we see that definitely they don't have the emissions advantage and they have like high cost. That comes to our point where, okay, let's take a look into this and dig deeper a little bit. So what we can do is we can take an average of all these weights, and each method has a ranking between 0 and 10. The closer to 10, the more sustainable. And the first thing that we see is steam methane reforming with carbon capture. So that brings us the statement that it is a good first step. So while more novel, smaller scale hydrogen production methods become more and more technologically mature, we could kickstart the transition to hydrogen economy with large scale, more technologically mature and clean hydrogen production options. So then with this hydrogen, we could start decarbonizing the vehicles, industry, steel, aviation, and in the long term, this hydrogen could even be used in the distributed systems to build, in the built environment, and just in large-scale centralized energy systems. We need infrastructure, we need the people, and we need the market to be ready as well. We have to think about this. We have high-speed internet at our homes because there are fiber optic cables. So we need every player in this matrix to work together to kickstart the transition for hydrogen energy. So we need partnerships, we need engagement, we need to play in the international market. There are some challenges which are mostly like cost and the reliability. So in the short term, the cost minimization is a strategy, but in the longer term, the performance and durability. And there are many research and development focus from engineering point of view. I could start with the techno-economic analysis. Here are the resources, and this study is actually a continuation of the study that I conducted under the supervision of Professor Dr. Ibrahim Dinçer. So I would like to appreciate and acknowledge his supervision. And I would also like to thank the Turkish Academy of Sciences for awarding me with the Outstanding Young Scientist Award. And I would also like to thank all of you for listening to me. And I hope that I stayed within the time limits. Thank you.
Thank you, Dr. Jana. It was a very nice presentation. If you have any questions, please raise your hand, or you may type in the chat box also. till someone is typing. Dr. Janan, I have a question. As per the study, SMR with carbon capturing is the method right now, which is the most suitable. But carbon capturing is not easily achievable. Technically, it is very difficult. So have you taken that in account also?
For sure, because it is taken into account in actually for both technology maturity level and the cost items.
Oh, okay, great. So that's the best method right now.
Atmospheric carbon dioxide is very, very challenging to absorb because it's already in the atmosphere, which we need to do that too. But in the source, it is less challenging. So if we can just capture carbon dioxide before it escapes or it is absorbed or sent to the atmosphere, that would be the good first step, while electrolysis, renewable electrolysis, photoelectrochemical systems, and more like novel options gain momentum.
That's great. Thank you. Hope you are enjoying over there. Thanks for the amazing presentation.
Thank you so much for this session sharing, and I wish the best of luck to the presenters coming. Thanks.
Thank you. We move to our second presentation. It will be Hydrogen Refueling Station, State of the Art and Perspective by A. Kovash. You have 13 minutes to present, and then we'll have 2 or 3 minutes for Q&A session, please.
Hello, Ankita is speaking.
Yes, we can hear you loud and clear.
Did you propose me to give a presentation, or I missed it?
No, I did propose you.
Okay, because I saw my name as a third presenter, so I wasn't. I was just listening, Janan, and I wasn't prepared my presentation. But now I will share it. I'm sorry. Just a second.
No problem. Please take your time.
Mm-hmm. I think now it should work. It seems something went wrong. Can I send you my presentation so you can share it for me, please?
Sure, please share with Fateh, and he will share for us.
To Fatih, okay. it takes some time. I'm sorry for this. Why does it not working?
Do you see the green share sign?
Yes, I see, and it takes me to the system preferences.
Okay, maybe you have not allowed your system to share the screen. So you might have to allow that.
I click on desktop. Now I'm as a co-host, and when I open system preferences, it and I give him access. Okay, I sent to Akif my presentation.
Okay, let us figure out over here then.
Okay.
Please wait for a few minutes.
Okay. He's asking me for my preferences, but I turn on for everything, and it doesn't work.
Dear Dr. Koch, can you hear me?
Yes, I can hear you.
Please, can you share any of your screen, please? We want to request access to your screen. We will remotely control your screen to share your presentation.
How can I?
At the bottom of the screen, you will see the share screen button in the green one.
Yes, I see it.
You can click on it and share any of your screen, please, if you want.
Yes. But it is asking me for system preferences.
Yes. You need to allow the system before.
Yes, and I clicked on each item, but still it's nothing.
Dear Dr. Moderator, if it is suitable for you, maybe we can move on to the next presenter, and then you can present after you fix the problem, okay?
Okay, thank you very much.
Okay, thank you, Dr. Koch.
I'm sorry for this.
Thank you, Doctor. Okay, so let's move to the fourth presentation of this session. It will be, the topic is thermodynamic assessment of a power to methane system under real world scenario by AC Einsche. Are you there?
Yes, I am. Please? I am here and I am sharing my screen right now. Can you see my presentation right now?
Yes, we can, and we can hear you loud and clear, please.
Okay, it's perfect. Hello, everybody. I am Alper Canince. Well, today I am going to tell you about a thermodynamic assessment of the power to methane system under real-world scenario. Well, this is an ongoing project, and it is performed in collaboration with 9 Eylül University, Gebze Technical University, and Garanti Koza Energy. So this is my outline. I will start with introduction to power to methane, and then I will give you study objectives, system description, a mathematical model developed for this system. And finally, I will present results and discussion and conclusions. Actually, power to methane systems is a promising technology to produce methane, synthetic methane from surplus electricity. That's why it provides flexibility to the system and compensate renewable energy sources fluctuation. And also it allows converting power into methane. That means actually that reduces CO2 emissions. Another important advantage of power to methane systems, it uses existing infrastructure. So it is important actually. So actually there are 4 key components in the power to methane concept. The first one is renewable power. And the second one, water electrolyzer, CO2 capture and separation unit, another one, and finally fuel upgrading section where methane produces. So after methane is produced, we can use in many applications like mobility, industry, power generation. So what are our objectives in this study? Actually, firstly, we did basic thermal integration, and then we developed a mathematical model for subcomponents that are electrolyzer, reactor, and solar PV module. And then we investigate the effect of operating window of reactor, methanation reactor actually on the system performance, and finally we present system efficiency under different working conditions. So this is the system we consider. Here actually you see the solar PV grid, CO2 capture and separation unit, electrolyzer, and methanation reactor system. So solar PV drive the PEM electrolyzer to produce hydrogen. Here actually I would like to say that hydrogen is produced continuously. It is our assumption actually. And then we compressed, and finally we combine with CO2 that is captured from flue gas. Then the mixing gas are heated and then sent to a methanation reactor system to produce methane. So before model, I would like to give you our assumptions and some main input parameters. Here actually all gases behave as idle gas, and carbon formation in the methanation reactor is neglected. And it is important, and another important assumption is that the CO2 capture process is actually neglected in this model. And potential and kinetic energies are neglected in the energy balance. So you also see input parameters, some main input parameters in our model. While the operating point of electrolyzer is 1 ampere per centimeter square for current density. So actually we investigated the hydrogen CO2 fate ratio between 0.2 to 0.4. And also we investigated the effect of reactor pressure on the system performance. That's why we take the reactor pressure 1 to 3 bar. So the reactor temperature is constant and it is 250 degrees Celsius. So what about mathematical model? Firstly, I would like to present you solar PV model. Here actually we use specifications of solar PV model that was taken from the commercial company. Here we first calculated efficiency, and then we calculated power produced from PV model. So here actually two scenarios are considered. In the first scenario, when the solar PV is operated at maximum radiation point, and in the second scenario we consider the solar PV is operated at average solar radiation. So this solar radiation profile is obtained for Muller. So another important component is electrolyzer, and we modeled electrolyzer through the semi-empirical equation actually that was proposed by Harrison et al. Here we aim to estimate performance of electrolyzer. So in this figure you see the polarization and actually performance characteristic curve here, and data get from using data got from this curve, we calculated the consumption rate of water, hydrogen production rate, and oxygen production rate. Another components model is we developed is reactor model. Here actually we choose membrane-based reactor, palladium-based membrane reactor here because it brings us many advantages. Because I mean it can operate at low pressure and it can be operated at low temperature. So that means actually thermal integration is a little bit easy when compared to other reactor types. So for the modeling, we used a Hagen-Watson type rate equation. Here actually this is the Sabatier reaction in another name. So we calculated the reaction rate, and then we applied mass balance around the control volume of a reactor. And using this reaction rate, we calculated how much methane can be produced, how much hydrogen and CO2 consumed actually. So what about results? Here actually you see the species net flow rate of some species. Here in the left figure you see the hydrogen, CO2, and water consumption and or production. So here the key factor we determined is hydrogen CO2 ratio. When we increase the hydrogen CO2 ratio, fed into Sabatier reactor, I mean fed into methanation reactor. Here we when this ratio increases, the hydrogen hydrogen increases, while water produced by reactor decreases as expected actually. And again CO2 increases at the same time. So, but most importantly, of course, methane, when the hydrogen and CO2 ratio increases, methane yield decreases. So that's the important point actually. So what about system efficiency? Here we calculated electrical efficiency of this system considered. Here actually it should be noted that the system boundary consists of only electrolyzer and reactor. So when we calculate electrical efficiency, we ignore solar PV. That means actually the system efficiency accounts for only electrolyzer and reactor system. So here actually two parameters we investigated to see their effect on the system efficiency. Well, when the reactor pressure increases, the system efficiency increases slightly. And here actually, when the reactor pressure is just over 6 bar, the system efficiency doesn't change significantly. And another important parameter is hydrogen CO2 ratio. When the hydrogen CO2 ratio increases, the system efficiency decreases for a low heating value of methane and also high heating value of methane. So in conclusion, again, when the pressure increases, the system efficiency increases. However, the effect of pressure becomes negligible when pressure is just over 6 bar. And when the hydrogen CO2 ratio increases, the system efficiency decreases slightly. Besides, methane yield decreases. In the future works, as I said, we ignore CO2 capture and separation in the model. That's why we plan to consider CO2 capture and separation unit, and then we plan to do exergy analysis of this system. And most importantly, of course, the economic analysis will be performed under different scenarios and different reactor designs, not only a membrane reactor, other reactor types will be implemented into model actually. Thank you for your attention. And that's all from my side.
Thank you for your amazing presentation. Anyone has any questions, please? You may write in Q&A part also, or you may ask. Okay, I think there are no questions. Thank you for your nice presentation. We'll move back to Dr. Kovash. Are you able to share your screen now?
Thank you. I will try now. I hope it will work. Just a second. It seems that it still doesn't work. I don't know why is this happening. Can you please share presentation for me if it is possible? Okay. If not, I can talk without presentation. I have it here.
Dr. Kovac, I have your presentation. I can share if you want.
Okay, please. Thank you so much. Thank you.
Okay, so Dr. Kovash will be presenting hydrogen refueling station, state of the art and perspective. Dr. Kovash, please.
Thank you very much. Can you please put it on a full screen?
Okay.
Dr. Kovac, you can now control the screen. You have access. You have access my screen. You can change the slides.
Ah, okay,
But first of all, you should accept our request.
On my email.
No, now you're controlling our screen. The floor is yours. You can change the slide. We can try if you want.
Okay, just to check. I don't see where you can control. Okay, just a second. Where can how can I control it?
You can use the arrows in your keyboard.
Yes, but it doesn't work. I'm trying. Even you are controlling Turkish Academy screen. Now it's okay. Yeah.
Yes.
This is me. Okay. Yeah. Thank you. Well, thank you so much. I'm so sorry for this complication.
No worries, doctor.
Okay. Thank you very much. I don't know how to put it on a full screen because.
Dr. Kovac, you can accept the changes part. You see the yellow part, and then there's a white box over there at the top.
Okay.
In English, you would say accept, edit changes. Click on that, and then you can go into the full screen.
I see view options. Stop remote, use my keyboard. Okay. Okay. I don't see it. Okay, to not waste time, I will speak as it is. Okay. Good afternoon, everyone. I'm so sorry for these complications, but this never happened to me before, but for everything you have a first time. So my name is Ankica Kovac, and I'm coming from Croatia, University of Zagreb, Faculty of Mechanical Engineering and Naval Architecture. Background that you see is first Croatian refueling station and first Croatian hydrogen powered bike. Okay, today I will give you some overview on the state of the art and perspectives of hydrogen refueling stations. Oh, okay, it works. What do we think when we say hydrogen technology? So this implies hydrogen production and mostly green renewable hydrogen that is produced by water electrolysis using renewable energy sources. Such produced hydrogen we need to store in a high pressurized storage tanks, and we use it in fuel cell stacks, and with transportation and distribution by road and maritime transport and pipelines, we get the whole term of hydrogen technology. In a nutshell, this paper that we made, I would like to stress out that the rapid development of hydrogen technology over the last decade is the result of the public comprehending the gravity of environmental pollution and global warming. And this is the most important global warming and climate changes. And then hydrogen technology that has the biggest impact in media is fuel cell electric vehicles. And almost every day we see on the road launched new vehicle, new tram, new train, and also boats and airplanes. And for this reason, amongst the other considerable benefits, fuel cell electric vehicles are ideal promoters of a hydrogen society. For hydrogen to progress further into the vehicles industry and for users to comfortably drive these vehicles, it is imperative to build an adequate infrastructure. And for the infrastructure, I mean hydrogen refueling stations, because there is always the question, what was before, egg or chicken? Introducing hydrogen vehicles and hydrogen infrastructures need to go in the same time. So what was the motivation? Well, it is very well known to everyone that fossil fuels are one of the major causes of global warming, and the Paris Agreement aims to limit global temperature growth to well below 2 degrees, but with the higher goal to keep it below 1.5 Celsius degrees. Clean alternative fuels need to be used and to develop the application to phase out fossil fuels as soon as possible, and to ensure the competitive industry of EU, but the world in general. So hydrogen has the great potential to be such an alternative. Regarding to the topic, I will just scroll fastly through the hydrogen transport tech sector regarding to fuel cell electric vehicles. What is the current status of these vehicles? We have around 25,000 fuel cell electric vehicles worldwide, and the number of passenger cars reached almost 19,000, and increase of 69% in 1 year. This is amazing. And most passenger cars are located in US roads, while China dominates in buses and light and medium trucks. I don't know if it will work, but I will shortly just show you how does fuel cell electric vehicle work. Even I'm sure that you already know it, and many of you, I guess, probably tested these vehicles. So it is equipped with a fuel cell stack, with the storages tank and the battery. So once it is filled with the hydrogen, it is driving, and the only product is the water. Only byproducts are water and the heat, and we get electric energy as the main product. Refueling of this vehicle is around 3 to 4 minutes up to full tank on 700 bars. I will stop it now because I'm sure it is very well known to you, and I even had the honor to drive this vehicle. I show you the photo later in my presentation. Here is the diagram of all types of fuel cell electric vehicles by country, and we see that China and Korea and US has the most hydrogen vehicles located on their roads, but also European Union has the great role in this energy transition to clean transport to achieve climate neutrality also in the transport sector. What about the continents? In North America, we have around 32%, in Europe 9%, and in Asia we have 59% of the total hydrogen vehicles on the road. Total number of all types of vehicles in the world, as we mentioned before, we have passenger cars around 19,000, of light and medium duty trucks around 2,000, and buses 4,500. And heavy duty trucks are just 8, even though there is a huge focus on the buses and on the heavy duty trucks to take the main role in this energy transition, and these vehicles are the most promising in the faster transition in the transport sector to clean transport. Passenger cars by continents, in Europe we have 11%, in North America we have 43%, and in Asia we have 46%. What about passenger cars in Europe? Well, it is located differently, but it is impressive number on the road of European roads, and mostly they are in Germany and Scandinavian and countries, and in the middle of the Europe. Overview of the current situation by the end of 2019 is that from 2017 to 2019, we see the progress of huge percentage, and in the years that are coming, it is expecting to double, triple, and more on the roads, and mostly because a lot of countries are presenting their hydrogen strategies in which they are focused also deeply on the transport. So what about hydrogen refueling stations? Current status says that the total number of hydrogen refueling stations, including public and private or non-public, is 470. Maybe in the meantime it was changed a bit, but this is the number around 500. Public hydrogen refueling station in 3 countries, Japan, Germany, and the USA, represent more than a half of these total stations, and most of these stations are located in Asia. We have there 200, followed by Europe of almost 200, and the USA of around 70. Japan is the country with the largest number when we look at just the countries, with the largest number, and followed by Germany and the US. China is on 4th place, ahead of South Korea and France. This is a source from International Energy Agency division. It's a technological program for collaboration on advanced fuel cells. So here I just put a short video. How does hydrogen refueling station work? It is presented very simple, and it is simple as it is presented. You just come with your car and press the button. It's everything on the button, and press the button, press the nozzle, and wait for a couple of minutes, and your tank is full. Everything is easy, everything is clean, without any harmful emissions. Okay, and almost all hydrogen refueling stations are operating on the same principle. Here is an overview of the current situation by the end of 2019. And what is interesting is that here is Croatia. And we have one little hydrogen refueling station. It is not for vehicles or for the buses. It is a small refueling station up to 30 bars, and it serves to refuel first Croatian hydrogen bicycle. So we have this is background that I talked about on the beginning, and I hope soon up to 2025 that we will have a few hydrogen refueling stations to welcome all hydrogen vehicles that are already on the road. What is the current situation by the end of 2019? As we said, we have Japan, Germany, US, that are China, Korea, and France that are mostly with the highest numbers, just as for the vehicles. And many of these countries has a great developed their strategies regarding to the all sectors, not just to the transport sector, but also have a great infrastructure to serve the vehicles they have. What are the goals, long-term goals up to 2050? Currently we have around 25,000 vehicles and around 500 hydrogen refueling stations. And if we look, I will not read all these tabs. You can read it by yourself. I guess this presentation will be shared. So up to by the 2050, we will have impressive number both for vehicles and for hydrogen refueling station. Why hydrogen? Why hydrogen infrastructure? Because there is no emission, there is no harmful emission, and it is completely environmentally friendly. We have renewables in unlimited amount, like sun, like solar energy, and we have water, and we need to use it, these resources, to achieve the goal of climate neutral world up to 2050, because why we are doing all this energy transition and we are searching and investigating all clean technologies is because of climate changes. And every time we get new strategy, I don't know, hydrogen strategy, some general energy strategies, or some other plans, it is all about climate changes. So if we don't make it, it will not be good, because we are almost now over the limitation in degrees and the concentration of CO2, where soon will not be possible to breathe, to think. And I think we, on the global level, we need to make this transition faster, just to save the environment, to save our lives. And just a short from Croatia achievements on this field. As I mentioned, here is a refueling station. Inside of it is electrolyzer, because only acceptable hydrogen, type of hydrogen, is renewable hydrogen, green hydrogen that is produced by water electrolysis using solar energy. And on the roof, top of the roof, we have PV photovoltaic modules that we produce hydrogen by electrolysis, and we are put it in the storage and refueling our little bike. This shape is protected as intellectual property on the national and international level because of its design, and it has a light, LED lights, and it is a part of sophisticated equipment inside of it. It is also visually attractive for the visitors and everyone who passed nearby this station. Also, we are on the European hydrogen map, and it is noted. If you see this map, we are divided on the west and east block. And we have to change it. We are working now on it to cover this part of Europe also with the hydrogen refueling station. Only in that way we can accept all vehicles, and we can fulfill our achievements in clean energy transition in transport sector as well. And also what we made, I was a pride leader of this project, is Croatia Mirai Challenge. From 2019, when we did road trip from Zagreb to Brussels to demonstrate clean transport based on hydrogen, and it was a trip of 1,300 kilometers, and it was so exciting to plan this trip because the nearest hydrogen refueling station to Croatia, from Zagreb to Croatia, was in Graz, and all the time we were like, oh, just drive to Graz, just be enough to Graz, because we don't have the option to refuel our tank, because during the stay of this vehicle in Croatia, everyone wanted to test it, so we also drove it during the via Croatia roads, and this was the first time that some hydrogen vehicle was driving on Croatian roads, and this is a refueling station in Graz. So, what are the conclusions? The development of hydrogen society is the most evident through the rapid expansion of hydrogen refueling stations, and also as nation's ambitious plans, we are currently working on our national hydrogen strategy, and based on trends, goals, and visions for Korea, Japan, China, Europe, California, as well as the world in general, and visions of the Hydrogen Council for 2050, we can conclude that hydrogen and fuel cells have a strong potential to play a crucial role for sustainable mobility. How we will achieve all these targets, set targets to become global climate neutral to 2050, just with the collaboration of policy, academy, and economy. This is a dream team to achieve a great success of our aims. By the way, these wheels are rolling, but as I'm not able to put it on a full screen, they are just fixed on the slide. Okay, this is all for me. Thank you very much for your attention, and I apologize one more time for the problems that my laptop caused. I'm on vacation currently, so I guess my laptop is also on vacation. So thank you for understanding and for listening, and thank you, the host, Turkish Academy of Science, for the whole patience. Thank you.
Thank you, Dr. Kovac, for a very nice presentation. Let's wait for a few minutes if there are any questions. Dr. Kovac, I have one question. When you went for a road trip, so what was your economical average as compared to the fossil fuel engines?
Yes, I have this data written, and I think I already published it somewhere, but if I remember well, we stopped for around 5 times, and our cost of the fuel was around 100 euros, if I remember well. It was cheaper than if we travel with the fossil fuels on conventional vehicle. Yes, I calculated on it, and it was cheaper. If I remember well, completely in total, just on fuel, was around 100 euros more or less, and we have one sleepover in the hotel because it's too much kilometers, and it was successful, and our mission was completed to show how is it cheaper and cleaner, both.
Thank you, Doctor. We have one question. Priscilla, can you ask your question, please?
No, sorry, mine is not a question. I was just wanting to join for my presentation. Sorry about that.
Thank you, Dr. Kovac. We'll move to next presentation.
Thank you very much.
Okay, so the topic of our next presentation is testing membranes for separation of CO2 from small molecules in landfill gas. You have 13 minutes to present, and then we'll have 2 or 3 minutes for Q&A session.
Okay, good afternoon, everybody. I really sincerely apologize for for not joining in at my exact time slot. I got confused about the timing in the UK, so I'm really sorry about that. I'm just going to pull up my slides in a minute, and then I will go on. Again, I really apologize, and I'm so sorry to everyone. Okay. All right, so can everyone see my screen, please, and hear me okay?
Yes, we can see the screen and we can hear you loud and clear.
All right, perfect. So my name is Priscilla Ogunlade, and I'm from the Robert Gordon University. Sorry, I'm just trying to, I don't know if, pardon me. Sorry, now you can see me. Sorry about that. I'm from Robert Gordon University, and I'm just making my presentation on testing membranes for separation of CO2 from landfill gas. And my work was done in collaboration with some PhD graduates, as well as my supervisors from Robert Gordon University, who is Professor Edward, and another from another university, Dr. Ferdas Mohammed Tuki. Right, so this is an overview of what I'll be discussing today. Just quickly run you through the introduction, the methods that we use, the results, the discussion, the conclusion, and the future work. Okay, so biogas is a renewable form of energy that's involved from anaerobic digestion of biodegradable materials, and it contains mainly methane and CO2. It has some trace quantities of other impurities such as hydrogen sulfide, chlorofluorocarbons, and a few other siloxanes and things like that. However, majorly it's methane and CO2 which contributes to the larger percentage of a biogas mixture. It's formed from the anaerobic digestion of biodegradable materials, and the process occurs in nature, so it's inexpensive, and we can produce a gas that can be used, biogas, which can be used as a fuel, can be used as well for domestic purposes, for transport, for in cooking and heating, and a variety of purposes. So biogas on its own, when it's produced from the digester, is because of the CO2 content that's in it, it can cause problems down the line, like taking it through a pipeline to distribute to other people that require it. So that's the essence of the purification process that my research is working on. So the whole process it's beneficial because it utilizes waste materials that would have been polluting the environment and incurring costs for removal and disposal of those materials. So again, a few of the incidents that have been occurring in the last few years, which have brought the awareness of climate change and global warming. So we see some flooding incidents, some heat waves, droughts, and even food shortage. And those are and these are just a few to mention the most. So the rationale of this research is that we're going to be utilizing gases that would have otherwise been polluting the environment. So we're making use of greenhouse gas emissions to produce a fuel that can be basically recycling and producing fuel that would be used for purposes that fossil fuels are currently being used for, and then that would that in itself would curtail the reliance on fossil fuels that on their own, the burning causes and the release of these harmful gases. It's also cost effective membrane technology. Again, it utilizes waste waste from food, waste from humans, waste from animals, and turns that into this valuable gas after being in the digester. The process is efficient and we can produce a high heating value fuel. Okay, so again, the method that I'm using is membranes, and these membranes act as sieves that limit the passage of some gases and retain some of them. So if you can picture a strainer from your kitchen, these have pore sizes in the nanometer range, and that in itself allows the fluids that are passing through it to be excluded based on certain criteria, be it size, molecular weight, and a different other conditions or different that the membrane will be going through. So it uses a shell and tube system, and for this study, we used 3 different membrane models of pore sizes, 15 nanometers, 200 nanometers, and 6,000 nanometers to test the behavior of these gases, CO2 and methane in particular. So the membrane was fitted into these models, and I'll show you a picture just coming in the next slide, fitted and sealed with graphite seals at the end to prevent cross mixing of gases. And then we studied the behavior of these gases at different temperatures and pressures. So again, this is the rig that I'm just trying to explain the methodology. That's the rig in the photo. And you can see there's a gas cylinder that contains the mixture or the single gases and the regulator that's attached to it. It then goes through the pressure gauge into the membrane module that's pointed or labeled 2, which is insulated. There's a temperature indicator, and there's a temperature indicator and a heat regulator, so that we can monitor the process conditions. On the exit, we also have a flow meter that takes the permeate gas down to where we'll be testing it, and then we have the retentate in the system as well. So just a few of the results we have from this study. I've displayed here the effect of membrane of the pore size on the permeance of the gases at different temperatures, and you may be able to see that as the pore size increases, the permeance of the gases reduce, and the type of the curve that we're seeing here is quadratic, which tells us that there's a parallel flow regime taking place in this gas flow, and the mechanisms that are at play are the viscous flow and Knudsen flow, Knudsen diffusion. So again, this gives us very good information or good insight as to what is happening in the membrane as these gases continue to pass or flow through, and how CO2, as you can see, there's methane and CO2 and how they are performing in terms of even the difference in the permeance of these gases. We can see for methane, it has a higher permeance in both cases than CO2, and that can be attributed to the molecular weight of the gases that make it that of methane in comparison to CO2 that causes to diffuse faster. So, like I said, the gases exhibit parallel flow transport model, and viscous flow and Knudsen diffusion are characterized in this the effect of the pore size on the fluid behavior was analyzed, and we're able to find a relationship that links these pore sizes with the tortuosity and the permeance of the gases. Previous research was focused on porosity and tortuosity, but here we're beginning to find or see the link between pore size, tortuosity, and the permeance of the gases. So thank you very much for the time and for listening.
Thank you, Priscilla. We don't have much time left for the question and answer, so I'll just skip that. Thank you for your nice presentation. Best of luck.
Thank you.
We'll move to our last presentation for the session. The topic of the presentation is suitability of spheroid as oxygen carrier in chemical looping combustion. Presenter is Mr. M. Durmas. Please, you may present. Sorry, Ms. M. Durmas.
Hi everyone. Can you see my screen?
Yes, we can see and we can hear you loud and clear.
Okay. I will start it. Good afternoon, everyone. My name is Merve Durmaz, and I am a research assistant at Chemical Engineering Department in Çankırı Karatekin University, and also I'm a PhD candidate. Today, I'm here to talk about suitability of siderite as oxygen carrier in chemical looping combustion. As you know, carbon dioxide is the largest contributor to greenhouse gas emissions. Carbon dioxide emissions mostly from human activities, and it reached 417 ppm in June 2021 in this year, the highest level in history. This increase in the carbon dioxide level affects the living life by causing the climate change. Renewable energy sources, they do not cause carbon dioxide emissions. Not enough to supply energy for increasing the world population. Therefore, the use of fossil fuels is inevitable. Scientists have developed many methods to capture carbon dioxide from fossil fuels and sequester it from atmosphere. Among these methods, the most popular one is the chemical looping combustion technology in recent years. What's the chemical looping combustion? It was given in 1950s as a way of producing pure carbon dioxide. It was developed as a combustion technique in 1980s and later presented as a way of separating carbon dioxide at fossil fuel combustion in the 1990s. Interest in chemical looping combustion has increased in recent years due to its high energy efficiency and low cost of carbon dioxide capture. The combustion products, carbon dioxide and water, are easily separable without any extra downstream processing cost. In addition, chemical looping combustion minimizes nitrogen oxide formations because in the fuel reactor, the combustion of the fuel occurs in non-nitrogen environment with only oxygen. And in the air reactor, the reduced oxygen is reoxidized without the fuel at the temperature lower than the formation of nitrogen oxide gases. Also, solid, liquid, and gaseous fuel can be used in the chemical looping combustion processes. Chemical looping combustion with gaseous fuel. Chemical looping combustion involves the use of metal oxide as an oxygen carrier. The process consists of two interconnected fluidized bed reactor as an air and a fuel reactor. And the solid oxygen carrier circulates between the air and the fuel reactor. The gaseous fuel is fed to the fuel reactor. Carbon dioxide and water are obtained from the complete combustion of fuel with oxygen, the metal oxide. Water vapor is condensed and then separated from the carbon dioxide stream. In the chemical looping combustion, lots of metal oxides using as a oxygen carrier. For example, nickel and iron and manganese like that. We study with iron oxides. Why we study with iron oxides? Because iron-based oxygen carrier are a suitable oxygen carrier for chemical looping combustion applications in terms of low cost and the low toxicity. However, these oxygen carriers have low oxygen carrying capacity, poor redox characteristics, and low methane conversion. But we can track these properties with some applications. When the hematite is reduced, magnetite, iron oxide, and the iron can be formed. Due to the thermodynamic constraints, only hematite to magnetite conversion is suitable for industrial scale use of chemical looping combustion. And we used in this study as an oxygen carrier, siderite. Why we use siderite? Because siderite is an ore that contains satisfactorily iron, and it has not been evaluated as an oxygen carrier before. And it is a very common and affordable mineral that can be easily transformed into the form of its oxide by simple pretreatments such as calcination. And it was supplied from Hekiman Mining Company from Malatya, Turkey. And it consists of like this minerals, especially we use 56.6 iron oxides totally. And the preparation of siderite for experiments, if we want to look, first the siderite sample were dried at 105 centigrade degree in an oven for 2 hours. And then they crushed and then sieved, and finally samples were calcinated in furnace at 900 centigrade degree for 12 hours. This picture illustrates chemical looping combustion experimental setup process. The gas traffic in each test was adjusted and controlled by collaborative operation of the mass flow controllers and selenide valves and a PLC flow control and software. The composition of the stack gas emitted from the reactor during the test was determined via gas analyzer. And experiment conditions are aqueous fullerized bed loaded with 5 grams of siderite. Reduction half cycle temperatures is 850 centigrade degree, and time reduction half cycle 30 seconds. And the fuel gas mixtures consist of carbon monoxide, nitrogen, and hydrogens. Time of oxidation half cycle 180 seconds. And the oxidative gas mixture composed of oxygen and nitrogen with like an air ratios. And the volumetric flow rates of gases entering the reactor 6 times of minimum fuelization velocity. And we completed our experiments end of the 50 cycles. And when we look at our results, oxygen carrier materials, ours is siderite, exhibited sufficient and stable performance during the 50 cycles for all compositions, while yielding more than 92% fuel conversion. Due to low viscosity and the density of the hydrogen gas, the highest molar flow rate was required in test tube for establishing the 6 times of minimum fuelization velocity. You can see here the results of test 1 and test 2. Test 1 is just, we use carbon monoxide and nitrogen. Test 2, we used hydrogen and nitrogen. And the test 3, we used carbon monoxide, hydrogen, and nitrogen. And the test 3, again, carbon monoxide, hydrogen, and nitrogen with different ratios. And the variation of the reduction rates of siderite versus conversion through the chosen reduction of cycles of all tests is given these figures. Conclusion, siderite kept its reactivity for almost whole tests since no considerable decrease on reaction rate was occurred. As you see here, test 3 and 4. And in this figure shows the variation of the fuel conversion efficiency during the CLC tests. While the mean value were as approximately 88% for test 1, 96.7% for test 2, and 93.7% for test 3, and 89.3% for test 4. As can be seen from the figure, the fuel conversion efficiency dramatically decreased after 40 reduction of cycle for test 1, in which the fuel was not include hydrogen. However, the conversion efficiency was almost stable for 50 reduction of cycle during the remaining test, in which the fuel was blended with various amount of hydrogen. And the conclusion, siderite is a proper and cost-effective iron-based oxygen carrier for chemical looping combustion process, sufficient reactivity and durability. Siderite accompanied 92% fuel conversion as a mean of 4 tests, each lasted 8 hours. Siderite may be considered as a suitable oxygen carrier for pilot scale chemical looping combustion applications, especially during the conversion of coal-derived syngas into energy. And also in the study was funded by Tibetan Pratekin University research project grants, and these supports are thankfully acknowledged. The authors also grateful to Mr. İlker Kılıç for supplying considerate samples. Thank you for your attention. And now I can take your questions. Thank you.
Thank you, Dormat. Are there any questions? You may please type in Q&A part. I think there are no questions.
Thank you.
Thank you for your presentation. Thank you everyone for attending the session. Hope you enjoyed and you learned from each other, and hope you enjoy the conference further.
Yes. Sorry, I can't understand the last sentence, your last sentence.
I was just thanking everyone. It's fine. Thank you.
Thank you.
Hello to everyone. Hello, Nuri. Can you hear me?
Yes, Sandro, I can hear you. I think it's you, right?
Yes, yes. I will activate my camera.
Okay, I also turn it off. Welcome.
Welcome. Hello. Thank you.
Yeah, how are you doing?
I'm nice. Yesterday, my son was born, so we
Is that right?
Yes,
That's
we
perfect
yes.
news. Yeah,
Yes.
congratulations.
Thank you. We had a celebration, so it was long night. It was also long night before, but now everything is.
I think it's worth for it.
Yes, yes,
Excellent
yes.
news. Is it a boy or girl?
Boy. I had one girl. She's 8 years old, and now this is my second child, which is
excellent. So you will have a great presentation then.
Yes.
You are all boosted up with a joy. Excellent.
Yes.
I'm so happy.
Okay.
And this is my birthday today.
Okay.
Yeah. Wow.
My congratulations also.
Thank you.
Okay. So
we're expecting David. I think he's also online right now.
Yes.
But we still have another 5 minutes before we start the next session.
Okay. During my presentation, I will plug off camera because of.
I think somebody will be with us, a technician, to help us. You can just share the screen. I think you have the.
Yes. It's not a problem. Yes, I will share the screen, but I will turn out my camera because sometimes when you have camera plus presentation, it can be like blockage, and later when questions will come, I will activate again.
Correct. Yes, no problem. So I will make a short introduction, then I will hand it to you.
Okay.
And David is also here. Hi, David.
Okay. Hello.
David. Hello.
Welcome.
Yeah, Kemal
this
with
is
me.
Nuri. Okay, Kemal. All right, good to have you both. So I think we have another 5 minutes before we start the session.
Okay.
We'll start with Sandro, and I'd just like to remind you that we have 30 minutes for each, and please allocate the last 5 minutes for the questions and the discussion. Maybe we will have some questions.
Okay.
So let's wait another 5 minutes. Are you in Turkey, David, since you have Kemal with you? Are you in Turkey right now?
No. We're both in Albuquerque, New Mexico, USA.
Oh, I see. Okay.
So it's very not very early, but it's morning here.
I can imagine. Maybe 8 hours. Yeah. Thank you. Yeah. It's almost 5 o'clock in the afternoon right now here in Izmir. So perhaps it's around 8 or 9 o'clock there in New Mexico. I'm not sure.
Just a few minutes after 8. 15 minutes after 8. Yeah.
Okay, 8:15. Okay. All right, I'm waiting for the green light from our organizations. So another 2 or 3 minutes, maybe.
Okay.
And I will be happy before you start your presentations, if you just quickly introduce yourself to the audience. I see some people already joined us, waiting for us. I'll just make a short introduction, then I'll just hand it to you.
Okay. No problem.
And David, I don't know if you heard it, but Sandra has just a boy yesterday.
Oh, my son was born yesterday.
Exactly.
So.
Thank you. Wonderful. Yeah.
Is there any problem with the connection, David? Can you hear me right?
Yes, I can hear you fine. So
okay, thank you. If there's any problem, just don't hesitate to stop me.
Okay.
Kemal Bey, siz orada mı yaşıyorsunuz? I'm sorry that I just spoken in Turkish spontaneously. I was just asking Kemal if he's living there or not.
No problem.
Yeah, I'm working with Dr. Vincent for almost a year, right?
Okay. Yeah. Are you a postdoc or?
Here. Yeah, I actually work in Dumlupınar University.
Good.
So I am a visiting professor here.
Excellent.
And
excellent. First, and in Turkey, where are you from?
I'm from Tokat.
Tokat, good, excellent. Okay. Let me just send an email to organization, a person from organization, see if they're going to give us a green light or not. I think Mr. Mehmet is dealing with us. Well, I don't see any message from our organization, but I think we're on time. And with your kind permission, I'd like to initiate the conference. And I'd like to welcome everybody to the last session of today. And I thank to TÜBA for letting me, for giving me a chance to moderate this conference. We have really two esteemed speakers today. Mr. David Whitten, I hope I pronounce your last name right. Is it Whitten? Yeah. Okay, good. It's good enough. So Mr. David Whitten and also Sandro Nizetic. I hope this is also right.
Yes, thank you.
And I'd like to give our audience a good news. It's a good start. Sandro, I hope you don't mind that I'm really excited for you.
No
he
problem.
just had a boy yesterday. So this is a good news for our conference.
Thank you.
So my name is Nuri Azbar. I am from Ege University in Izmir, Turkey, and I am the moderator for this session today. For the sake of the time, I'm not going to go in details, but I'm a full professor at Bioengineering Department at Ege University. This is a state university. My main expertise is also energy. I'm dealing with the biofuels, the bioenergy part of the energy production, and also sustainability in regards to environmental issues. So we have two esteemed speakers today, as I said, Mr. David Whitten and Sandro Nizetic. And I'd like to start with Sandro, if I may.
Yes.
And please, Sandro, before you start your presentation, would you introduce yourself shortly? Then we will give you the stand to you for your presentation for 25 minutes. Okay, go ahead, please.
Okay,
good to have you here.
Thank you, Chair, for nice introduction words. And also I would like to thank organizing committee for invitation. So I'm Sandro Nizetic. I'm also full professor at the University of Split, Croatia. My main research field is related to renewable energy technologies, energy-related issues, energy efficiency. And I'm editor-in-chief of Energy and Energy Sources Part A Journal, associate editor in International Journal of Energy Research, as well as associate editor at Journal of Cleaner Production, and hope that today my lecture would be interesting to your audience.
Good luck.
Thank you. I will just turn off camera, not to. So is it okay? Can you hear and see?
Yeah, everything is perfect. Go ahead.
Okay, okay, great. So today the topic of my lecture is more focused on photovoltaic thermal collectors, basically solar photovoltaic thermal collectors, and special designs with incorporated phase change materials. Since PVT collectors are, of course, assembled from photovoltaics plus a kind of heat exchanger, first of all, I would like to address a few issues which are linked with photovoltaic technologies as well as renewable energy technologies. So as we can see from global situation worldwide, we can say that energy transition has started. And it all depends how each country is working on it. But it is more than clear that renewable energy technologies, especially mix of energy technologies, is in front of us, and that currently majority of installed capacities regarding renewable technologies is focused on photovoltaics as well as wind generation technologies, which is kind, of course, of very likely directions in the close future, although other also renewable technologies are also growing. If we see overall global market related to the photovoltaic technologies, then of course it is not surprised that China and Asian region is leading in the production of photovoltaic technologies as well as in overall installed capacities. And China has got over 200 gigawatts overall of installed capacities in 2020, while globally we have over 700 gigawatts of installed photovoltaic capacities. Europe is also working on PVs, but of course, if we look Asian region, it is clear that in upcoming years and the case this Asian region plus also Indian region would lead in overall installed PV capacities. If we look what we have currently on the market regarding the implemented PV technologies, then of course still we are using the oldest PV technologies which are based on silicon in mono multicrystalline variant. Plus we also have thin film technologies which are basically interesting because they can be applied on different geometries. But if we look the share, then it is clear that almost all installed PV capacities are based on mono or multicrystalline silicon PV panels. This is a new state in 2020 taken from Fraunhofer Institute. They are closely monitoring global installation on PV technologies. And we can see that still the trend is the same. Thin film is just few percent, while majority of the markets are mono or multi-silicon based photovoltaics. Of course, why mono and multi had survived the market? The issue is obviously techno-economic suitability. Although the majority of installed capacities are in multicrystalline variant because they are a little bit cheaper. Yes, they are less efficient, but on the other side, if we have some suitable geographical location with sufficient space requirements, then it is more likely that we will take multicrystalline variant, while if we have some limited surface and request for higher efficiency, then we will take monocrystalline silicon PV panels. If we are analyzing what is the current trend regarding the general development of new PV technologies, time to time, we can see that we have some laboratory jumps where efficiency is quite higher when compared to silicon-based photovoltaics, which are usually below 20% in overall energy conversion efficiency. Then perovskite photovoltaics are maybe interesting in the close future, although still they have some issues with long-term stability, with application on large scale, and also some issues with environmental footprints. But currently in laboratory conditions, multi-junction and especially in CPV variant are reaching the highest efficiencies. But on the other side, there is a problem, of course, with cooling, because if you have PVs which are set on relatively high temperatures, they are also suffering from efficiency degradation. Photovoltaic technology still they have some open issues. Of course, we can speak about efficiency or energy conversion efficiency, which is usually less, as I said, less than 20%. In some occasions, it is even not a problem, because if you have large area and suitable solar characteristics, you could produce electricity which is competitive with also other energy sources. But in some situations, and especially in some economies which are weak, of course, there is a problem with overall investment cost, which is again affecting, of course, efficiency. Then we have also issues with environmental impacts of photovoltaics, which will be more emphasized in upcoming decades since we are increasing PV capacities. As I said, currently over 700 gigawatts, but there are some projections that around 2050, globally, we would have over 4,500 gigawatts, which means that we will have problem with recycling, with waste. And of course, there is also issue with grid and management of photovoltaics in the sense of how to achieve efficient energy storage technologies, because in some cases, if we have battery storage systems, then of course there is issue with cost. And finally, with silicon-based photovoltaic technologies, there is also issue with long-term performance, because usually we have degradation, which is somewhere between 0.5 and 1% per year. Plus, we also need to emphasize that there is also degradation that is caused by elevated operating temperatures. So very likely that in upcoming decades, if we check what would be like the future of photovoltaic technologies, I think, and it's my opinion, that we will obviously have some hybrid approach, maybe silicon-based plus perovskite. We will see what the future would bring us. Because of that, of course, we are trying to implement photovoltaics on some other ways, or we are trying to find some new application areas. One of the interesting areas are floating photovoltaics, and we can see that number of installation globally worldwide is increasing, especially in China, because floating photovoltaics are very interesting since they have better performance than ground-based photovoltaic systems. But still, of course, there is a challenge for these installations in, let's say, open sea environments. And also we need to think about potential environmental impact of photovoltaics. It is fine if you have some lake which is controlled, but what if you are putting this kind of floating systems in some areas which can cause issues for environment? There are also ideas for agrivoltaics. So very nice way how we can integrate photovoltaics in the production process of different vegetables, because vegetation can be used for cooling of the photovoltaics. And there are some interesting research studies where different cultures have been checked in order to see what is the best performance of the photovoltaics regarding the cooling effect of vegetables. At the end, I would like to once time to emphasize this waste issue. Those are projections, because we have increased number of installation, but on the other side, we also need to think in advance on the waste, how we will manage this waste in the upcoming decades. Now let's speak a little bit about photovoltaic thermal systems, since this is the main topic of my lecture. An introduction was related to photovoltaics, as a PV panel is the main part of the PVT system. So those are systems that can cover both thermal and electricity demands, which are usually demanded in especially residential building, but facilities where electrical efficiency is usually less than 20%, thermal range between 40 to 70. Of course, there are some designs when we can reach over 70% of thermal efficiency. Unit cost is typically 300 to 500 euro per square meter, which is the main problem, and why we have a less number of installed capacities, because of still high unit cost. And usually producer warranty is 10 years, which of course is not so attractive, because if you compare a typical photovoltaic panel, then usually 25 years is warranty from producers. good thing with PVT is that fact that in the PVT configuration we are cooling photovoltaic panel, and cooling of the photovoltaic panels is important because we are improving efficiency, since photovoltaic panel, when exposed to solar energy, and of course when exposed to higher operating temperatures, which is usually, let's say, 50 degrees and above, there is a degradation of energy conversion efficiency, which usually ranges for typical market available technologies from 0.4 to 0.6% per degrees of Celsius. So if we are cooling, we are fighting to increase efficiency, which is, as I said, relatively low. And of course, we are increasing the lifetime of the PV panel. There are recent studies that have shown up that by cooling, we can increase the lifetime, which means that we can go above 25 years. And in general, we will prevent also degradation issue, which is caused by aging, because constant cycling, heating and cooling on, let's say, high operating temperature is reducing the lifetime of the PV panel. Because of that, when we are designing PVT panels, we should also consider different cooling approaches that can be divided on passive and active cooling techniques, or even hybrid combination, one or other. Passive are low cost, easy applicable, but they have limited increase in performance. On the other side, we don't have operation cost and very easy maintenance. On the other side, active cooling techniques are associated with high initial cost, but they are more flexible. They have improved cooling effects, but we have operational cost, and of course we have more complex maintenance. More detail, passive can be attached heat sinks, so different variants of heat sinks can be attached on the backside surface of the PV panel. We can arrange thermoelectric cooling, even liquid immersion. We can change architecture of the PV panel, so we can change geometry in order to enable passive cooling or more efficient airflow over the PV panel. And finally, radiative cooling with different coatings. Active cooling is usually water or indirect water, air forced, and finally application of nanofluids. One important thing with cooling of the PV plant is that it can be successful. When I have analyzed a few years ago the cooling strategies and the recent studies for PV panels, then I have realized that majority of the authors have been just focused on performance, and but they were not, of course, focused on economic viability. This is one successful story from Portugal. They have been used a cooling system with water sprinklers, and it was 5 kilowatt PV system that was experimentally tested in Portugal climate conditions, and based on realistic performance, they have calculated payback time period in 2 years, revenue from $17,000 to $20,000, with annual increase in performance between 12 to 17%. So this is just proof that cooling is, and it can be suitable, but of course we need to be careful regarding design. So let's speak now more detail about photovoltaic thermal systems. Of course, always when we speak with some technology, we would like to see what are the main application areas. We can use them for production of domestic hot water. We can use them for process heat, for drying purposes, for different vegetables or some raw products. Or we can use them, which is the most case, for residential heating or just for heating systems. Usually PVT collectors are made, on their design is being made that they work on low temperatures, which is usually water up to 50 degrees of Celsius, but with proper design, we can produce them with water which is over 80 degrees of Celsius, but in that case, we are speaking about CPVT systems. Phase change materials can be very easily incorporated with PVT collector design, and phase change materials, they are very useful because they can reduce operating temperature of the photovoltaic panel. And of course, on the other side, we can store, remove heat. In general, we have two opposite goals. In one sense, PVT collector needs to produce electricity and needs to produce, on the other side, hot water. If we are increasing temperature of the PVT panel, we are decreasing produced electricity. So the fine balance needs to be found with proper design. PCM is interesting because it can help to regulate operating temperature of the PVT panel, especially if we have active cooling. There are different types of PCM, organic, inorganic, hygroscopic, and the main focus of nowadays PCM materials is directed to the latent heat, and of course price depends from the latent heat, and nowadays we can produce various PCMs from different melting temperature and with relatively narrow range of thermal conductivity, which is usually a problem. So the main issue with PCM materials in the PVT collector design is, first of all, high unit cost, which means careful design. It is usually 5 to 15 euro per kilogram. Then we have issue with properties, with physical properties of PCM in the long terms. No one can tell us what would happen with physical properties in, let's say, 10 or 15 years. Usually, producers are giving some narrow range, but in the long terms, it is question what will occur with PCM materials. There is also a problem with thermal management. PCM layer is good in the short term aspect because it can absorb the heat, but later you have problem because it is problem how to remove the heat, and there is a problem with thermal inertia of the PCM layer, which means that we need to optimize thickness of the PCM layer, especially in the case of the PVT collectors. And in some case, we can have problem with weight. If we have limited weight in some specific application and we have relatively thick layer of the PCM, then it could be a problem. And finally, environmental footprint, because the production of the PCM materials is linked with the release of different chemicals. So the main requests for PCM materials in the PVT concepts are focused on low unit costs, high thermal properties, which means latent heat, thermal conductivity, specific heat, stable melting point, environmental suitability. It will be great if we can use some organic PCM that are non-toxic, then efficient phase change transition, and finally to secure long-term stability. Regarding the designs, of course, one of the main elements we will see later of the PVT systems is also the coolant. It can be air-based PVT, water, or we can even use the nanofluids. But when we see the performance improvement, then it is clear that water and nanofluids as coolants are ensuring the highest performance in the PVT aspect, which means electricity and thermal power output. Configurations of PVT PCM-based collectors can be freestanding. It can be building integrated PVT PCM systems, or we can have CPVT systems, so the systems which are designed with kind of concentrator technology. The main design element of each PCM or of each PVT PCM collectors are PCM casing, PV cell, of course PCM material as itself, insulation, tubes or channels or tubes equipped with absorber, and finally, of course, the working fluid. So recently I have analyzed several PVT PCM collector designs, but just one that were experimentally tested. So no, just I was not focused on just pure design without providing experimental setup. And regarding the PCM casing, usually for design, aluminum, copper, acrylic glass, steel, or plexiglass are used. Regarding the PV cells, there are always silicone-based, mono or poly. Then regarding the PCM, usually it is, and mostly it is paraffin based, but in a few studies I have found combination of PCM plus biochar. Then usually we are using thermal insulation to reduce heat transfer from the PVT panel, which is mineral wool, rock wool, polyethylene, cork wood, polyethylene foam. And finally, the tubes, or as I said, channel and absorber, are used as straight, square, or serpentine, or even twist, and they are usually made from aluminum, copper, aluminum roll bond, or polyethylene absorber. Regarding the selection of the working fluid, we have three choices usually. Air is cheap, of course, but weak thermal properties, and lowest overall performance, because air is not able to cool and to provide the cooling of the PV panel as water or nanofluids will do. But on the other side, if we have air-based PVT systems, so PVT PCM, they are very suitable and they can be very easily integrated in the building HVAC systems, which is one field that should be further investigated more in detail. Water is usually the most used, and the widely used suitable coolant with suitable physical properties, as well as overall performance improvement regarding the water-based PVT collector is very good regarding the electricity and thermal power output. And finally, we can use nanofluids. There were several studies that have examined PVT PCM plus nanofluids. So nanofluids were first put inside of the water, or even nano-enchanged PCM materials. But the problem with nanofluid is, first of all, nanofluids are toxic materials, and it is problem with handling, and no one knows how they will behave in the long terms, especially if we have some building integrated systems with nanofluid. Then we have problem with preparation. Preparation of the nanofluids is strongly affecting physical properties of nanofluids, and also the long-term stability of the nanofluids. And at the end of the day, nanofluids or nanomaterials, which are later used to create nanofluids, are associated with relatively high unit costs. So it is something which needs to be justified also from economic point of view. Regarding the tubes and channels, or importance of the tubes and channels in the PVT PCM collector designs, is critical, and we can have different configurations. I have just emphasized typical use. It can be straight tubes, serpentine tubes layout in different configurations, or straight channels. The main idea is try to cover as much as possible larger area of the PV panels, especially the central part of the PV panels, and also from my point of the view, to have like efficient cooling and good response in the cooling. It is good to divide layout, or it can be tube layout or serpentine, no matter, but to be divided in different sections. Regarding the absorber is usually made from tubes plus a kind of plate in order to be easily attached on the backside surface of the PV panel. Plus it is also recommended to put some thermal paste in order to ensure good thermal contact between absorber and the photovoltaic panel. The absorber design is critical because it can basically direct either we will produce more electricity, or we will produce more thermal power output. For instance, this kind of design with polymeric and roll bond absorbers is good if we would like to produce, or if priority is to produce thermal power output, and then what we can produce from electricity we can produce. But the idea is to retain at least the same level of the produced electricity in the PVT configuration as we would produce electricity in one single PVT panel. Of course, the main goal is try to achieve more improvement in electrical efficiency. Economic evaluation, very important, especially in PVT PCM collectors because of high unit cost of PCM. When I have checked the existing literature, usually economic analysis is poorly investigated because just focuses on the performance, and usually lifetime is between 4 and 15 years. That is a range. Recently, we have published one paper when we have checked what would be allowed unit costs depending from overall efficiency improvement for specific PVT PCM design. So which means that you can target specific efficiency, overall efficiency improvement, which mean electrical and thermal. And also you need to take care about overall cost. Otherwise, there is no sense to produce expensive PVT collector where tomorrow no one would like to buy it. I would like also, before my conclusions, to stress out that environmental aspect of each technology, and in this case in PVT PCM collector design, is very important. We have analyzed this environmental footprint for passive cooling approaches of photovoltaic panels, and the same thing is, or the same problem is also with PVT PCM collectors, where we should also take care, beside economic evaluation, we should take care about environmental aspect. And for PVT PCM collectors, the main problem is utilization of the PCM materials, which is causing like acidification effect and global warming effect, which needs to be carefully taken into account when designing PVT collectors. At the end, because my time is almost approaching, I would like to conclude that if we analyze present PVT PCM collector designs, usually electrical performance is lower than 20%, but it should be higher than reference PV panel. Thermal is mostly from 40 to 70%. As I said, there are some designs that can go even over 80%. Regarding the highest expected performance improvement, it is rich with water and nanofluids as working fluids, while the lowest we will ensure with air. But I said previously, we should think to incorporate PVT PCM collectors in HVAC systems, especially for buildings. The critical part of PVT collector is absorber design, because it has got the most significant part on the performance improvement. So we need to work more on more advanced designs that should be suited for specific climate conditions, because design is also depends from specific climate operating circumstances of the PVT panel. The problem with PCM is high unit cost, which means that we should work to, and we should seek for novel alternative PCMs, which are not expensive and which have good long-term physical properties. And finally, the more research efforts should be directed, beside performance improvement, to check economic and also environmental evaluation of different PVT PCM collector designs. I think that I have almost approached my time. So thank you for your attention. And I would like once time to thank you for invitation. And also I would like to state that this complete research was funded by Croatian Science Foundation. So my project, Smart and Hybrid Cooling Techniques for Siliceous Silicon PV panels. Thank you.
Thank you, Sandro. It was a really nice, interesting, and exciting presentation. This is not my special area, but even I was able to improve my knowledge on this topic. Thank you for the new information. I'm just checking my screen if there's any questions or any comments. And as far as I can, maybe you can switch back to your own screen so that we can see you. Okay,
can you see me?
Yeah, I can see you. I can see you right now. Okay.
Okay.
I see no questions or no comments, but maybe a quick comment or short question from my side. I wonder if David has any questions. David, do you have any? Well, I don't think David also has any questions. You're muted. Okay, go ahead, David.
Yeah, no, I have no questions. It's been very interesting, though. And
okay.
I really see relation with what we're doing.
Okay, thank you.
Thank you.
Sandra, I'm just wondering, you know, perhaps since you're living in Europe and the Green Deal is a really hot topic right now, perhaps David may not know it, but the European continent, the European Union has just decided to be a carbon neutral continent up to 2050. So we have some ambitious targets in terms of decarbonization. In this regard, most likely the demand for PVTs and other renewables, of course, especially focusing on the PVTs, the demand will be escalating tremendously. That means that the demand for the precious metals will be escalating too. So do you see any problem in near future in this regard? If we all switch back to PVTs as a replacement of fossil fuels? And also, you also mentioned the land use change and other environmental problems, but I see a bigger problem for precious metals in the future. What do you think?
Yes, thank you, Nuri, for this interesting observation. I can just, let's say, pull the same thing before I would answer with smart technologies. So nowadays, everything is smart, everything is, we have this buzzword, smart, we have a lot of electronic gadgets, but no one is asking, do we have a sufficient quantity of limited raw materials for production? The same thing also could be asked for lithium batteries. Do we have sufficient quantity of lithium? And of course, we are coming to this issue with photovoltaics. Yes, I agree. There are limitation of the regarding the quantity of silicon as raw materials. As far as I know, China and Russia, they have large quantities of silicon. But the good question is, do we have sufficient amount to produce those desired PV capacities? I don't have answer on this question because still there is issue with quantity of material. So we can say we have quantities, but the problem is with mining capacities. Like it is problem with lithium. There are specific quantities of lithium that are available, but mining capacities are not sufficient to cover production for lithium based on high demand. And the same thing would be also very likely for photovoltaic panels. But I'm more focused on the future, that very likely in the upcoming decades, the silicon PV panels would go in some kind of hybrid variants, like perovskite plus silicon, like combination, where we will basically reduce consumption of silicon, and by that secure larger quantities of production quantities of the PV panels.
All right, thank you for your comments. Maybe we can just leave this question as a message to take home for our audience. All right.
Yes.
Thank you again for your nice presentation. And I'd like to continue with David Whitten.
Thank you, Nuri.
Thank you. Could you turn off your screen, and maybe we can direct the screen to David now. David, it's your turn now. Okay. Could you share your screen? And before you start, David, we will be very happy to hear about yourself. Could you introduce yourself shortly before your presentation?
Sure. Okay, I think, I hope everybody can hear me.
Yes.
And see me?
Sure.
Okay. So yeah, I'm David Whitten from currently at the University of New Mexico in the US. This is in the southwest part of the US. And the energy questions are very important here because we're a relatively poor state, but we do have oil and natural gas resources. But we also have 330 days of sunlight per year, which means that we can certainly do much better than we're doing currently with solar and wind. But what I'm going to talk to you about is something we're doing right now. I've worked in energy conservation, energy production over the years with an emphasis on photochemically producing energy. Currently, though, we're focusing more on antimicrobial materials. And I think this is relevant because this is, of course, a major concern today in the time of pandemics. So I'm going to talk to you about this work, and this work involves conjugated polyelectrolytes, which are simply organic polymers that also have charge groups. They can be used in water. They can be used to some extent in organic systems, but they're very versatile in terms of their reactivity. And I'd like to share with you what we were doing. So I'll go to share screen now, please. And I hope I can see my,
we can see your screen, but not the presentation.
Yeah.
All right, it's already done.
Here's my
All right.
presentation, and I guess I want to use, I hope I'd like to go to slideshow.
Please.
And, oh, we should be here. Okay. Okay, so the title of my talk is Novel Light Activated Antimicrobials for Elimination of Viral Pathogens. And I'm very grateful to the opportunity of presenting what we have today. And this is the work of several people, several co-workers, and they're listed here. I'll say more about them, hopefully during the talk. But I'll get right into the materials we're working with and tell you a little bit about the background work that we've been doing over the last 15 years. So we're working with primarily cationic conjugated polymers and oligomers. As you can see here, some examples are polythiophene, which we've been working with, phenylene, ethynylene polymers, again, with cationic groups on them that render them water soluble. We've also been working with smaller units, and we had developed a lot of our work starting with the cationic polymers, but later we decided, can we break this down into repeat units? And then what governs reactivity, the repeat units or the length of the conjugated polymer? And so I'm going to use some schematics here where we'll be talking about oligomeric polymers, OPEs, I'll use that, and the term CPEs for the cationic polyphenylene ethynylene. And this is a representation of the polymer here, and where this is a polymer repeat unit. And so you can see the repeat units are shown in both these cases. Now, one of the questions we had when we started this work 20 years ago, probably, we knew that the polymers by themselves are fairly stable in the dark, but they absorb light, typically in the visible and near ultraviolet range. And so they're inactive in the dark. Well, not totally inactive, we'll see that. But when we excite them with light, we reach an excited state. We actually have two excited states involved, because every time you excite a molecule that's a ground state singlet, all electrons are paired. When you excite this, you move to a situation where you have two electrons in different orbitals, and they can either be paired or unpaired. Typically, you reach a state where they're paired, and this is a singlet state, and it's fluorescent and also quite reactive because you put a lot of energy into this polymer. Now, you can also reach a triplet state where the electrons are unpaired, and that occurs typically from the excited state. You can't directly excite the triplet state, but the triplet state has a longer lifetime and is typically rather reactive. Now, we'll be dealing with one particular property of the triplet states, and that is the ability to activate molecular oxygen in the environment. And this is an energy transfer step because the ground state of molecular oxygen is a triplet state, which is not terribly reactive. But when it's excited by energy transfer to an excited singlet state, you have a state that's very reactive, but is only transient. And that will be important to the work I'll be describing today. So we're interested primarily in the light-induced antimicrobial activity. As we'll see, both light and dark processes are important to us. Okay, well, what do these materials do? Primarily, they function to generate singlet oxygen. And they generate singlet oxygen in the proximity of a pathogen. And some of the pathogens we've looked at in our work are yeast. Our primary studies have focused mainly on bacteria. And I give an example here, E. coli, but several others I'll show you are also very effectively killed by our singlet oxygen activation. And they break down the bacteria in different ways. And then finally, antiviral agents. And I'll just show you one example of what we call a non-enveloped virus. You can see this is a virus that attacks bacteria, primarily E. coli. Now, in these reactions, you get products, and we can see the products often by transmission electron microscopy. And we see here, for example, the virus particle, which has a very definite structure, this structure is broken by the singlet oxygen and degraded. Yeast cells similarly are strongly modified and inactivated by this. And then the bacteria themselves, typically, we know a lot about what's going on in the bacteria. Under the influence of light, what happens is the contents of the bacterial cell, the nucleic acids and the proteins, are damaged primarily by cross-linking, as we see here in the killed bacteria. Now, there's also a dark process for the bacteria and for the others in certain cases. And what we see, again, by looking at transmission electron microscopy images, here we have cross sections of a healthy E. coli cell. And you have all these materials inside the cell. These materials are primarily the nucleic acids and proteins, as I mentioned earlier. Now, what we find is the actual damage in the dark, which occurs typically less rapidly than the light-induced reaction, but all of this is subject to modification by different things you can do. But what happens here is really quite different from what happens in the cells under irradiation. The cell's essentially empty, and that's because our materials can physically interact with the mosaic envelope of the bacteria. And as that breaks down, the contents of the cell leak out. This is very interesting because it's different from the the light-induced reaction, where the contents inside the cell more or less stay there, but they're inactivated and cross-linked and further don't do any of the damage that the live pathogen would do. Now, it's interesting, if we look at the properties and the reactions of these materials, we can coat them on surfaces. And that's very important to understanding and looking at the opportunities. And now we go back to the first intermediate that's produced upon excitation of our materials. If they're coated on a surface, when we reach the excited singlet state, we can detect the presence of our materials because they fluoresce very strongly. And we've seen this as a very general property. So before they decay to a triplet state, they have fluorescence. And when the singlet state is deactivated, as shown, you see that the fluorescence disappears. So you can tell whether your material is active or not active by the presence or absence of fluorescence. Now, how do these materials perform? Well, they perform rather remarkably. Here, what I do is separate out the light processes and the dark processes, and we're looking at log kills of bacteria. So for example, here where we have in 10 minutes, a 5 log kill, that means that we've killed 99.999% of the bacteria. Here, 99.9999. So we're really killing virtually all of these biological pathogens in both the light and the dark. The dark, for example, this would be 99.99% killing. And the bacteria I'm showing here are Staph aureus, which is a very reactive pathogen. We're using a laboratory stain, which is not. And here we have Staph epidermidis, which is easy to kill. It's also a pathogen and an opportunistic pathogen. And then a very dangerous pathogen, Pseudomonas aeruginosa. And you can see we get very good killing in both the light and the dark with all 3 of these pathogens. And we've seen many more. So interestingly, what we find is when we compare the killing at 30 minutes and at 10 minutes, they're virtually the same in many cases. The difference between this and this is, for example, the difference between 99.9999% killing in the light and 99.99 killing in the dark in 30 minutes, but also in 50 minutes. Okay. This is actually using, an oligomer, and the oligomers that we found are just as reactive as the polymers. I won't go into the differences, but the oligomers are easier to synthesize and generally have some advantages over the polymers. So the polymer structure, the number of repeat units is not really a major factor. After you go, let's say, this is just 1 repeat unit, and this is a small pathogen, a small molecule, and it has many advantages over the polymers. And we're focusing now mostly on the oligomers, but we still compare both. Now, this just gives you an example. These are polythiophene derivatives that we've looked at. In fact, this is a polythiophene that has about 60 repeat units. And this turns out to be a very good antimicrobial reagent. And this polymer interacts with a lot of different materials. And what I'm showing here is just the different fluorescence colors you can get by different reactions of the same antimicrobial with different components. It's quite reactive, and you can see the fluorescence can be green, yellow, red, or almost purple, and quite different. So what can we use these things for? Well, we talk about them being, of course, antiviral, antibacterial, antifungal. We have the bimodal activity, dark or light induced. We can tune the properties, and they're environmentally safe. And actually, we've done a lot of testing recently to show that they're not very toxic towards mammalian cells or humans. So the toxicity is low. The stability is variable. We can control this, and that's a good feature in terms of our using them. They're not likely to be hazards to the environment. We could see them being used as wipes, and we've made some wipes and seen that they're very effective as coatings onto a hard surface, permanent or removable, in solutions, of course, and in mixed formulations. Now, I'm going to focus for the rest of my time on the antiviral properties of our materials. And of course, that's relevant to the current pandemic. Now, we had studied several of our materials against a series of bacteria, primarily this T4 virus that affects E. coli, and the MS2 virus, which also affects E. coli. These are what we call non-enveloped viruses. And as you can see, when we look at reduction of the plaque-forming units here, we see that they're very effective in both the dark and in the light. And you can see the kind of damage we see is different in the dark and the light. With this is a large polymer With an oligomer, we also see differences between the dark and the light. The amount of reduction of activity of the virus here is really phenomenal. 6 logs, in this case in the dark, 6 logs in light. These are non-envelope viruses. And as I mentioned, these are pathogens you can look at and not be worried about danger to people working with them in the laboratory because they only affect E. coli. So these can be studied very well. And you don't need a special laboratory for studying them. So they're interesting. But the question is, are these very good models for the bacterium responsible for COVID-19? And the answer is they're not. So what we did, we found that we were able to do some studies against the actual SARS-CoV-2 virus about a year ago, when the pandemic had just sort of started. And so we could test them at our university in a microbiology laboratory that was set up and was actually working with this virus. And we studied both our oligomers that we had found reactive in different cases, including even an anionic charged oligomer. And then we looked at polymers that were cationic, a phenylene, a phenylene that has these very reactive cations embedded as a side chain. And then we looked at the polythiophene with an imidazole group in the side chain. So what did we find? Well, let's start before this by looking at the SARS-CoV-2 virus. It's an envelope virus. That means it contains a protein coat, and it shields the RNA that's inside the cell, which is used in the cell replication. Again, a virus is not a living particle. It's a non-living particle which only acts to reproduce itself. And of course, on the surface, you have the a protein coat protecting the nucleic acid. And then you have these spikes, which enable the virus to invade cells, including mammalian cells in this case. And of course, then it's toxic towards humans. Okay, so we looked at these different materials, and this shows you that the 2 polymers that we're looking at absorb well into the visible region. This is the polymer 4. This is the polymer 5. The oligomers, on the other hand, absorb more into the near UV, and but they still absorb light very strongly. And so we studied first with near UV light, and then subsequently with visible light. But what we found, and this was really interesting, is that we could verify that all of these materials are active in the light, but they're not reactive in any case in the dark. And we think, again, this is something that goes back to the structure of the envelope virus, the SARS-CoV-2. Okay, so what did we find? Okay, how do you detect the virus, the viability of the virus, whether it's active or inactive? Well, it turns out that these viruses that go after human cells also go after monkey cells. And what we have is a Vero E6 cell monolayer, and we treat this with a sample containing potentially active virus. We also stain this with a crystal violet stain. And so we have a very pretty assay here where we have the virus samples containing potentially the virus. Wherever there's a virus plaque forming unit, what you see is the color disappears. And you can count plaque forming units very easily in this case. And that's how we measure the activity. Okay, well, what do we find? Looking at these, here you have just the virus sample by itself with the inoculum, that's the virus it hasn't been treated with oligomers or polymers. And you can see that when you treat it with, and again, we're looking at log plaque forming units. So here what we see is the activation has been reduced by 4 orders of magnitude. So there's very little virus left and very low inactivity. And you can see in 10 minutes, in 15 minutes, and 20 minutes, there's no virus that's active. Okay, so it's different now with the second oligomer, which we won't worry about the title of the structure of at this moment. But what we do is we do see inactivation from all 3 oligomers. And in the absence of oligomer, there's very little inactivation until fairly long times. Both polymers are active against the virus, both by UV and also by visible light irradiation. So we found that these materials are generally reactive, but only under radiation, and that in general, different structures give us different inactivation rates. How do we understand all this? And I'll just quickly finish up with this. Again, here's a structure, a schematic cartoon of the SARS-CoV-2. And you can see again that we have this protein shield. Now, if this were a bacterium, this shield would not be protein. It would be a mosaic of different, like phospholipids and carbohydrates. The mosaic is fairly easy to penetrate by a molecule. But if we have our oligomer or polymer, it's not going to be able to disrupt the protein in the dark. Nonetheless, the structure of the oligomer or polymer will tell you something about how it will dock against the protein coat. And here we can see if we have a cationic one, it will search out for negative zones on the surface of the virus. If we have an anionic one, it will go to a different site where we might have overall a positive charge. So anyway, both anionic and cationic materials can interact with this protein envelope, but not easily destroy it. But again, what we think is when you have light present, the light will activate the antimicrobial material very close to this interface between the protein and let's say water, interfacial water. And that will allow the singlet oxygen that you make to go into the cell, into the cell and deactivate the components on the inside. Okay, so to give you a summary, we've tested both cationic and anionic oligomers and polymers. They all inactivate the SARS-CoV-2 virus when irradiated with UV or visible light in aqueous solutions. In the best case, it's very effective. At 10 micrograms per milliliter, that's a very low concentration. We have 5 log kills or inactivation of the virus. This works both in artificial light and in direct sunlight. And there's no dark reaction. And this shows that our materials and other potentially active disinfectants like quaternary ammonium complexes, they're not likely to be effective against the coronaviruses such as SARS-CoV-2 and future pathogenic viruses. We have previous studies that shows that these active materials are not active against mammalian cells. We've recently had that verified with a third party, a group that we paid to test these materials. And we've also done studies in our laboratory to find that these actives degrade to form water-soluble products not likely to damage the environment. So we're at the point now where we're pretty confident that our materials will be very useful by several applications, simply incorporating it into wipes or sprays, paints, clothing, and also other personal protection equipment. One of the best uses of these materials may be in water and air filtration, and we're looking into that right now. And Dr. Kaya here, as a visiting professor, has been leading our group now for the last several months, and we're getting some very promising results that I think may be useful. Again, I want to give my thanks, first of all, to the organizers for inviting me to present. And also, I'd like to thank my coworkers, Professor Kaya, 2 graduate students or 3 graduate students. I think I had Mohammed here, but I don't see it. And Professor Allison Kell in the microbiology department at the University of New Mexico, who's been really vital to doing all the work with the SARS-CoV-2. We can't work with that in our labs and would be helpless without her. So, and then Kirk Schantz, who's a former student and a close collaborator over the years, who has been responsible for first bringing us our attention to the phenylene and phenylene polymers, and then our support by the rainforest, where we're talking about that. This is I would say, the incubator for a lot of reactions, and also our intellectual property, and then the startup that we've been involved with, BioSafe Defenses, who have funded all these co-workers over the last couple of years. And finally, thank you very much again for the invitation and for your attention to my presentation. I'll be glad to take any questions.
Yeah, thank you so much, David, for your interesting presentation. I was really excited to listen to your presentation. I hope that you can come up with a really professional and commercialized product soon. I think this research is so timely in thinking that, or considering the fact that we still have this COVID-19 problem all over the world. And I see a great feature in your research. I think this is really important research for humankind. I was really excited to listen to you. And let me check my screen if there is any questions or comments. And I see Professor Ekmekci is thanking to you for your presentation. And I'm looking at the others, and I don't see any others. Maybe I can ask you one short questions. My background is from biotechnology. Of course, I'm not deep into this microbiology stuff. I'm just using the microbiology or biotechnology for biofuel production. But in the past, I also spent some great deal of time with the advanced oxidation processes, where we used ultraviolet lights or UV lights for degradation or destruction of organic materials. In this parallel, we also noticed that of course, as everybody knows very well, that the UV lights works as for the destruction of pathogens. And the main function of the UV light is to produce hydroxyl radicals that are very active radicals that destruct all organic materials. I wonder if you had observed any effect of hydroxyl radicals during this processes that you experience in your laboratory, apart from the light-activated oligomers or polymers. Do you understand what I'm trying to say?
Yes, I do. And that's a very good question. So basically, what we find is that we know that if we went to 254 nanometers, we would kill all of these pathogens directly by light absorption. But those wavelengths of light are very harmful also to humans. And you generate ozone and other reactive species. What we find is that we're using long wavelength UV, around 350 or longer wavelengths, 420. Under these conditions, you generally don't see much killing of the pathogens, but there's much slower killing if you just irradiate the let's say SARS-CoV-2. It takes many, many hours, but it will degrade with 350, 360 nanometer light.
Okay.
But going to 420 or so, that light does not damage the pathogens. So we're getting selective damage of pathogens in the range from, say, 350 to 450. And certainly we get radicals. The singlet oxygen, of course, is the principal reactive species that starts the ball rolling. And it will generate, it's a strong nucleophile. It's a strong electrophile. It's much more reactive than ground state oxygen. And so, for example, it can extract an electron and form superoxide anion, which rapidly protonates to hydroperoxy radicals. And that can disproportionate to hydrogen peroxide plus molecular oxygen. So we are generating very reactive species, but you're only doing that at a relatively low turnover. And so you're not making any of those intermediates lasting very long, persisting. So that's the trick here. And this has been well known. I mean, we're not the only people to investigate this, but the light activation under low, relatively moderate intensity light generates very corrosive reagents. But now we're finding we can use these. We've developed reagents that are not reactive at all in the dark. In fact, Professor Kaya has developed some materials that are reactive with light, but absolutely not reactive even against bacteria in the dark. So we're thinking that gives us a real edge, that the light activation only, avoids making very long-lived corrosive materials. Also, I should point out that what we see as a real advantage in our approach is if we can use these as air filtration and water filtration applications, we can get around some of the problems that have turned up with the vaccines, where people refuse to take the vaccines. I don't think anyone should object to our putting this in as a filtration device where none of the corrosive reagents will affect a person. So we're looking forward to that as a real driving force for adapting this technology.
Excellent. Well, thank you for your comments and the nice answers. And I think that was a very fruitful discussion. I really learned some new stuff from your side. Thank you again for your contribution. Let me see. I think there's one question from Professor Ekmekci. I'm just reading his questions to you. Can we use this novel process at HVAC equipments?
For what?
The equipment, I think it's HVAC equipments. I don't know what it stands for.
Oh, yes. Heating, HVAC, heating, ventilation, air conditioning.
Yeah. All right.
Yeah, absolutely. Yes,
okay,
we think that's possible. We're looking for partnerships to do this.
Excellent.
And I think this is probably the most important application that we could do.
Perfect. And we're looking forward to see your commercialized products very soon, especially for COVID-19. I hope you have some very efficient applications in the near future. All right. I saw an air conditioning. He just explained that it's an air conditioning, as you already explained. All right. By that, I think I would like to complete this session. Before we finish it, on behalf of the organization and on behalf of TÜBA, I have the honor to thank you our two esteemed speakers. Those are the invited speakers, David Whitten and Sandro Nizezik. I think that was a very fruitful session. At least for myself, I learned a lot of things from both speakers. I really thank you both And I wish you good and healthy days in the rest of the day. And good luck with your researches, and wish you a good day. Thank you.
Thank you. Bye-bye.
Bye-bye, and hope to see you in the future. Bye. See you.